Dear participants, welcome to TQC 2020. I'm Andris Sambainis and I'm the chair of the local organizing committee. We are looking forward to welcoming you here in the House of Nature of the new campus of the University of Latvia. Unfortunately, we cannot hold an in-person conference now. Dear participants, but fortunately, welcome to TQC 2020. I'm Andris Sambainis and I'm the chair of the local organizing committee. And there are many more participants. We are looking forward to welcoming you here. Of Nature.
My apologies.
Conference. We will have a full 4-day invited talks from Elena Kirshanova, Xing Wang, Henry Yuan, and Thomas Mons. 41 contributed talks. Conference. We will have a full 4-day invited talks from Elena Kirshanova, Xing Wang, Henry Yuan, and Thomas Mons. Dear participants, 41 contributed talks. TQC 2020. I'm Andris Sambainis and I'm the chair of the local organizing committee. Conference. We are looking forward. We will have a full 4-day invited talks from Elena Kirshanova, Xing Wang, Henry Yuan, and Thomas Mons. Dear participants, 41 contributed talks. TQC 2020. I'm Andris Sambainis and I'm the chair of
My apologies for the technical difficulties. We'll get back in a second.
participants, welcome to TQC 2020. I'm Anders Sambainis, and I'm the chair of the local organizing committee. We are looking forward to welcoming you here in the House of Nature of the new campus of the University of Latvia. Unfortunately, we cannot hold an in-person conference now. But fortunately, we can all meet online, and there are many more participants now than there would be for an in-person conference. We will have a full 4-day program with exciting invited talks from Elena Kirshanova, Xing Wang, Henry Yuan, and Thomas Mons, 41 contributed talks, as well as posters and hopefully lively discussions during the breaks on Slack. Thanks to our supporters, Baidu, European Regional Development Fund, University of Latvia. Thanks to the program committee for all the work that they put into putting together the program. Thanks to the local organizing committee for all of their work. And enjoy the conference. And we hope to see you in person here for some future TQC when it will be possible to have it in person.
Hello, everyone. Welcome to the first section of the TQC. Let's kickstart this invited talk. Before I introduce Thomas, our first speakers, let me say a few housekeeping rules instructed by the local organizers. Because we are using the online-only platforms, if you have any questions, please, using the Q&A chat buttons down at the room screen, write down your questions. We will, if you cannot do that, you can also using the Slack platforms, provide your question there. We will collect all the questions toward the end of the presentation, and we would ask the question at once. Okay. So our first talk is an invited talk. It will be given by Thomas Monzef from University of Innsbruck. And should we allow Thomas to share his slide?
So, good morning, everyone. I hope you hear me.
Yes, we can hear you, but we cannot see your screen yet.
That's about to come now. So, ideally, you should see.
Yes.
Perfect.
Yes.
And
so,
including a laser pointer. So
yes, clever. So Thomas would talk to us about some experimental content error correction from qubit loss to lattice surgery. So let's welcome Thomas.
So good morning, everyone. And thank you very much for inviting me to be part of this virtual conference. So I'm going to give a brief overlook about error correction, in particular quantum error correction in our Eintrap-based quantum computer. And I'll show you some recent developments in terms of how can you combine error correction, not only in terms of like the normal errors that you would assume to be there anyway, but how would you, for instance, correct for qubit loss, or how can you extend these methods that correct for qubit loss to implement new methods such as lattice surgery that allow you to then look into scalable processing in combination with error correction. So the outline of my talk is I give a brief reminder, especially for the PhD and the students not so much familiar with Eintrap-based quantum computing, on how do you do quantum information processing with calcium. I'll then give you an overview about our work on qubit loss correction. I'll show you then the lattice surgery experiments, and I'll give you an outlook on how can you put all of those experiments into a neat little 19-inch rack unit to show you how much room do you actually need in the lab, how far has technology evolved to give you a feeling what you want to do there. So how does Eintrap quantum computing work? Essentially, all you have to take is take these 4 plates, apply ground, on two of them, apply RF on the other two, and you will get effectively a radial confinement. Then add these two tips on the left and right, apply about 1 kilovolt, and you'll get in total potential that's essentially, let's say, a cigar shape. If you now load ions in the center, they will automatically align into a neat linear string, and this linear string of trapped ions you can then manipulate. For instance, the blue beam here illustrates how you would cool and get the ions to fluoresce, which you then can detect on a camera on the side. And then red beams indicate that you can, for instance, illuminate the entire string collectively, or you could have individual beams, 10 ions at the bottom, and if they are bright, you would call them 1. If they are dark, you would call them 0, and so you immediately have the connection from, let's say, AMO physics to quantum information. How does that look in detail? So for calcium-40, we have a ground state, we have a metastable excited state, and this is on a laser light field. You'll excite the electron, it will decay again, you scatter photons, and on a camera, you would see a bright spot. However, if you're in excited state, if you switch on the light field now, you wouldn't scatter any photons, and on the camera, it would be effectively dark. And so you see, from a spectroscopy point of view, you would call that the D state, it's the dark state, or for information, you would call it 0, whereas here you would call it spectroscopically the S state. You could call it the bright state or 1 state, depending on which language you prefer. Or you can also refer to it as spin up and spin down. It's a effective two-level system. How well can we distinguish this bright and dark? You can look at the fluorescence, as you can see at the bottom here. And there's a huge difference between the bright and the dark state on the camera, such that even notably faster than a millisecond, we can distinguish these two states better than 99.5%. So how do you then build a computer from that? And the initial ideas were coming from Peter Zoller and Ignacio Serac. So you have a two-level system. That's just your qubit. But you wouldn't know, like, how do I manage to have one qubit talk to the other one? And there, the joint potential comes into play. So we have the electric field. It gives you a harmonic oscillator where the entire string is shaking around. So you, for instance, could have the center of mass mode. It's just a harmonic oscillator. And the trick is now that you can imagine this being a two-level system. It couples to the motion, but there would be another atom next to it where it could also couple to. So if you look at the joint level structure, you have both the two-level system by the harmonic oscillator. The coupled system would look like that for the particular settings that we have. In here, you have the ground state, the excited state, and the phonon number. And what you can now do is, if you send light in resonant with the carrier transition, it would be internal manipulation of the qubit, whereas if you use the sideband, you suddenly have all the atoms talk to each other via the shared motion, and this can be then used to create entanglement. What are the tools that we prefer to use? So for a long time, we have used an like a collective beam, which illuminates all the ions from the side. Experimentally, that's really easy to set up. And we can create any XY rotations on the Bloch sphere of your qubit in about 20 microseconds with the fidelities of better than 99%. In addition, you can use the very same beam just to send in a bichromatic light field, which is slightly detuned from the sidebands. And as I mentioned, these sidebands allow you to couple the ions. And if they are coupled, you can then create entanglement. This Möllmer-Sørensen interaction gives you essentially from the absolute ground state, you can get to something like a huge Z state. It's an sigma x squared, and the way you can think of it is like you start in the ground state and you end up in 0, 0, 0 plus 1, 1, 1, and ideally regardless of the register length. And we've been able to use this tool with up to 14 qubits. And to give you a feeling how well that works, for 2 qubits, we have achieved better than 99% fidelities. These sets are really easy to set up. However, they don't allow you to have a universal gate set, which you need to have in order to implement arbitrary quantum computation. I mean, you look at it and say, well, everything is collective. There has to be something which allows you to pick up a single ion and manipulate only that. What we used to do there is we had one beam which we were shining on a single ion, and we could move that beam around to induce stark shifts. And the combination of these local stark shifts with collective operations allows you to implement any local operation and any arbitrary local operations in combination with the Mermer-Surrance interaction is universal. However, if you then talk to the theorists, they would claim, well, this Mermer-Surrance interaction is wonderful, high fidelity, very resilient to many effects in your Eintracht quantum computer, but it's coupling everything with everything. I'd prefer you to implement it just on a subset. And so we made some changes to the system. We now have the capability of shining in light in parallel on a subset of ions, both doing that resonantly with the qubit as well as doing Stark shifts. And based on the ideas up here, we can also now apply bichromatic gates on just subsets of your ions and get their gate fidelities of 98 up to 99% now. How do we do that? We essentially were picking up ideas from the cold atom community, where these routines are used by, for instance, Adam Kaufman, Mark Zeffman, Antoine Brevet, before they used spatial light modulators and so on. All you have to do is take two ions, cross them, and what you then get by applying two RF fields on those is a pattern on your camera that looks like that. So you have here frequencies, F1, F2, F3, and so on, and these off-resonant spots. Essentially what you're doing is you go one frequency up, and then you go one frequency down. The cool thing is that in that case, along those axes, there has been no frequency shift, but there has been a shift in position of your laser beam. And now all you have to do is scan the frequency to pick the right ions. And there are a couple of advantages. So there's no frequency shift. The undecided spots and the top and the bottom are off resonant. If you, for instance, say, I only want to work with two ions at a time, then the power consumption that you need to have on NIMBET is constant regardless of the register length, and you can maintain good beam quality due to the AOMs that you're using. You can see here a scan where we had 18 ions in the register, and you essentially just have to dial in the frequency on your DDS or AWG and you're done. How far does that get you? We can control even the individual phases on the RF fields, as you can see here. And for proof of concept, what we are doing here is apply in parallel Ramsey experiment on qubit 1 and qubit 4, where we on purpose shift the phase of these two relative to each other to demonstrate that we have individual control on both the beam where it's shining as well as its phase and frequency. Then how does it also work with the MS gate? So yes, it does. So we've, for instance, been loading 4 ions. We illuminate the subset. And what you can see here is the upper triangle. This upper triangle essentially tells you what's the fidelity of this entangling gate operation between qubit 1 and qubit 2, qubit 1 and qubit 3, qubit 1 and qubit 4, and all of them. And this was data already some time ago. We have now better data, but on average, we managed to get to about 97, 98% gate fidelity, regardless of which subset we were picking. And that gets us also, that works quite well. For instance, for 10 in a 10 ion register, picking the first and the 10th ion, we still get fidelities on the order of 95%. One of the limitations there was cooling. So we learned that we need to cool many more modes. We implemented polarization gradient cooling, which is a technique that people, especially in the cold atom community again, are very familiar with, that helps us to push these numbers farther up now. What's the comparison? So how much better is it really? So we used to have this global MS gate. This global MS gate gave us fidelities on the order of 99.5% for 2 qubits, and then was dropping off quite fast for 10 qubits. And that drop off actually was quadratically. And the reason for that are twofold. First of all, THZ states are very dependent on collective noise, frequency and phase. And so where is this collective frequency and phase noise coming from? First of all, we have a single laser for the entire register. So any kind of small frequency fluctuation affects the THZ states most sensitively. And you see that, and when you go through the mass, you actually see it's quadratic. Another way of looking at is why does it drop quadratically? Is also the MS gate couples all ions with all ions, and so you could say it's always two-body interaction. So how many two-body interaction can you write down? It's quite clear. It's like if you have an n qubit register, you have n, where like n qubits, you pick the first one and you pick any other one. So you have n times n minus 1. So essentially that scales with n squared. any kind of little error that you have there, again, frequency, phase, amplitude, gets multiplied by this n squared term. That's why this curve exactly ought to behave like a quadratic decay. However, if we now pick a subset of just having light on 2 qubits, we did a quick test run there. We see that it's essentially flat for 10 qubits upwards, and probably also beyond, but we didn't have to push there yet. So what do we want to do with that? It's an ideal toolbox to push towards error correction. And this is work that we've been carried out in particular with Philipp Schindler, one of my colleagues in Innsbruck, and Markus Müller, who was until recently in Swansea, but he's now in Jülich. So how does like error correction, what does it look like? And so if you open up any textbook, quite often you will see a strong recommendation to look into topological encoding, and the code or the idea behind it is, first of all, pick several physical qubits and just do a special encoding in such a way that you call several physical qubits one logical qubit. And then this redundance between several physical qubits allows you to detect and ideally correct errors in your system. There exist various codes with thresholds on the order of 10 to minus 3, even 10 to minus 2 if you think about the surface code and color code. The main problem is whether you use a color code, a surface code, or anything else, the encoding tends to be, let's say, easy, but implementing gate operations on those codes is really challenging. There's one rule, especially for the students out there to remember. So one really neat feature would be, imagine you could have, you want to do a Hadamard gate on your logical qubit. Wouldn't it be great if all it would take to implement a Hadamard gate on a logical qubit to implement this Hadamard gate on all of these individual qubits, and just because of some nice symmetry of your code, that would immediately give you a Hadamard gate on the logical qubit. The color code actually has this property for all Clifford gates. So for all Clifford gates, you can implement them just doing it on the individual qubits, and it corresponds to the same operation on a logical qubit. However, there's also a statement, a proof essentially, that you can't have a universal gate set that's also transversal on your logical qubit. But that would be the holy grail from an experimental point of view, because it would facilitate the implementation of error on computation on logical qubits significantly. And some of the stuff that I'm going to present to you is essentially, let's say, rules of execution that allow you to bypass some of these limitations. So what's the minimal instance? We prefer, for instance, to work with the color code most of the time because it has this property that it's transversal for Clifford gate operations. So here you can see something that Markus Müller has worked out. Take 7 qubits. We aligned them here just for illustration purposes in 3 plaquettes, a blue one, a red one, and a green one. And the definition of this logical qubit is that it belongs to the stabilizers, that all of these stabilizers, so the Z and the X of blue, Z and the X of red, Z and the X of green, all of them need to be +1. And if you do that, you have, as you can see, 7 qubits. You have 6 constraints, so that means effectively there is a subspace left open, and the subspace then corresponds to your logical qubit. So for purposes of illustration, how do we implement that? It's quite easy for us in the lab. So you can start off with a state that you can see here. It's 1 0 1 0 1 0 and so on. This one already fulfills the stabilizer criterion that all sets ought to be +1. And if you take that state now and apply the MS gate on just 4 qubits, you essentially create a GHZ state there. And this GHZ state then also fulfills the property of your Z stabilizer being +1. And we used to implement that just on red, blue, green, and you're done. You have your logical qubit. At that point, you would ask, like, how does error correction then work? And I'm just going to briefly help you along those lines. So the idea is this, and we're just doing that for X because it works the same way for others as well. Imagine all stabilizers say everything is +1, then everything is fine, and you would say, well, there was no error. Now imagine that the green one is -1, and you could say, well, obviously, so that's -1, something went wrong, but you could say, well, which qubit could you pick so that the green one gets a -1, but all the blue and the red one remain unperturbed. Now you see only qubit 7, that's the only one where you could induce an error without also affecting blue and red. And so you can immediately deduce if this one, if the green one is -1, then it had to be qubit 7. In a very similar way, if you, for instance, have the blue one become minus, then you know it's this corner. And you can go on all the way through, for instance, if you have all of them being minus, then you know it had to be the center qubit. That's the only way for you to get an error on all 3 plaquettes. And in addition, finally, that's the cool part about it, it's transversal. So we have implemented this qubit, this logical qubit, and we have demonstrated, for instance, X and Hadamard gates on these with fidelities on the order of about 90%. What's the big problem? Well, I mean, the code was initially developed to compensate for errors in the code space. So everything which is not in the code space, let's say everything which is not an X or Y or Z error, you can't correct for. So what could happen? For instance, one problem, and usually that is only one error. So what happens if you have more than one error? Think about this example again here. You could have one qubit, let's say if 1 and 4 had an error, then the parity of this one would still be correct because you get a minus and the minus gives you a plus again. But here you would get a minus. So the green one would say there's something wrong and you would accidentally deduce that the error occurred on qubit 7 and not on 1 and 4. And so there are errors which you can't compensate for, which are, for instance, 2 qubit errors. Another problem is we've been assuming that we are working with a 2-level system. Here you can see the spectroscopic scheme of calcium, or the level scheme, and obviously there are way more levels there than just 2 levels. If you have any leakage, for instance, in the initialization, you don't end up with minus in the S-1/2, but in the S+1/2 state, or you accidentally couple to any other of the excited states, you left the computational space and your error can't be corrected for that anymore. In a very similar fashion, you can also lose your qubit. I mean, we can lose ions from our trap. It happens very rarely. So for instance, maybe once or twice a day, but not much often. Whereas if you think about photons, you can lose photons quite easily. It's just absorption in your material. If you think about superconducting qubits, they are anharmonic harmonic oscillators, or like anharmonic oscillators. And in that case, you can get accidental excitation to, for instance, these 2, also from not just 0 and 1, but to level 2. And that would also be leakage, which you can't correct with normal error correction. And finally, if you think about Rydberg atoms, you have them excited very far up. And for instance, recent experiments of a colleague of ours in Sweden by Markus Henrich were showing that if you are really highly excited in order to make sure that your Rydberg interaction is really fast, you also have the problem that black body radiation, simply from your vacuum chamber, can result in accidental ionization of your atoms. And then again, you lose your atom from your quantum register. And you'd like to have means of compensating for that while staying in your logical qubit. And so you'd look at all the books that are out there, and you say, like, what's a good way of doing a correction for qubit loss? And you will stumble upon the code from Markus Grassl, which is actually quite old. And the idea back then was essentially a teleportation scheme. So you start off with a certain input state, you distribute it over these 4 qubits, and the key part here to know is you really need to know where you lose your qubit. So assuming you know that you lose your qubit up here, you can measure here, you do a teleportation step with feed forward, and you can still retrieve your initial qubit, your initial information in that system. One big problem is, as I pointed out, you need to know where it is, and you need to know that qubit is actually lost. So how do you know that? So you want to do something like a QND detection of the presence of your qubit. With thread 1, luckily, that's quite easy. Imagine you take this ancilla qubit. This ancilla qubit's goal is to tell you, did you lose your computational qubit? And one way of doing it is using this Melmer-Sørensen interaction and using it in such a way that it essentially does a pi pulse, a collective pi pulse on both qubits. At that point, you would say, well, what's so great about doing a pi parse collectively on both qubits? The key point there for you to keep in mind, the MS gate is a sigma x squared operation. So if you have 2 qubits, you get a bit flip on both of them. However, if you have just 1 qubit, you are left with this x1 squared. X1 squared is the identity operation. So the Melmer-Sørensen interaction essentially does either a bit flip if you have 2 qubits, or it does nothing if there's only 1 qubit there. If you follow up with another, let's say, X operation on both qubits, you end up now with something where if the qubit has been there, it's a pi parse plus a pi parse. This gives you identity operation. You simply measure there. However, if the qubit was not there, this gives you identity operation. This gives you a bit flip, and you can use this ancilla to really determine whether you lost your qubit or not. How do we do that now? We on purpose induce qubit loss. So we couple to another excited D state where we just detune the laser to the respective frequency, and then we look at the excitation depending on the rotation angle here versus the ancilla. And so you can see data here now where you see the computational qubit and the excitation there, and on the ancilla qubit, which is the blue stuff, you see perfect correlation between the two. We looked at it in more detail, both in the case of having 2 qubits there just as a proof of concept non-collision measurement, as well as in case of having another 3 qubits there, as we need later on to look into the fidelities. And we can see that we have about 90 to 95% process fidelity of implementing this QNT detection of the qubit in the system. We implemented that now with the Gassel code, and we get about 80, 85, up to 90% fidelity. The algorithm works. The problem is this algorithm obviously only works for qubit loss. If you would have had an X error or a Y error, that's not something it was designed to do for. And another problem is you start off with 1 qubit, you encode them in 4, you end up with 1 qubit again. So you're leaving the encoded space, and because you leave the encoded space, if anything goes wrong at that point, you'd be screwed. You can't correct for it anymore. So could you do something like loss correction without leaving the encoded space? And yes, that's true, it's possible. So Tom Stace figured out the way in 2009. If you think about the surface code, where your qubits are encoded both along the lines of plaquettes. So you would have, for instance, here a crossing with qubit 1, 2, 3, 4. You could say, well, here is my code space. That's one line of thought. If I now lose this qubit 1, one way of can I just redefine my logical qubit to then do a detour? It's similar to like you drive with your car. There is a crossing you can't go through. Well, you just your navigation in the system tells you like take the other block, get around it. So Tom Stace was working with that. It all works. We looked at it now in particular for a 4-qubit proof of concept example. You have to redefine your stabilizers, as you can see depicted here. And we went to the lab and implemented it. The encoding for us is just a single MS gate. We on purpose induced the loss. We used our QNT loss detection scheme to then trigger a restoration process in such a way that the remaining 3 qubits then have exactly the stabilizer properties that we intend to do. And more details can be found in this archive paper together with Markus. Where the experimental realization has been done by Roman Stricker, a PhD student who I can strongly recommend. He's not finishing this year, but if anyone wants to work along those lines, get in touch with us or get in touch with Roman. So what you can see here is we started off with an eigenstate of the Y state or Y operator. We then do the loss detection and we infer it again. You see that starting off with almost 100%, we managed to receive or maintain the properties of our Y eigenstate with about 80% fidelity. These code deformation tools, however, get you notably farther. Once you say you have done this loss correction, you have done this detour in your code space, can't you do more than that? The one line of thought there is, imagine you have something like a surface code, as you can see on the left-hand side. You have something like the color code on the right-hand side. You could say, wouldn't it be great to be able to combine these two? So why would you want to combine them? Surface code has a very high threshold and has some nice properties in terms of implementing it on hardware, such as solid state systems. The color code has these nice properties of being transversal for all Clifford gates. So you could say, well, if I merge them, if I am able to move around between these two, I could have the best of both worlds. So this is something that we've been working on with Hans Briegel and Henrik Bulsen. So the idea was, let's look at that example. The idea, like you could say, we can move information from one code to the other. If you can move it there, you could suddenly think of, and that was what I was pointing out in the beginning, imagine there would be one gate you can easily implement here, but not here, and vice versa. What you could do is you could simply say, well, if I need to do a particular gate here, let's do it here. If I could do the gate easier over there, let's just move it over, do the gate, and bring it back again. Another advantage is, for instance, stuff that Steve Lemire and others are working on in Sydney. You can think about adapting the code depending on your noise model, so that you would say, if I have more Z errors or more X errors, can I adapt the code for that? Another cool aspect behind it is, once you have this interaction and you think about this being two qubits, you could have an interaction between these qubits and could do teleportation between them. And once you can do that, you can implement something like a CNOT gate between logical qubits. And so with Henrik and Hans Briegel, we've been working then on a minimal instance. And so what we've picked was an example of the surface code where the smallest instance is just a 4-qubit logical qubit, 2 of them. And the idea was, can we then create something like a merge and split operation again to create a logical Bell state? And so what you can see here now is we started off with 4 qubits. This is the first logical qubit on the left, which we just call A. And then there is a second logical qubit, which we call B. There are the respective code stabilizers, followed by the implementation, where you can see we have about 93% in the raw data. And if we take post-selection on the stabilizers, we have better than 99% fidelities on these gates. We merge the codes using 2 ancillars. So you can see that we are really working with 10 ion qubits in our processor there. You get the merged code with the respective properties out, where you see here, we have in the post-selected data about 98% fidelity. And then we split them again to end up with a Bell state in your logical system, where you really have the X, Y stabilizers, X and Z stabilizers at the O to B with a little bit of a phase shift. That gets you 75% fidelity on the post-selected data, but even about 60% fidelity on the non-post-selected data in our system. So that was quite good. We were happy to see, look, we now have suddenly a tool set to really start working on creating interaction between logical qubits, but how far can that get? And then the theory support by Hans and Henrik noticed, well, once we get that going, you can think of it like an XX operation. And once you have that there, you're not far away of thinking along the lines of teleportation. And so the idea there is you have one logical qubit and another one. And you would simply teleport this psi state on your first logical qubit onto the second one. And as is normal for teleportation, you likely have to do some kind of correction step, whether you want to do post-selection or not, like post-selection or feed-forward. In our case, we opted for doing just post-selection rather than doing the full feed-forward process. And what you can see here is we start off with various encoded input states, for instance, 0, 1, or a superposition. And you can nicely see on the output state, either with, again, 0, 1, or then in the other case, the plus state with fidelities between about 80 to 90% in the post-selected data. And I think just on Monday, we had the archive paper out on these publications. So what's going on else? In Innsbruck, I'm just going to give you a brief outline of what's going on before I'm slowly running out of time. So we've been working on getting cloud access going to our devices. We have put everything into 19-inch racks, working on improved Eintrap with colleagues from Infineon to push towards more qubits. So obviously we like to work with theorists again and again and again. The problem usually is a question of language. So I mean, as most of you are familiar, it's like your Y. Do you have in your sigma Y is the minus at the top right or at the bottom, and do you define it with an I or not, and stuff like that? So we said, let's opt and do a slight change. There are more and more software development kits for quantum processors. Why not just use those and create an interface so that theorists can run their code directly in our devices? So here you see one example based on Circ. There is already an ion device defined in Circ. That was work that was done by our colleague Ken Brown in the US. And with typical gate times at the end, all you have to do is say, initialize please 2 qubits, apply a Hadamard and the CNOT gate, and with that you would immediately generate a Bell state, and you can send that code to Innsbruck and have it directly executed on our devices. To date, we support the software development kits from Circ, KISS, Quest, also ByTicket from TQC, as well as PennyLane from Xanadu. In addition, we are working, for instance, here you see Silke, who's a PhD student of ours, together with Clemens Rössler at Infineon, to work on better traps with higher performance, which is, for instance, a project supported by the EU. And the goal is then to say, this is a lab as you would see it if you, for instance, visit us in Innsbruck. Here is the control desk where the PhD and postdoc students are working. You have a couple of lasers and a vacuum chamber over there with air conditioning and vibration insulation, all the stuff that you have. But ideally, we wanted to move on now and have everything in two 19-inch racks, and we managed to succeed there. So everything which used to be 100 square meters of lab is now essentially 2 by 1 meter by 2 meters, with the lasers, the light distribution, everything in there. And actually here, besides one year, there is the vacuum chamber, which you can see here. So that's when you pull out this shelf, there is the vacuum chamber on a vibration platform with the connections at the front and all the control electronics. Here you can see the ion trap inside the vacuum chamber. Current, both racks combined have the power consumption of about 800 watts. A few bits and pieces are still missing, but the total consumption is then ideally going to be less than 2 kilowatts. That means if you drink a lot of tea and you have a water boiler, I mean, your water boiler is about consuming as much power as our entire ion trap quantum computer. And that's just made to be compatible with a normal office environment. We have loaded ions here, and as you can see in this little video at the bottom, it's a string of 50 ions, and if we illuminate it with the 729 light, they would start to blink, and it gives you a good impression of what the 0 and 1 encoding would correspond to in terms of quantum computing. And obviously, we now want to push for control of these entire 50 qubits. How far does that go? I mean, we managed to load even more than that, more than 100 qubits, and we're working together with Fraunhofer to have all the optics in place to really control all of those ions. And with that, I'm coming to the future goals. So we want to now push towards controlling these 20, 30, 40, 50, even more ions. We need to improve the fidelities, get faster gates to then work also a little bit on faster detection. Ideally, for reasons of scaling, we need to look into 2D to then push towards large entanglement in larger systems, which will be done in combination with error correction and error mitigation methods. Where our main focus is metrology and computing, but we also have experiments in Innsbruck, for instance, focusing on simulations as well as communication, for instance, by Ben Lennion and Tracy Northup. And the ultimate goal for us there really is to keep a qubit alive, to do computation as long as possible with as high fidelity as possible. Here you can see the team that's actually with Rainer Blatt and Philipp Schindler and Christian Roos, who's working on the simulation, and a couple of others. In particular, I'd like to point out the theory support, such as Peter Zoller, Markus Müller, Joe Emerson, Christine Muschig, and a couple of others, as well as the funding that we have in Innsbruck there. And with that, I'm already finished, and I'm looking forward to your questions.
Okay, so I would clap on behalf of the audience. Thank you very much, Thomas. So yes, we actually have 2 questions from the audience. I wonder whether you could see that from your Q&A.
Okay.
Okay. So let's go. Let's answer the first question by James Wooten first.
Yeah. Would you be able to implement QDID code to explore some of the more exotic custom subsurface codes? Yes. So we have one project The right guy for that is just entering the room. It's Martin Ringbauer, where we on purpose are looking to go beyond qubits and just do qubits. On some of the slides, we were showing that we have 2 ground states and we have 6 excited states. And the MS gate can actually also be set up that you can couple more levels. And so we are looking into QDIT codes, not just in context of surface codes, but also generally to encode more information per ion. And that's work that we can do and very likely will do on the long run. Yeah.
Okay.
And then there is a question by Ingrid Strandberg. I'm having some trouble understanding the geometrical images of the columns. So kind of some good reference to read. A good reference for surface and color codes. Honestly, for the color code, I would really recommend the work by Daniel Nick, which was the science paper. Other than that, Markus Müller has been working on some very intuitive ways of thinking about the color code. And on the surface code, there is quite good literature out there from the team by IBM. So that would be Jerry Chow and Jay Gambetta.
Okay, so we have a third question coming in. So,
yeah, so
can you explain
the detection of up and down state by looking at the scattered light by Soumyakanti Bose? So I'll just go to that slide quickly. So we have a ground, sorry, just get the laser pointer going. So we have a ground state and we have an excited state. And if we send in light on this transition, which is just blue light at 397 nanometers, if we are in the ground state, you would excite the electron, it will drop down again because it has a short lifetime of only a few nanoseconds. By going up and down, up and down, up and down, you would scatter photons on the 4 pi. We have a lens on the side, which is, for instance, a photomultiplier or a camera, and they will collect some of these photons and you would see them on a string here. And then obviously, if it's bright, you would say, well, that was the ground state. If it's dark, it's been in the excited state. For instance, when you look at it with a photomultiplier, you would get either a high rate or a low rate. So you would say in a certain detection window, you could have counts which are essentially 0, or for the excited state, we tend to get something like about 50 kilocounts per second or so. And so what you can do is you can easily go to even say 1 millisecond would then give you either 0 counts for the ground state, the dark state, or 50 counts for the bright state. If you now make a rule of thumb, 50 counts Poisson distribution, that would be about 7. So it would be 50 plus minus 7 would be the width of your Poisson distribution. If you put a threshold at say roughly 20, you can essentially perfectly distinguish bright and dark. And that's what we do either on a photomultiplier as well as on a camera to distinguish the two. And actually, if you think about this video, this is also a way of here you can see these, all of them being in the ground state. And then if we illuminate them to the excited state, which we don't do in a controlled fashion here on purpose, just for getting this video going, sometimes they are in the excited state. And yes, if they are in the excited state, it would turn dark. If you evaluate the data, you would then get 0, 1, 1, 0, and so on. I hope that answered your question.
Okay, in the time constraint, so we have one last question. That's by Mosent.
Okay. So that was by Mohsen Ratzavi. So I was wondering about the prospect of getting 99% fidelity in your latest experiments, where currently you can achieve 80 to 90. What are the limiting factors? So if the challenging part, or like it's good and bad at the same time, our current focus is not so much to fix all the little issues. Our main focus for the moment is to get all those things automated. So we have, for instance, been working to give you a feeling. Imagine you have those 50 qubits here. We can illuminate any two. So you never seen me. I think the video is off. So like we can illuminate. we can send light on any of the 2 qubits in that register. And if you could say, well, any of those 2 qubits in this 50 qubit register, that means you have 50 times 49/2 combinations. That would mean you have about 1,000, roughly, different 2 qubit gates that you could set up here. And manually, I don't want to tune up 1,000 entangling gate operations. So these have to be tuned up automatically. That's our main focus. And so we've been working on that. So for 2 qubits, our automated tune-up gets us to fidelities of about 99.5%. If we now add qubits, the tricky part is how to evaluate this fidelity. Imagine you want to talk about 2 qubits, but these 2 qubits are in a 5 qubit register. And actually they happen to be qubit 2 and 4. So suddenly each of those 2 qubits has 2 neighbors, and the center ion even has 2 neighbors left and right, which are part of an interaction. So we can set up the MS gate to be better on qubit 2 and 4, for instance, but there will be crosstalk to qubit 1, 3, and 5. And so it's really a question of how honest you are in your evaluation on the performance of the gates. So I would argue we have the automated capabilities to get to better than 99% fidelity. What we need to work on is to suppress these undesired coupling to the neighbors. That's a question of beam focus and beam shape properties. That's exactly why we're working together with Fraunhofer. So we have we are going to get a new addressing unit by the end of June. And then these numbers should get us back to about 99% fidelities.
Okay, thank you very much. I think that's a wonderful talk. So we would move on to our second talk, which is a contributive talk. Could Akin share your screen? Okay, good.
All right.
So the second talk will be given by Akin Tiku from UCL. Am I correct? Oh, sorry,
yeah,
University in Sydney, yeah. Yes.
That's right.
And the title is Non-Additivity in Classical Quantum Wiretap Channel. So welcome. The floor is yours.
Thank you. So thanks to the organizers for allowing us to present at TQC 2020. Today I'll be talking about some joint work with Mario Berta and Joe Rennes on exploring the boundaries between classical and quantum Shannon theory in the setting of private communication. So let me first switch off my video and use the spotlight for the purpose of the presentation. And so let's cover first some motivation behind our work. So most of the basic settings within point-to-point classical information theory have already been fully resolved, and most of the open questions are really confined to the setting of network classical information theory. However, the quantum analogs of those very point-to-point settings are still only just partially resolved. And it is therefore only reasonable to wonder whether exploring the boundaries between classical and quantum Shannon theory within this setting might help us in deepening our understanding of the latter. So first, let us cover some background about classical noise. Sorry, about classical noisy channel coding. Sorry, I think there are some disturbances there. So let us first cover some background about classical noisy channel coding. So the basic task considered at hand is that we would like to send some classical information reliably over a noisy classical channel N. And in order to do so, we first encode our information into an error-correcting code of block size N, send it over N copies of the noisy channel, and then the receiver applies some decoding map D onto the code block in order to infer the logical message M. Now, the efficiency of any such scheme for a fixed channel N is given by the transmission rate R, which is simply the ratio between the number of channel uses and the logarithm of the cardinality of the message set. Now, the optimal rate for any such scheme is given by the so-called capacity, which is characterized by Shannon's noisy channel coding theorem, which tells us that the capacity is equal to the maximization of the mutual information between the input and the output of one copy of the channel maximized over all possible input probability distributions. Now, what is nice about the noisy channel coding theorem is that it gives us a single letter expression for the capacity. This means that the capacity is solvable and is a tractable optimization problem that can be solved using some polynomial time algorithms, such as, for example, a Blahoud-Arimoto type algorithm. Now, one may also consider sending classical information over a quantum channel. In that particular setup, we're also allowed to use CPTP maps as encoders and decoders. And an achievable rate for any such coding scheme is given by the so-called Holevo information. Now, the Holevo information is simply the mutual information between some auxiliary classical system that is classically correlated to the input of the quantum channel, where the input of the quantum channel is some quantum state rho A. And the mutual information is evaluated on a classical quantum state that we are also optimizing over. Now, the Holevo information might be achievable, but it is not optimal. And this was shown in 2008 by Matthew Hastings, who proved that for a choice of random quantum channels, the Holevo information becomes non-additive. What this means is that if we choose two random quantum channels, N and M, and we use entangled inputs at the encoder, then the Holevo information of the tensor product of these two quantum channels is strictly larger than the sum over the Holevo information of each of the channels individually. Now, what this means is that essentially there are achievable coding rates that are greater than characterized by the Holevo information. This implies then that the classical capacity of a quantum channel, which is characterized by the Holevo-Schumacher-Westmoreland theorem, is only lower bounded by the Holevo information and is instead characterized by something that we refer to as the regularized Holevo information. This is simply the normalized Holevo information evaluated on n copies of the channel in the infinite limit. Unfortunately, this is only a multi-letter expression because it involves an intractable optimization problem over an infinite number of channels, and it does not uniquely characterize the capacity. Now, this does not rule out that there might exist a single letter expression for the classical capacity of a quantum channel, but it does mean that it will not be given by the Holevo information, but instead it will be characterized by some other single letter information quantity. All right. However, we said that using entangled inputs at the encoder is necessary in order for this non-additivity phenomenon to occur. And in fact, if we're using a noisy channel that destroys quantum correlations, a quantum channel that is entanglement breaking, then the Holevo information actually becomes additive. And an important subclass that will be of interest for our work is the so-called classical quantum or a quantum classical channel. These are channels for which either the input or the output is constrained to be diagonal in some prefixed orthonormal basis. All right, so let's consider our setup. So for our work, we considered the wiretap model. The wiretap model considers the following task. Imagine some sender that would like to send some information privately and reliably to some legitimate receiver Y, but would like to do so without some eavesdropper Z intercepting their communication and inferring something about the sent message. Now, an achievable rate for such a coding scheme is given by the private information. The private information here is defined by taking the difference between the mutual information between some auxiliary system U and the output to the legitimate receiver, and the mutual information between some auxiliary system U and the output to the eavesdropper. Then we simply maximize this difference of mutual informations over all input distributions that are joint with the auxiliary random variable U. Now, the reason for allowing for this auxiliary random variable is because one can show that if one were to only allow for the input variable X and maximize over its distribution, then this would only form a lower bound to the private information itself. In our work, we refer to this more simpler expression as the naive rate. Now, in 1978, Chisar and Kerner then showed that the private information for the classical wiretap channel is in fact additive, and therefore the regularized private information collapses down to just being the single letter quantity, and the private capacity is therefore characterized by it. Now, if we switch to the completely quantum wiretap model, then the private information is very much analogously defined, except the difference being that now we're evaluating the mutual information on some classical quantum state, omega, where omega is this time tripartite, and where V is now the classical auxiliary random variable that is classically correlated to the input quantum system to the channel. In contrast to the private information for the completely classical wiretap channel, however, the private information for the quantum wiretap channel is in fact non-additive, and therefore, once again, like for the Holevo information, the private capacity is given by some multi-letter regularized expression of the private information. Again, this is an intractable optimization problem, and this was shown in work by Kai et al. In 2004, and also independently by Devitak in 2005. All right, so we've seen this very stark difference between the purely classical and the purely quantum setting. But what happens if we interpolate between these two settings and choose a hybrid setting where we minimize the amount of quantumness and we ask that two of the parties are restricted to be classical and only one party has access to quantum states? What happens then to the private information? Does it become additive, or does it stay non-additive like in the fully quantum case? The results that we found were that if we allow for only the sender to have access to quantum states, then the private information in fact becomes additive. So we have a channel that has a quantum input and classical outputs, and for this case, the private information does become additive. However, when either of the outputs is allowed to be quantum, then the private information stays non-additive. Now, this is surprising because here the input is purely classical and there's no entanglement at the encoder, but still the phenomenon of non-additivity occurs. So how do we show this? All right, so in the case of the quantum sender, we simply needed to show that the private information of some joint channel W1 tensor with W2 is in fact equal to just the private information of each of the channels itself. Therefore, we needed to show these two inequalities. We need to show both directions. And the first one is really just immediate. It's completely trivial because the right-hand side requires you to do an optimization over a much larger set of states than is allowed on the left-hand side. Therefore, the left-hand side is simply trivially achievable by the right-hand side, and the inequality holds. Now, the real meat lies with the second inequality, where we had to adapt the classical proof of additivity that was given in the reference Chisar and Kerner from 1978. And the reason why we're able to adapt this classical proof to the quantum setting is because there's no conditioning on any of the input quantum systems in that proof. This would have posed a problem because conditioning on quantum systems is slightly problematic. And in our case, for the quantum sender, the input is quantum. Now, since that wasn't the case, it was possible for us to adapt the proof. And together with other tools from classical information theory, such as the Chisar sum identity, we were able to prove the second equality. This is just a rough proof sketch, of course. Now, in addition, in order to show that the optimization problem that the private information sets out to solve, we also showed that there is, in fact, a cardinality bound on the auxiliary random variable V, which makes it possible to solve the optimization problem, or at least it shows that it is not an obstacle to optimizing it. All right, so the case for the quantum receiver, we needed to show non-additivity, and we showed this using an explicit example channel. So the example channel that we considered is to be understood as follows. The full wiretap channel is given by the dashed box, and it should be understood into three separate parts. So at first, the sender inputs a quantum state and then duplicates that quantum state and sends one copy over a so-called binary pure state channel parameterized by channel parameter R to the quantum receiver. Now, the binary pure state channel R here is simply a quantum channel that outputs two pure quantum states with pure state fidelity R. And then she sends the other copy over the binary erasure channel parameterized by some function of the parameter r to the eavesdropper. All right, so the non-additivity of the private information here is illustrated by the following plots. The solid line represents the private information for one copy of the channel, and one can see that it vanishes for some critical threshold channel parameter that lies somewhere around 0.542, while for the case of channel coding with two copies of the channel, we employed a block coding scheme using parity preprocessing as shown below. And we were able to show that it vanishes for a channel parameter somewhere around 0.544, a little bit bigger than that. But what this tells us is that there is a critical parameter regime for which the private information of one channel vanishes, but there still is a non-zero achievable rate that we can achieve by using only two copies of the channel within that very same regime, thereby showing us non-additivity of the private information. Now, we would also like to rigorously show that, in fact, the private information does vanish within this regime. And we did so leveraging ideas from classical information theory. In particular, we used a result by Ulukos and Uzel from 2011, in which they rewrote the private information in terms of a function f that is both a function of the channel as well as the input distribution, where if you were to maximize this function, it would give you what we can refer to previously as the naive rate, which is simply a lower bound to the private information itself. Now, rewriting the private information via this function f in this form helps you in the following way. If f were to be a convex function, then using Jensen's inequality, you would know that the second term here will upper bound the first term. Therefore, the entire term is upper bounded by 0. And since we're setting this out to be a maximization problem, and since 0 is always an achievable rate, this means that if f is a convex function, then the private information itself is, in fact, 0. Now, what we did then is that we, in fact, showed that for our particular example channel, the function f becomes convex in the parameter regime for which we desired the private information to, in fact, vanish. We did this by simply evaluating the second derivative of the function and showing that it becomes positive. So after having shown that for the quantum sender, the private information, in fact, does become non-additive, we employed the same proof strategy for the case of the quantum eavesdropper. In this particular case, we simply needed to switch the example channel that we used, and we also need to change the coding scheme. Again, we illustrate this here with the following plot, where the solid line represents the private information of a single use of the channel, which vanishes for a critical threshold parameter somewhere slightly larger than 0.124, and where the dashed line represents an achievable rate that is achieved using a block coding scheme that uses both the repetition code and some noisy preprocessing via a bit flip channel, and which was taken from work by both Joe, my co-author, and Graham Smith and John Smolin from 2006. Essentially, our coding scheme is morally equivalent to their quantum key distribution protocol, for which they tried to show that a certain single letter expression did not fully capture the achievable key rates. So the proof strategy, again, here remains the same. We used the second derivative check to prove that the private information does, in fact, vanish here for this parameter regime. And we showed via this coding scheme numerically, but also analytically, that the achievable rate in this regime is, in fact, non-zero, and that therefore non-additivity holds. All right, to wrap up this talk and to conclude, we've used non-additivity. We have shown non-additivity examples for the private information. But we've done so using explicit example channels in contrast to the randomized constructions that Hastings provided back then for the whole of information. In addition, we showed that entanglement is, at least in the wiretap setting, neither necessary nor sufficient for non-additivity to occur. And a direct corollary, actually, from our work is the fact that if you want to relax the restriction on the number of classical parties, such that 2 parties are allowed to be quantum, then we already know that this will become non-additive. And this is the case because if two of the parties are allowed to be quantum, then at least one of the outputs has to be quantum too, and that case is covered by us. So lastly, one can ask, and this is an open question, how large such additivity violations can become for the private information. And this is, of course, open to future work. Okay, so thanks very much, and I'm happy to now take any questions.
Thank you, Akin. It's very clear talk. I don't see any question from the audience. Is there anyone who want to just mute yourself and ask? I think you have done a wonderful job. It's very clear.
Thanks very much.
Okay, so I was told that you won't be able to unmute yourself, but you can just raise your hand if you want to ask questions. Oh, I think Masahito want to ask questions. Oh, okay. So Masahito has a question.
Mm-hmm.
So
the Q&A doesn't open for me for some reason.
Let me see if I can unmute him. Okay. Okay. I think you can talk now, Masahito. We cannot hear you. Can I think you are unmuted, but we cannot hear you.
Should we just use the chat maybe?
Yes, or if you want to type up your questions. So Masahito's question is that, can you give the detailed definition of the quantum sender Alice? So I think that.
Does he mean
so
whether?
I think you have 3 different cases, right? And for the non-additivity one, you would have like the quantum sender, if I remember correctly.
Yes. So if I understand the question correctly, does he want me to define the model for the wiretap channel in the quantum sender case, or?
No, I think he probably wants you to clarify what the input to the quantum channel is.
Oh, so well, the input is simply the classical quantum case that, yeah, it's pretty much any mixed state, but again, we're using this particular classical quantum state, right, of this form. So if you can see my pointer here, so the input will be any mixed state, but this mixed state will be classically correlated to this auxiliary random variable that is classical. So that is the input to your wiretap channel. Now, when we have classical inputs, then all that happens is that these mixed states here are restricted to be diagonal in some prefix spaces. So that's the only restriction when you go from the quantum sender to the classical sender.
Okay. I see. There is a question by Julio, who asks, could you explain again your conclusion about entanglement is not necessary for the non-negativity phenomena?
Right. So essentially, what we mean here is that the basic consensus within the community is that essentially the fact that non-additivity occurs in quantum Shannon theory is due to entanglement. And this is, in fact, true when it comes to the Holevo information, where in order to achieve any sort of rate that is bigger than just the Holevo information itself, you do require entangled inputs. Now, what we show here is that this might be true for the Holevo information, but it's not true for the private information. Here, if you can get non-additivity without using any entanglement at all. So that's what's meant by that. I hope that answers the question.
Yes. Okay. Okay, we have two more questions. The first one is by Dina. If entanglement is not the reason that this non-additivity occurs, so what makes the quantum case different compared to the classical one?
Right. Yeah, that's a very good question, and I'd say that the answer to that should be as follows. Namely, so the phenomenon of non-additivity is not entirely confined to quantum Shannon theory. It simply does not appear in those very basic point-to-point settings in the classical Shannon theory, but it does very much appear in network information theory, so in the completely classical version. So in that sense, and this goes back to the last question, non-additivity in general is nothing that's actually dependent on entanglement whatsoever, and also appears in completely classical scenarios. However, they need to be somewhat more complicated, involving many more receivers and other other technicalities. And so in that sense, it's definitely, it does not have to be, while we don't know what it is, I wouldn't say that it definitely has to be, it does not have to be a quantum phenomenon of any kind in order for non-additivity to occur. But the origin of non-additivity is, of course, is a good question to investigate.
Okay, let's have one last question. But if you have further questions, you can post your question here, and I think the speakers could get back to you offline. Okay, so the last question of the section is by Hayata. He is interested about how you perform the numerical simulation to demonstrate the gaps between one use of channel and 2 or 3 use of the channel to show the non-additivities.
Oh, right. So so the first thing, so the private information there that you saw, that's just basically doing the brute force optimization, because it's just for one copy of the channel. Then for the n equal to 3 case, that again is really just the same thing, but you don't actually even have to do that. You can already just look at the naive rate and compute a, which is a lower bound for that. And that optimization is even easier because you're not even optimizing over this auxiliary system anymore. You're just looking at the inputs. So it's basically because they're very small instances.
Okay, I see. Okay, so thank you very much. Let's thank the two speakers of the sections. And we are going to have bring yourself a coffee before the next session starts. Thank you very much. Thank you, everyone. All.
Thank you.
Bye-bye.
Test. 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 Test.
Check.
The next session of TQC is just about to start in about 1 minute, so we'll get started soon. Thanks. Okay, so good morning, everybody. Welcome to the next session of TQC 2020. I'm Ashley Montanaro. I'm going to be chairing this session. This session has three talks in it. And the first talk is going to be by Alexander Belov. And he's going to be telling us about a tight quantum lower bound for approximate counting with quantum states. So Alexander, please, whenever you're ready, can you get started? I think.
Okay, thank you, Ashley.
Oh, and actually, before you do start, maybe I should say to everyone that at the end, for questions, you can ask questions either on Slack or via the Q&A feature on Zoom. So I'll try to be monitoring those and pass the questions on to Alexander. Thank you.
Okay, good day, everyone. Okay, I hope you can hear me. So this is a presentation tied quantum lower bounds for approximate counting with quantum states. So it's a joint work with Ansis Rosmanis from University of Nagoya. So first, let me briefly sketch the history of the problem. So it's a counting problem. It's a very old and well-known problem. So given a subset X, so we can think of X both as a subset of the set M and as a characteristical bit string, so of n bits. And so I'll be using a small letter X to denote the subset N. So it's common to denote an input to a quantum algorithm by a small letter, so I'll be using it as a small letter. And the problem is to detect, to find what is the size of the set X, or if you think it's a string, the Hamming weight of X with multiplicative precision epsilon. Okay, so it's a problem, so one of the first problems solved by quantum computing. And so this can be done in order of 1 over epsilon times the square root of n divided by the size of X queries. And so this was shown by Bassart, Hoyer, and Tapp in 1998. And so this is essentially tight. So let me give like two caveats. First, because I'm interested in lower bounds, I am interested in distinguishing two cases. So this is a simple problem, and I will prove lower bound. We will prove lower bound for this simple problem. So I want to distinguish two cases when the size of X is k, or the size of X is exactly 1 plus epsilon over k. So if this problem is hard, then finding the size of X is even harder. And the second thing that this result is done assuming the standard Oracle access to X or the membership Oracle access, so which is the same thing. So given an element I, you can say whether I belongs to X in one query, and of course it's a quantum algorithm, so we can do this kind of queries in superposition. Yeah, so this is a very old problem, but recently it was given new life. And the question is, what if we allow other input oracles? Because last year this question was raised by Aronson, and then together with Koshari, Krenschmer, and Tower. I think I am not sure what the motivation was, but essentially what I can guess that standard oracle is good, but let's do something more quantum. Okay, and what can be more quantum than this thing? So uniform superposition over the elements of the set X. So you are not only given the membership or access to X, you are also given these uniform superpositions. Okay, and what does it mean to have these uniform superpositions? So in the case of this paper, they assume two cases. So you can either have copies of this state, or you can have an input oracle that reflects about the state. And the theorem proved, so assume that epsilon is equal to 1. So the task is to distinguish whether the size of X is k or 2k. And then the algorithm either has to invoke the membership oracle, so the standard oracle, square root of n over k times, or access the state in this way, using at least that many access, so cube root of k, or the square root of n divided by k, whichever is smaller. Okay, so let us move to our result. So first, our settings. So previously, they were considered two possibilities, so accessing the copies and accessing the reflection oracle. Okay, so we add the state generating oracle. So that's the oracle that just starts in some state 0 and can produce the state psi effects. You can also run it in reverse, so you can uncompute psi effects if you want. And so this is more powerful because with this kind of oracle, you can get state just executing it twice, or you can also reflect about the state just executing it twice. Okay, first we consider just considering this type of oracle, but then we realize that we can actually have all type of resources. So we'll have four type of resources: membership oracle, copies, reflection oracle, and the state generating oracle. And the second thing, previously it was assumed that epsilon is equal to 1. So we consider all values of epsilon between 1 over k and 1. So epsilon is actually a multiple, positive multiple of 1 over k, so it cannot be smaller than 1 over k. And in fact, you can go beyond 1, but we just didn't want to make our life too complicated, and so we just considered this lower range of epsilons. Okay, so what we get. So for the reasons, so this is the main theorem. So the reasons that will be clear afterwards, let me denote by L the number of copies of the state that the algorithm have, and L prime the number of executions of the state generating oracle that the algorithm will do. Then in order to solve this problem, so this approximate counting problem, the algorithm should, and there are multiple options. First, either have that many copies of the state psi fix, and then so there are three options, okay, whichever is smaller, that the algorithm can do. Okay, then execute the state generating oracle that many times. And note, so there is an also trade-off between the number of copies of the state L and the number of execution of the state generating oracle. So if you have more copies of the state, you can execute the state generator oracle fewer times. So this is given by this L vector here. Okay, if you don't like the state generating oracle, you can execute the reflecting oracle that many times. And again, there is a trade-off between this time the copies, the number of the copies of the state, and the number of executions of the state generating oracle combined. Okay, and finally, you can execute the membership oracle that many times, and that coincides with Bassett and O algorithm. Okay, so there are four options, and there is actually one more option that you can do. So that's the second slide, is the same theorem. So you can have at least one copy of the state, or you can execute the state generated oracle at least once, or you can execute the membership oracle square root of n divided by k times, or you can execute the reflecting oracle the same number of times, and together with that, one of these four options, you can execute the reflecting oracle square root of k divided by epsilon times. And so the theorem says that these are all the options that you can have. Yes, this is quite a long list, but it's a long list for a reason, because this result is tight. And so there are four different input resources, and because of that, you can have a lot of flexibility. And in the paper, we list 7 different algorithms showing that you cannot improve actually anything in this theorem. So this is tight. Okay, just let me just briefly explain 2 of these algorithms. So the first one is from the first slide of the formulation of the theorem. So that you need that many copies of the state psi x. And so note this red k over here. So this cannot be improved. And the reason is being that you can run the whole set x just using k or k classical samples from x. Of course, if you have a quantum sample from x, you can measure it and you get a classical sample from x. And coupon corrector problem says that you require k or k. It's enough to have k or k samples to reconstruct the whole set x. And if you have the whole set x, of course, you can now know its size. Okay, so this is the only place, so I cheated a bit. This is the only place where we are tied only up to a log factor. Okay, everything else is tied up to a constant factor. And also see Ronald's talk right in this section. It will be the third talk. Ronald will talk about quantum coupon correcting problem that's closely related exactly to this algorithm. Okay, and the second matching upper bound is from the second slide. You can execute the membership oracle square root of n divided by k times, and you can execute the reflecting oracle that many times, and then you can solve the problem. Okay, and okay, so roughly how the algorithm works. So without going into any calculation, so use the membership oracle to find one element of X. Then use the refactoring oracle and amplitude amplification to find second element of X, third element of X, and in such way you find 1 over epsilon elements of X. Then use amplitude estimation on these 1 over epsilon elements using the refactoring oracle. And in this case, if you perform square root of k divided by epsilon queries, you can distinguish the cases when the size of k, the size of X is k, or the size of X is 1 plus epsilon over k. Okay, that's all about the formulation of the theorem. So let's talk about the techniques. Okay, so first, so this paper by Aronson et al. That I mentioned previously in the history section uses a new technique that they developed called Laurent polynomials. And with the help of Laurent polynomials, so it's a generalization of a well-known polynomial method. So if you remember, for polynomial method, we have a degree of a polynomial, and degree of a polynomial is a lower bound on the number of queries that the algorithm has to make. And in Laurent polynomials, you have both positive and negative degree of a polynomial. So it allows terms with negative degree. And so the positive degree still is a lower bound on the number of membership queries, and the negative degree is essentially a lower bound on this number of copies or refractions about the state. And so this is just one quantity, and it's impossible to separate copies and refractions. From the point of this technique, they have the same weight, so they cannot be separated. So we use adversary bound, and that's a very different technique. So let me first overview the standard spectral formulation of the negative weighted adversary bound. So this is a very high level technical overview. So this is due to Hoyer et al. From 2007. So this quantity here, this fraction, is a lower bound up to a constant factor on the number of queries to the standard oracle to solve the problem. So let me just go through my legend. So gamma here and here is a real X times Y matrix. So where X and Y are sets of positive and negative inputs respectively. So X is a set of, so the capital X is a small of all small x's of size k, and capital Y is a set of all small y's of size 1 plus epsilon times k. So the size k, the size 1 plus epsilon times k. So the two things we have to distinguish. So the gamma, this delta J is also X times Y matrix. And so this is 0, 1 matrix. So for each J, where J is an input variable, you have this indicator variable that says whether X and Y, so it's an element at the intersection of X rows and Y's column. It says it's 1 if X and Y differ in the J's variable, otherwise it's 0. Okay, and this notation here is an Adamar product, so this is just entry-wise product of the matrices, and this thing is a spectral now. So if you can find a matrix gamma such that this thing is large and this thing is small, you have a good lower bound on your query complexity, assuming the standard input oracle. Okay, and so let me modify it a bit, just to go to make the transition to the next things easier. We can do some kind of accounting here. So let me introduce this delta membership. Mem stands for membership. So it's a collection of n times n matrices, and which each n times n matrix is a diagonal matrices with 0 and 1s on the row. So this is the same thing. So this thing was actually in delta 2 previously, and this thing was in delta 1. Okay, and I extend the Adamar product notation, this gamma, so it's X times Y matrix. I'm multiplying by this family of n times n matrices. Okay, I'm getting a block matrix where each entry, XY entry, is a n times n block matrix obtained by multiplying this matrix by the corresponding elements of gamma. Okay, and if you look carefully, so this is a direct product of matrices. So the Adamar product, this extended Adamar product of these matrices, is actually the direct sum of gamma times delta J from the previous slide. And so this is a Borg diagonal matrix, and the norm of the Borg diagonal matrix is equal to the maximal norm of the Borgs. So this norm is equal to the maximum J over J of norm of gamma times delta J. Okay, so this means that I can rewrite the spectral formulation of the negative weighted adversary bound as this fraction of the norm of gamma divided by this norm of this extended Hadamard product. Okay, and this is a tight lower bound. And so we say that this correction delta membership represents the standard or the membership input oracle. So because this thing holds, so this is a lower bound in this problem. Okay, and now it turns out that you can generalize this, and instead of membership input oracles, you can consider general input oracles. And the general input oracles is actually arbitrary unitary, O of X. And so not just performing some specified operation like in the membership oracle, but it can, for each input X, you can assign your own unitary, that can be anything. And this still gets the same type of lower bound, and this is still tight. And the difference is that this correction delta, it's replaced by this thing, just the difference of two unitaries. Okay, and this is a tight lower bound, assuming this, you have access to this arbitrary unitary, so your black box increments this unitary, and you can also run it in reverse. Okay, you don't know what X is, but you can, as a query, you can execute this unitary and you get this lower bound. So in the context of our problem, we can use it for the oracle reflecting about psi x. So this refraction is just a unitary operation, so it looks like this: 2 psi x by x star minus I. Just refract two things, you get this thing: 2 psi x, 2 times essential projection on psi x minus projection on psi I. Okay, then let me move on the state generating input oracle. So it implements the map from 0 to psi x. And so it's represented by, okay, this thing. So direct sum of psi x and psi x star. So this is n plus 1 times n plus 1 matrix in our case. And this is again the same thing, can be characterized by the same quantity. So this represents the same, this type of oracle. Okay, and finally, I have to explain how we can deal with multiple input oracles, because we are allowing actually 3 different input oracles. And so again, this is the formulation of the spectral adversary. Okay, and assume, if I renormalize and assume that the norm of gamma is 1, then it says that the algorithm needs omega of 1 divided by the norm of gamma times delta queries to solve the problem. And what happens if you assume you have 2 different input oracles that you can execute, delta 1 and delta 2, so they are, which are represented by delta 1 and delta 2. So it turns out that natural things happen. So you still renormalize gamma to have norm 1, and then the algorithm has to make either this number queries to the first oracle, or that number queries to the second oracle to solve the problem. Okay, so pretty intuitive, and it turns out that this is the case. And this also holds for any constant number of input oracles. Okay, so now we can write the formulation of our optimization problem. So gamma is an x times y matrix with the norm of gamma equal to 1. And we want to find this such that if we find a good matrix, then we have 3 different quantities. Just evaluate the norm of the extended Hadamard product. And you get the lower bound on the number of membership queries, the number of refracting queries, and the number of state generating queries. And you can take one of them to solve the problem. Okay, but there is one thing that we forgot, is the copies of the state, because the copy of the state is not an oracle, so it cannot be characterized by this, but luckily we can state it as a state conversion problem, which is due to Ambanis, Madnim, Rotower, and Rotorand. And to solve this, I have to define the, okay, I'll go very quickly. I have to define the Graham matrix of this correction of vectors. So if we have L copies of the state, then this Graham matrix is just this matrix Hadamard producted with the self L times. Okay, and the change I have to make in the formulation of the problem is that I have also to assume that the norm of the product of gamma with this psi to the L is omega of 1. And then if I have L copies of the state psi x, I still have the same number of queries I have to make to one of these oracles to solve the problem. Okay, so that's pretty much it about the techniques. So very briefly about the representation theory. So we essentially solve this optimization problem using the representation theory. Okay, so the matrix gamma is symmetric with respect to the permutations of the elements of the set. So we can apply the representation theory of the symmetric group. You can see that the general form of gamma is represented as a linear combination of the morphisms between the different IREPs of the symmetric group. Okay, and essentially, instead of constructing the whole matrix from scratch, it suffices to just give k plus 1 parameters, these small gamma j's, and the norm of gamma is just the maximum of this absolute values of gamma j's. And you can just do all the math, so it takes some time, but you can do this. And essentially, you just have some quantities. These are just copied from the paper. It doesn't fit on the slide, but doesn't matter that much. Okay, then you have 4 different vectors that are obtained from these quantities on the previous slide, and also gammas that are coefficients from the gamma matrix. And you can rewrite the thing that on the previous slide, this is the norms of the tensor product or additional product of gamma with this delta matrices, just in terms of these 4-dimensional vectors. So essentially, these are just norms of 4-dimensional vectors, and this is maximum over norms of 4x4 matrices. And it looks a bit scary, but actually it's not. You can do all the stuff. And also you have the membership oracle. You can also have the estimate on the norm. If it doesn't use the same vector psi x, so it has slightly different thing, not in the terms of these vectors. Okay, but you can, but it's kind of manageable. You can do everything. Again, the final construction, this gamma j are essentially in this form. So t is some parameter, and essentially it starts from gamma 0 is 1, and then it goes linearly to 0, and then it's 0 at some point. And putting different values of t to actually match all possible upper bounds, and you prove the lower bounds. Okay, so I'm finishing with a summary of the work. So first, it's a first real-world application of the adversary bound in this for this general case with various input oracles. And also the first time actually it was realized, to our knowledge, that you can prove trade-offs in this way between different oracles. Okay, and the second contribution, which I didn't touch, I touched very briefly at the very end, that it was developed and seen this in theory matter to deal with subsets of a uniform set. So if you have a problem where you have subsets of a uniform set and you have oracle that in some way deals with superposition of them, then you can actually reuse the same machinery to prove different problems. Okay, the things we find interesting, first, of course, generalize it in whichever way possible. Okay, most interesting to us is try to tie this lower bound with the error probability. So everything about this was assuming that we have bounded error, but what happens if we want to deal even with small error probabilities like in cryptography? And more specifically, the problem may be to aim to, just to get the techniques right, is the k-fold search. So it's the same problem, but you don't want to estimate the size of x, you want to run the whole x. And of course, interestingly, you want to show that it's hard even if the success probability is really, really small. And so again, watch Ronald talks later in this section. It will try to brief about this. So yeah, thanks.
Alexander, for that very nice talk. So we have a couple of minutes for questions. So you can either ask questions in the Slack channel or using the Zoom Q&A feature. In case anyone's typing, maybe I'll just ask a quick question first to get things started. So in some of your previous work, you had these nice results where you go from a solution to the adversary bound to an explicit algorithm somehow. So, well, this is semi-explicit algorithm, perhaps what one could say, based on taking the adversary matrix and doing some reflections about it and things like this. Does this approach also work for these generalized oracles?
Well, yes, you can still make algorithms. Okay, it doesn't apply here because it's a lower bound. So I cannot get an algorithm of the lower bound. But yes, actually there was a paper of mine last year, where I got an algorithm for the state generating problem. You have a problem with a state generating input oracle, and it was for distinguishing what the input probability distribution is. So this can be done.
Okay, cool, thank you. And there's a related question by Changpeng Xiao, which is, do you have an explicit quantum algorithm for this problem?
For the counting problem, yeah, as I said, we have 7 different algorithms in the paper.
And they're all
okay, but they are not really complicated.
They're not complicated. Okay, so they use sort of standard routines, and you can.
Yeah, standard routine. Yes.
Yeah. Okay. Excellent. Okay. I guess we should probably move along in the interests of time, unless there are any sort of urgent questions anyone would like to ask now. But if not, you can ask further questions on Slack later on to Alexander. But okay, let's move on to the next talk. So the next talk is titled Quantum Algorithms for Computational Geometry Problems, and it's going to be given by Nikita Larka. Nikita, I guess I will just hand over to you to get started. Thank you.
Can you hear me?
Yeah.
Okay. Okay. Hello everyone. My name is Nikita Larka, and I will give a talk on quantum algorithms for computational geometry problems. This is a joint work with Professor Andres Ambainis. So, as you probably already know, quantum algorithms outperform classical algorithms on many computational problems. And here you can see some of the examples, perhaps the most famous ones. Our goal for this, for our paper, was to extend this list with geometrical problems. So how did we start? We want to find a geometrical problem P that is hard for classical computation, meaning that classical algorithms cannot improve over some f from n complexity. And we want to find a quantum algorithm that beats this complexity. So the first question is, what's the geometrical problem P? Okay, now we'll consider a simple and quite famous problem, face-sum problem. In this problem, we're given a set of n integers, and we need to decide whether there are 3 integers which add up to a 0. This simple problem has also a simple quadratic algorithm. You just iterate through each pair of integers in the set, deduce the third one, and you have to verify whether this integer is in the set. Of course, it's roughly quadratic complexity. More interestingly is that advanced algorithms improve this complexity only by a logarithmic factor. And what's more, there is a conjecture that the algorithm with complexity n to the power of some constant which is less than 2 doesn't even exist. So this all means that improving quadratic complexity for face-sum problem in classical case is really hard, or maybe even impossible. Well, it also turns out that free-sum has deep connections with geometrical problems. To see that, let's consider 3 points on a line problem. In this problem, we're given a set of points in the plane, and we need to decide whether there are three points that lie on one line. Now, this problem is at least as hard as free-sum problem, meaning this problem cannot be solved in time and subquadratic time. It can be solved in subquadratic time if and only Well, basically, it means that if we solve 3 points on 3 line in subquadratic time, then we have a solution for a face-sum problem in subquadratic time. So this means that 3 points, improving quadratic complexity for 3 points on a line problem is also hard for classical algorithms. And there is a rather simple reduction to show that. You just map an integer from a set to a point with coordinates x and x cubed. And then it's quite easy to verify that the 3 integers add up to a 0 if and only if their corresponding points are collinear. Actually, in 1995, Gajentan and Overmars presented many geometrical problems which are at least as hard as 3-sum problem, and they call this class a 3-sum hard class. So now we can return back to our initial question: what's the problem P? This all means that those 3-sum hard geometrical problems are hard for classical algorithms, meaning that it's hard to improve over quadratic complexity. And we can now try to improve this complexity using quantum effects. Now, what's known for this type of problem? There is a rather simple quantum algorithm for a 3-sum problem, which achieves complexity n log n. But there was no known quantum algorithms for 3-sum hard geometrical problems, and those are the problems we focus on in our work. Now, what quantum tools do we use in our paper? Actually, we restrict ourselves only with a quite simple and famous quantum procedure called a Grover search. It means that we assume that we can find an element with some property in an n-element database using only square root of n quantum queries. Now, when we know the tools, we know the problems, how do we tackle them? From now on, let's consider point on 3 lines problem. In this problem, we're given a set of lines in a plane, and we need to decide whether there are 3 lines that intersect at one point. Of course, that's also a 3-sum hard geometrical problem, and it's hard for a classical algorithm to improve quadratic complexity. But there is already a straightforward quantum algorithm that improves this complexity. You just have to search through all the triplets of lines, and we'll verify whether they intersect at one point or not. The search space is of course cubic. The Grover search gives a quadratic speedup, and the resulting quantum algorithm has the complexity n to the power of 3/2. But as you see, this algorithm doesn't use any geometrical ideas, geometrical insights. So we hope that we can improve even further. Our main result is the algorithm with complexity, a quantum algorithm with complexity n to the power 1 plus small o from 1. And now I will try to describe this algorithm. So, well, okay, we are imagining we have a set of n lines in the plane, but first we'll start with some observations. We have a set of n lines in the plane, and suppose we randomly choose k lines from this set. So these are the blue lines. Suppose these are the blue lines, and those lines separate the plane into regions. We also triangulate each region. Now the plane is separated into regions where each region is bounded by at most 3 lines. Suppose any other line, say this red dotted line. You may note that this line cannot cross all of the regions. It crosses only some of the regions. And well, it's intuitively clear simply because it's a line. Now, what are the numbers behind that? So if we randomly choose k lines from a given set, we'll get around k squared regions. If we take any other line, this line would cross linearly many regions, linearly many from k. But we're actually interested in the following value. So suppose, so take one region, and we count how many lines pass through this region. Well, it's not that straightforward to estimate this number, because it of course depends on the region. It depends on which k lines we have chosen. But yeah, we know that on average this value is n divided by k. That's quite straightforward. But how far this n divided by, yes, but the goal is to bound this value from the above. And to do that, we came up with the following theorem. So what this theorem states is that the probability that the number of lines that pass through one concrete region is greater than n divided by k times logarithm from n, or maybe times some constant, is actually negligible. And so we can assume, we're assuming here that each region contains around no more than n divided by k times logarithms from n lines, multiplied by some constant. To see why this is true, consider endpoints on a line, and suppose we have chosen k points from those endpoints, and now we ask ourselves a question: what is the probability that none of the first c times n divided by k points is chosen? Now it's quite easy to see that this probability decreases exponentially as c increases. And of course, this happens not. This is true not only for the first c times n divided by k points, but for any continuous interval of points of size c times n divided by k. Now, if we take one region, we see that it is bounded by 3 lines. If you take one of these lines, then you get a n-1 intersection point with all of the different lines in the set. And basically, what this experiment with points says that the interval, well, again, yeah, this intersection point correspond to lines, and yeah, if you take this, if you extend a region segment to a line, the probability that this segment would contain c times n divided by k more than c times n divided by k points is negligible. And in order to have probability negligible for each region, we need to have c proportional to a logarithm from n. So basically, that outlines the proof of this theorem. Okay, now when we know these facts, we can describe our algorithm. So the algorithm would look as follows: we randomly choose k lines. We separate the region. We separate the plane into regions. The number of regions is k squared, and each region is crossed by n log n divided by k lines, no more than its value. So now what we do, we try to guess where the intersection of three lines will happen. At what region this intersection would happen. We have k-square possibilities, and if we guessed correctly, the problem reduces to the same, but with less lines, because we don't need to consider all of the lines. We will consider only the lines which pass through this region. So, and we recursively apply this algorithm further. Like that's actually it. The time complexity would be n times k to build this separation, to identify which lines pass through each region. Then you have k-square possibilities, and each possibility is it's just the same problem with less lines. Yes, so this algorithm is a bit unnatural. Of course, there is a quite natural algorithm for point on three lines which runs in quadratic time, but what is bonus here? The bonus is this algorithm is easily quantifiable. You can quantify this algorithm quite easily, but you cannot do it with a naive algorithm for point on three lines. And yes, you may know that up until now we haven't used any quantum effects. So how can you quantify this algorithm? You may note that we're actually guessing, or we are iterating through for each region, and we're trying to guess where this intersection of three lines would happen. And that's exactly the place where we can use Grover search, and we can quadratically speed it up this search. So in quantum case, it would be square root of k squared. And now what's left is you have to decide what's an optimal k. When you do that, you have an algorithm with complexity n to the power of 1 plus small o from 1. So that's about it. Now it turns out that this idea of separating the plane with a random k lines, it can be used for many free-sum high geometrical problems, and I'll show you that on this a bit quite maybe complex example than 3 points on the line is the example of the problem triangles cover a triangle problem. In this problem, we're given a perhaps big blue triangle, and we're given a collection of red triangles. Our goal is to decide whether those red triangles fully cover this blue triangle. How can we do that? Well, each red triangle is we extend each triangle side to a line, and we get 3n lines. We randomly choose k from the k lines and split the whole plane as in the previous problem. Now, what do we need to do? For each region which is inside this blue triangle, we need to decide whether this region is fully covered by the red triangles. Now, of course, this we have split our problem into many smaller ones, and we need to yes, so we split to many smaller ones, and similarly to the previous analysis, we see that we don't need, when we solve the smaller one, we don't need to consider all of the red triangles. We only need to consider the triangles that cross this region inside the blue triangle, and the number of such triangles of red triangles would be bounded by n log n divided by k, and so the algorithm has the same kind of time analysis, and the algorithm results in a n to the power of 1 plus small o from 1 complexity. So to sum up, we have achieved the quantum algorithm with complexity n to the power of 1 plus small o from 1 for the following geometrical problems. All of these problems are free from hard, and all of those problems are from Megajin-Tan and Overmars work. So I guess that's it.
Great, thank you very much, Nikita, for that very nice talk. So now, as before, we have some time for questions. We have a few minutes for those. So you can ask those either on Slack or in the Zoom Q&A. So in fact, we've already had a question, which I guess I'll start with, from Konstantinos Mekanetsidis, which I don't know if you can already see, but I'll just repeat it for you. So he's asking, how do you decide if a point belongs on a line or not? Or in intersection between two lines, perhaps? Do you need to have some kind of small distance around the line that you just determine whether a point's close to the line or not?
Close on the line or not? Does it? It was meant as a we can do it as a oracle, I guess. So
okay, so you just assume access to this as
yeah. So if there are integers, I guess we can do it like without any estimates. So basically, you have an equation of a line. So yeah, if everything is an integer, I guess there is no problem in that. So we assume we were not considering some problems with floating points or something like that.
Okay, cool, thank you. Okay, so we have some more questions. So one, which I think is from Adam Gloss, is have you considered the time required to transforming the data and transforming the problems? So towards the end, there's, I guess you have various other problems which are related to the problem you consider. Like, what's the time complexity of these transformations?
Transforming the data and the problems. Okay. Actually, I haven't considered that. I guess I'll have to talk with my colleague. So I'm sorry. Maybe I can answer it on Slack. I'll just have to think about this.
Excellent. Yeah, I mean, so Slack is a great opportunity for following up these things. So that's great. Okay. And another question from Danish Dar, which is, what's the space complexity of your algorithm? And also, did you consider rectangles in your algorithm? They have 4 intersections.
Yeah. So space complexity is polynomial, definitely, and I guess it's also the same. Well, it's bounded by n squared, I guess. It's definitely polynomial. And if there are rectangles, it doesn't change anything actually, because one of the way to handle this case is just to split the rectangle into 2 triangles. Everything would work.
Okay, excellent. Right, so I can't see any more questions. I can just see applause in the Slack channel. So unless there are any more urgent questions, then just in the interests of moving on with the schedule, maybe we should leave it there and proceed to the next talk. So yep, thanks very much, Nikita, again for a very nice talk.
Have a nice TQC. Bye.
Thank you. And the next speaker is going to be Ronald de Wolf. And he is going to tell us about quantum coupon collector problem. So, okay, Ronald, I can see you're there. So whenever you're ready, please feel free to take it away. Thank you.
Can you see my slides now?
Yep, can see your slides.
So I don't see them on Zoom itself.
So we can see your slides, but it's not zoomed in, so it's not full screen.
Oh, I see. That's the issue. Okay. How about now?
Now it's full screen. Yeah.
Okay, good. Shall I just start?
Whenever you're ready.
Okay, so yeah, nice to be here. I'm happy that things in academia are still progressing thanks to all these tools, these online tools. So this is my talk about quantum coupon collector problem, and this is joint work with Srinivasan Arunachalam, Alexander Belov, Andrew Childs, Robin Kothari, and Ansis Rosmanis. And the problem I want to start with is a very basic problem in classical probability theory, which I'll motivate by a real-life example from Dutch retail. So suppose you suppose you want to collect something from some supermarket thing. So Albert Heijn is the main chain of supermarkets in the Netherlands, and every year they have some sort of commercial activity where they hand out soccer cards. Of course, the goal here is to to get the parents to buy a lot of groceries because their children are begging for more of these soccer cards. So for every 2.5 euros that you spend on groceries at Albert Heijn, you get one of these soccer cards uniformly at random. And the goal, of course, is to collect all of them. And there are 18 teams in the Dutch major soccer league. Let's, for simplicity, assume just 11 players per team. So that's 198 different soccer cards. And your goal is to collect all of them. Maybe not your goal, but somebody in the younger generation. And then the question is, how much money do you need to spend at Albert Heijn in order to sort of end up with a copy of each of the cards, at least one copy of each of the 198 different cards? Right now, it's going to cost you $2.50 in groceries just to get one card. So obviously, you need to spend at least 250 times the number of distinct cards. So that's 198 times 250. That's roughly 500 euros. But of course, if you go to the counter, you pay. You don't have control over which soccer card you're actually going to get for your 250. Like it's the cashier just picks one at random and hands it to you. Right, and if you're unlucky, this might be a copy of a card of which you already have another copy, and it means you're not making progress towards your goal of getting copies of all of the 198 different cards. And of course, Albert Heijn, the supermarket chain, knows this, and this is one of their dirty tricks to get you to spend much more. So let's try to see how much more you actually need to spend in order to sort of have high probability of getting at least one copy of each one of the 198 different cards. So this is the coupon collector problem. It's a very simple to analyze problem. I guess it appears in every introductory course about probability theory. So here's the analysis of how many times you need to sort of buy a card in order to have high probability of getting all of the cards, at least one copy of all of the cards. You might get multiple copies of some of the cards. That's okay. Right, so suppose that there's k different cards in total, right? K would be 198 in my example. And suppose you've already been to the supermarket a lot, splurged, spent a lot of money, and you already have at least I of the different cards you already have copies of. Right, and now you go again to the counter, you pay $2.50 for your groceries. Let's say you buy some toilet paper, and the cashier hands you another random card. So what is the probability that this is a new card, something that's not among the copies you have already seen? Well, you have already seen, or you already have acquired copies of I out of the, let's say, k different copies. That means that the probability of seeing a new one, so a copy of a new card, is k minus I divided by k. Right, so if I is very small, then this probability is close to 1, that's good. If I is close to k, if you've already got copies of most of the cards, then this probability is close to 0, which is not good. And how many times would you need to kind of sample from this set of k cards to see a new one? Well, that's the reciprocal of this probability, right? If you have probability of p of success, then the number of trials before you actually have a success, the expected number of trials will be 1 over that probability. So the expected number of new samples from the set of k coupons that you need to acquire one new one would be k divided by k minus I, and you can just sum this up all the way until the end. Right? So the total expected number of samples, when I say sample, you should just think of getting one of the k cards uniformly at random. The total expected number of samples would be the sum of k divided by k minus I running from 0, which is your initial number of cards, up to k minus 1, which is your number of cards just before you sort of conclude. And this you can easily manipulate by kind of massaging it into k times a harmonic series. And a harmonic series, of course, behaves like natural logarithm of k. So you can do this very precisely, and the total expected number of samples you need in order to get at least one copy of each of the k cards would be k natural log of k plus a lower order term, which scales like a constant times k. And that means that if your k is 198, if you want to get copies, at least one copy of each of the 198 different cards, you actually need 1162 samples. That's the expected number that you need, right? Times 250, because every time you want to get another sample, you have to buy it for 250 of groceries. So this means you actually need to spend in expectation nearly 3,000 euros instead of the 500 that you would spend if you could just sort of choose which card you get for each 250. And it's almost 6 times bigger. Of course, Albert Heijn is well aware of this. And you might hope to be very lucky, you know, okay, maybe I'm just a lucky person and I will get my k different copies after spending much less than 3,000 euros. But that turns out not to be the case, because the variance of this around this expectation is very small. So the variance is roughly k squared, which means that the typical number of samples you need in order to acquire at least one copy of each of the k cards would be k ln k plus or minus k. So the variation is just, or the standard deviation is just a lower order term. But then this is for sort of a nice and clean analysis. And there's a Q in TQC, so I need to talk about quantum now. And the question, of course, that I'm going to ask is, like, how could quantum help with this coupon collector problem? Now, if the coupon collector problem is just you're given uniformly random samples from a set of k elements again and again and again, and you want to acquire a copy of each of the k elements, the answer is just the same as classically, because there's nothing that quantum could do to speed it up. So we have to modify the setting a little bit, and the setting is to generalize the classical uniformly random sample to a quantum superposition. So the setup is now going to be the following. There's a universe of size n, and there's a subset of the universe S, which is unknown, and this has size k. And instead of being given a uniformly random sample from S, we're given a uniform quantum superposition over S. So I'm going to write ket S to be 1 over root k times the sum of all the elements in the set S. This is very similar to what Alexander talked about in his talk. And our goal here is to actually learn what the set S is. So the resources are similar to what Alexander talked about, but the setting is different. In his setting, the goal was to approximate the size of S. In our setting, we already know the size of S, it's this number k, and our goal is to recover S exactly, right? If you want to impress venture capitalists, you would call this an instance of machine learning. Our goal is to learn the set S as efficiently as possible, using as few copies of this state ket S as possible. Now, what could you do with this state ket S? Well, obviously you could measure it, right? But then you're sort of throwing away the quantum aspect and you're back in the situation of classical random samples. And the answer would be the same as classically, you need k log k copies to learn the set S. So we want to do something smarter than just measuring straight away. So the question of this talk is there something smarter that you can do? And the answer is twofold. There's some good news and some bad news. The good news is that if your set S is kind of big in comparison to the universe, so if the size k is almost n, in other words, if the number of elements of the universe that are not in S, I'll call that m for missing elements, if that number is very small, you can actually reduce the number of samples thanks to quantum superposition. So that's the positive news. The negative news is if the number of missing items is not so small, which means that your set S is significantly smaller than the universe, then there's really no significant improvement in the number of samples that you need if you allow superposition. So in that case, you might as well just immediately measure your state ket S to get classical samples and you won't lose much. So the remainder of this talk is just to explain this bit of good news and a bit of bad news. Let me start with the good news. So the beautiful thing here is that you're given a superposition over the elements of S. In fact, you're given multiple copies of that superposition. And there's a trick to take a few copies of ket S and to convert this into a superposition of the elements that are not in S. So kind of flip the problem around. Given superpositions over S, you can actually build yourself superpositions over the complement of S. And you can sort of see that if the complement of S is very small, then you can now use these superpositions that you created to sample the few elements that you need to learn the complement of S. And if you learn the complement of S, you also learn S itself. So this is what we're going to do. We're going to learn S by sampling the missing elements. And how does this work? So here it gets slightly technical, but really not too bad. So if you take one of these uniform superpositions over the elements of S, you can write it in the following way. It's a linear combination of square root k over n times the uniform superposition over the whole universe. That's a very simple state. You can also make it yourself if you like. Plus the remaining amplitude, square root of m over n, is sitting on some state psi. And psi I've written here below. And think of the case where k is large compared to n, so m is small compared to n. Then this state here, this psi, is essentially negative the superposition over S. So this is the kind of the part of the superposition that we like. So think of ket S as mostly uniform superposition over the whole universe and a little bit of superposition over the complement of S. So we would somehow like to kind of isolate from this the state complement of S, because if we could sample a few times from that, we could learn S complement and thereby learn S. Right, and I'm always thinking here about the regime that m is very small. So m over n is very small. So how can we sort of convert copies of ket S into copies of S complement? Well, suppose we do a simple two outcome measurement on one copy of ket S. So we just use a two outcome projective measurement where the first outcome projects onto the uniform superposition. And the second projector is sort of the complementary subspace, everything else, right? So the first projector has rank 1, the other projector has rank n-1. And it's easy to see that in that case, with a small probability, m over n, actually you will get the second outcome of the measurement, which means you get actually a copy of the state psi, which is very close to the complement of the superposition over the complement of S up to an irrelevant phase of -1. And the good thing is you also know when this measurement succeeded or not. So you can just sort of use roughly n over m copies of ket S, just repeat this experiment until one of them succeeds. By succeed, I mean that you get the second outcome of the measurement, which means you get your copy of ket psi, which is essentially ket S complement. Right, so you can convert an expected number of n over m copies of ket S into one copy of ket S complement, up to small error that I'm going to ignore for this talk. Right, and that means you can actually make a few copies of ket S complement and sample from them. Right, and your goal now would be to collect the m elements that are not in S itself, so the m elements from S complement. But this is again a coupon collector problem, except it's now on the complement of S instead of S itself. Right, so you can now sample uniformly up to this small error, which I'm ignoring. You could sample uniformly from the complement of S. And this complement of S has m elements. So with roughly m log m copies of ket complement S, you actually learn the whole complement S and thereby S itself. And this last line is really just another instance of the classical coupon collector problem. Right, so if you multiply this, you need roughly n over m copies of ket S to make one copy of ket S complement, and then you need roughly m log m copies of ket S complement to learn S complement and S. So in total, you need roughly n times log m copies of ket S. Actually, it's not clear that you need them, but they suffice for a quantum coupon collector. And notice that if m is small, in particular if m is constant, then this beats the classical coupon collector only by a log factor, but it's still kind of interesting because this is such a simple and elementary problem. And also notice that the procedure that we have here, you can think of this slide as an algorithm for learning S complement. It's extremely simple. There's no fancy entangled measurements going on. You just take every copy of ket S, you measure it with this simple two outcome measurement, which is easy to implement. You just do that by itself. Either it succeeds or it doesn't. You keep the copies that succeed. You measure those in the computational basis, and you're sort of sampling from elements of S complement until you're done. So this gives you, this is the good news. For small m, meaning sets S that are close to the universe size, you do actually get an interesting improvement in sample complexity. Like classically, you would need something like n log n samples. Quantumly, you need order n samples if m is constant. And of course, you could ask, like, is this now optimal information theoretically? Could we maybe get by with even fewer copies of cat S, maybe by doing fancy entangled measurements? And the answer turns out to be no. So this very simple measuring scheme that I described on this slide turns out to be information theoretically optimal. So I'm now going to talk for one slide about a matching lower bound on the number of copies of cat S that would be needed. That now we're actually talking about the number of copies that would be required or needed to solve the quantum coupon collector problem. And the claim is that it's exactly the same number up to constant factors as the upper bounds that I presented on the previous slide. And again, I'm assuming here the case that m is relatively small. So you need roughly k times log m many copies of cat S to learn the set S with high probability. And here's our approach to the lower bounds. We're going to use the adversary lower bounds. You've seen this in Alexander's talk at the start of this session, and this is no coincidence, of course, because both authors of the first talk are also authors of this paper. But the slightly paradoxical thing here is that we're going to use the adversary lower bounds, which is typically viewed as a query lower bound, even though there's no queries whatsoever in our problem, right? So our problem is really just a measurement problem. You're given a number of copies of cat S, and you want to do the best possible measurement to extract from this the classical description of the set S. But there's no queries here. So how on earth does it even make sense to apply query lower bound methods such as the adversary bound? Well, the reason is that the adversary lower bound is extremely general and versatile method, and it also applies to situations where you want to do state transformation. So there's no queries in state transformation, but the setup is exactly what we have. So there's let's say we're given T copies of this state cat S, and we somehow want to transform that state into a classical description of the set S that we're trying to learn. And this is also a situation where you can use the adversary lower bounds. Now I'm going to be slightly technical here, so this is kind of related to many of the things that Alexander talked about. So let's consider the Gram matrix, which consists, whose entries are the inner products between our starting states. So there's different possible sets S here, let's say S and S prime. You're given T copies of the uniform superpositions over each of them. So the inner product between two such states, one for S and one for S prime, scales like the inner product between one copy raised to the power T, because inner products just exponentiate with tensor products. So this is the Gram matrix, and it's indexed by the possible sets S and S prime. So the dimension of this matrix is n choose k by n choose k, because there's n choose k sets of size k. So this is the Gram matrix. It sort of describes the sort of the quintessential aspect of the state transformation problem. And you can have another matrix F, which is like the photonegative of the identity matrix. So it's 0 on the diagonal, and it's 1 everywhere else. And it turns out, and I won't prove this here, but it's a basic fact from the adversary method, that the state transformation can be solved if and only if the so-called gamma-2 norm of the Hadamard product of these two matrices is small. I want to also define what the gamma-2 norm is. Let me just state its dual form, which should remind you of something that Alexander talked about in the first talk in this session. So you can actually witness this gamma-2 norm being large by exhibiting a so-called adversary matrix. So the norm here on the right-hand side, this is just the operator norm, largest singular value of a matrix. And the gamma-2 norm of the matrix M Hadamard product F that we care about is equal to the max over all matrices with operator norm at most 1 of the operator norm of the triple Hadamard product gamma MF. This is slightly technical, but the point is that you can show that the problem is hard to solve for a given number of copies T if you can find an adversary matrix gamma that makes the right-hand side big. And how on earth would you do that? Well, the trick here is to use symmetry. Again, this is similar to what happened in Alexander's talk. So notice that the entries of both the matrix M and the matrix F, they really only depend on the intersection size of the sets S and S prime that index the rows and columns. And that means that we need mathematics to respect that symmetry. And this mathematics that respects this symmetry is something called the Johnson association scheme, also known as the Bose-Messner algebra. Right, so at this point, I'm just going to sort of wave my hands over all the technical difficulties, which are significant, but you can do in the end of the day, you can do very elegant calculations using the symmetry in these matrices to show that if the number of copies T is too small, smaller than this number here, K log M, then there is an adversary matrix that witnesses that the gamma 2 norm is too big. That's the way you establish a lower bound. I'm running out of time, so let me very quickly also broaden the scope a little bit. So far I've only talked about a situation where you're given copies of cat S. What happens if you, in addition, you can also reflect about the state cat S. This is again something that Alexander touched upon. And let me just zip through this very quickly. So using amplitude amplification techniques, you can actually get tight bounds for how many times you would need to use this reflection. So for instance, if you're trying to learn a state, trying to learn a set S of K elements, K would be N minus M, and universe size N minus the number of missing elements. It turns out that something like square root of K times M reflections suffice to learn a set S, right? So reflections actually give you a lot more power than just copies of cat S. Like reflections beat even the quantum coupon collector. So that brings me to my summary slide. Sorry, Ashley, I think I'm going 1 minute over time. So what's the classical coupon collector problem that we started from? The idea is you want to learn some set S of K elements in a universe of size N. You're given uniform samples from this set, and it turns out you need roughly K log K samples in order to learn S. This is necessary and sufficient. In the quantum case, we replace the uniform samples by uniform superpositions over S. And when M is small, when the number of missing items is small, the number of samples goes down in the quantum case. So superpositions really help when M is small. We also gave tight bounds for learning a state when additionally you can do reflections about S. I kind of skipped over that very quickly. And lastly, let me just mention one open problem, which is actually the motivation that led us to this problem. And that is the question whether, if you look at back learning, it's kind of a simple mathematical version of learnings from examples. You can have learners that are supposed to output a concept, a hypothesis from the concept class they're trying to learn from. And these things are called proper learners. And there's also learners that are more liberal, where you can basically output anything. Where, for instance, you could output a neural network even though you're learning a decision tree. And classically, it's known that these two settings are different in terms of sample complexity. So if you restrict your learner to be proper, in some cases, you probably need more samples than you would need for an improper learner. In quantum, this is an open problem. And the reason that this coupon collector problem is interesting is it sort of kills the one example that we know in the classical world, separating proper and improper learning. So the open problem I wanted to end with are the quantum sample complexities of proper and improper quantum back learning the same for all concept classes? I haven't really defined what back learning means here. For that, I'll have to refer you to the paper. So this is all I have. If there's any questions, I'm happy to answer them.
Great, thank you very much, Ronald, for that really nice talk. While people maybe start typing some questions into Slack and the Q&A, maybe I'll just ask a quick question. So the points about sample complexity of proper and improper packed learning. So are you would you be looking for a sort of equivalence up to like a log factor or something, or could it be that it's the same, like exactly the same, the sample complexity?
I think the hope is that they would be the same. I think this would be quite a surprising result. We haven't been able to disprove that. So it's really an open question. I'm not sure what to conjecture here. It would be very nice if it turns out that somehow in the quantum case, imposing properness on your learner doesn't cost you in terms of sample complexity.
Or you could say having improperness doesn't help you, is another way.
That's that's a slightly more negative glass half empty way of saying it.
Okay, so now some questions are starting to come in. So there's a question from Miriam Backens, who asks, if we're trying to learn a large subset of some set S, why can't we do it by learning the complement classically?
So classically, this trick doesn't work, right? So classically, you're sampling from the set S only. So if you look at the classical coupon collector, the way it's set up, there is a universe of size n, but you're really only sampling from the elements of the set S itself. So those k elements, you're sampling uniformly from that. And classically, we don't really have tricks available that could convert a random sample over S to a random sample over S complement. In the quantum case, we can do that. And there shouldn't be a way to apply similar tricks to speed up classical coupon collector, because classical coupon collector is exactly tight. K ln k plus low order terms is what you need, necessary and sufficient.
Okay, great. Thank you. We also have a question about bribery coming up from David Mestel, who says that if you have the option of bribing the cashier, classically it's clear what you should do. At some point you stop taking randomly and start bribing the cashier. Yep. What about the quantum version, where we could imagine you might be able to pay extra for a few more helpful states in combination with some cheaper uniform superposition states?
I think the same situation applies depending on how much bribing you're willing to pay. I mean, sort of initially, coupon collector problem is easy, right? You sample for the first time, you get a unique card. You sample for the second time, you're very likely to get another card that you haven't seen before, and so on. It's only near the end that it starts getting tough. If there's only a few elements from the set that you haven't seen yet, so at that point you should start to bribe. I think this is the same classically and quantumly. And of course, the number of cards you need would be proportional to k, at least. So with a bit of bribing, you can get the classical k ln k down to order k. The quantum lower bound is always omega k, because that's kind of the output size, so you can't get below that. So I think bribing would kind of bring the quantum and the classical regimes closer together, and make them even equal depending on how much you want to bribe. Of course, bribery is not allowed, so let's talk about it.
Okay, so we have maybe there are a couple more questions that have come up. Maybe I'll pass those along, and then future ones could be reserved for Slack as we're getting to the end of the session. So there's a question from Karol Żukowski, who says that in real life, the simplest solution for your nephew is to find colleagues that are collecting the same cards and exchange with them the duplicates. Yeah, is your quantum solution somehow similar, because you can exchange the redundant cards in some sense?
No, the quantum solution exists in a closed universe. You have no friends that you can trade with.
So it's a very bleak universe for the quantum algorithm.
Yeah, such is life. Okay, similar to the lockdown isolation.
Okay, so maybe we'll leave one more question. Well, ask one more question, then we'll leave it here for now, and you can ask further questions on Slack. So this is a question from Abhijit Pense, who says, your analysis here assumes a uniform distribution on states. What about if we have some other distribution?
It's a good question. So I think this has been analyzed quite a bit for classical coupon collector. What happens if you're sampling not from the uniform distribution, but something else? I think it's interesting to look at what this means for the quantum case as well. We have not done that. So this would be like interesting follow-up questions.
Great. Wonderful. So thanks again, Ronald, for a great talk with lots of questions. So sparked lots of interest, and indeed thanks to everyone for your questions as well. So I think now we're going into a lunch break / breakfast break / dinner break for everybody. So depending on where you are. So thanks again to everybody, and the next session will be, I guess. Next session will be in 2 hours' time. So thanks very much, everyone, and see you for the rest of TQC later on. Bye.
Yep.
Okay, we are starting in 1 minute. Okay, well, everyone, let's start the first of the afternoon session. So it will be about quantum tomography, and the first talk will be given by Louis Chabot, building trust for continuous variable quantum states. So whenever you are ready, please turn off your presentation.
Thank you, Alexander, for your introduction. So let me just minimize this. Oops, sorry. There we go. Okay, so this is a joint work with Tom Douce, Frédéric Gossens, Elham Kashefi, and Damien Markham at Sorbonne University back at the time when we did this work. You can find it on the archive at this address, and it will be also in the TQC proceedings. And since then, we have put on the archive another follow-up work, actually yesterday, which I will briefly mention. It's somehow an application of this work. So the outline of the talk would be the following. I'll give a motivation about this idea of building trust for states. I'll briefly give a few review elements about continuous variable and phase-based tools that we'll be mentioning in the talk. I'll mention also existing continuous variable tomography methods, and then I'll explain our works and what we did. So the setup is the following. We want to retrieve information about some unknown quantum state. So assume you have some black box, which is outputting some quantum state rho here. And you don't know anything about this state. And so you want to know what this state is about. And this is really a very fundamental task in quantum information processing that you can think of, right? And so we'll be considering it in the following setting, where you assume that the black box is controlled by some untrusted party, which we call the prover. And the verifier within this dashed blue box is trying to is asking some say specific state to the prover and trying to characterize this state. And so this setting is super general, and it encompasses, for example, the physical setting of an experiment where you can think of the black box here, the prover, as the experiment, and the verifier trying to characterize its output state. Okay, so there's this broad motivation about this. The first one is, verifying the validity of experimental data in the context I was describing just before. You can also think in the quest of building quantum computers, you'd want to certify that each of the components of your computer is working all right. So that would be a motivation. And then maybe a bit more paranoiac setting, where you don't want to make any assumption, or at least the minimal assumptions, on the black box, because it could be controlled by some adversarial party. So this is the case in quantum cryptography, right? So you could think of the setting of delegated computation. For example, you ask your favorite quantum computing company to give you to prepare for you some complicated quantum state, and you want to make sure that that they did the right thing. Okay, and we'll add an additional ingredient, which is we'll be considering this problem in the continuous variable setting. So here, by continuous variable, I mean kind of a broad, it's a broad term for just saying that we're considering states that lie in some infinite dimensional space. So this unknown state rho now can be written in some computational basis as an infinite sum over this basis of coefficients. And you see this is an additional burden for characterization of the state, because now not only it has the problem of, it's a quantum state, so we cannot perfectly determine it, and we'll have to repeat measurements to get information about it, but now all the information is also stored in some infinite vector. Okay, so just a brief review about continuous variable, if you're not familiar with it. So essentially, because we're working in an infinite dimensional Hilbert space, we'll be using some infinite countable basis, which is called the Fock basis. You see the elements ranging for all integer, and a single mode state, which is the CV equivalent of single qubit, would be now expanded in that form along that basis. And okay, and by the action on that Fock basis, we can also define the so-called creation and annihilation operators that are ubiquitous in quantum physics, which essentially act as ladder operators for this basis. You see A dagger is a raising operator, raising the element n of the basis into n+1, while A is a lowering operator, which decreases n to n-1. And from these simple operators, we can define these real Hermitian quadrature operators. So Q and P, and they're referred to Q to the position operator and P to the momentum operator. And these operators are extremely important. Their respective family of eigenstates give a basis, an additional basis, which is continuous for the infinite dimensional Hilbert space. So the basis corresponding to the Q operator would be the position basis, and the one corresponding to the P operator, the momentum basis. Okay, and now there's yet an additional representation of a quantum state in continuous variable, which is called phase space, which really builds on an analogy with the classical, mechanics phase space, where now you get a representation which is kind of symmetric in Q and P, where Q and P are given somehow the same role. So I won't be entering too much into the details, but essentially starting from some quantum state here, I took, for example, the vacuum state, the zero element of the Fock basis. You turn that state into some function over a 2D space. So here, the representation for the vacuum state would be some Gaussian probability distribution over a PQ space. But the difference with classical, or at least one difference with classical phase space, is that now you have representations that can take negative values. So in the case of classical mechanics, you would interpret these functions as statistical probability distributions over phase space. Here, this kind of probability distribution interpretation is prohibited by the fact that sometimes these functions can take negative values. And then this is kind of a signature of a fully quantum effect. And these representations, they're referred to as quasi-probability distributions. So there's actually a continuum of such quasi-probability distributions. So here I've schematically represented them on a one-dimensional axis. And the most renowned is the Wigner function. But actually you can switch between all these representations just by doing Gaussian convolution, as the formula below indicates. And in this talk, we'll be considering the special case of two phase space representations, so the Wigner function and this Q function, which is the so-called Husimi Q function. So each of these representations, they contain all information about the state, meaning that if I'm able to probe any of these representations, then I'm able to retrieve all the information about the quantum state. So the first possibility is the so-called homodyne tomography, where we're trying to probe the Wigner representation. So because this representation can take negative values, we cannot sample from it directly. And in practice, what happens is that, for example, this is the way schematically how it's done in optics. We sample instead from a marginal of the Wigner function, which itself is a probability distribution. So you see here on that picture, the 2D representation will be the Wigner, and on that yellow plane, you see the projection, the marginal of the Wigner function. And so for each angle theta, which in the experimental setup would be determined by some angle, some phase parameter of this ancillary state. For each angle theta, you would sample from a marginal. And in practice, what you do is you perform these measurements for many different values of theta. And from these, you reconstruct different histograms and you perform some mathematical reconstruction of the Wigner function from this from these cuts, essentially. So hence the name tomography. And so another probability distribution that can be probed is the Houssimi-Q function. So this time, for this representation, it is always positive, and it's actually always a probability distribution, and it can be sampled directly. So here is kind of the schematic, again, representation of a measurement setup, where now essentially it's just you're mixing the state, that the unknown state, with a vacuum on a beam splitter, and then you measure both output branches with homodyne detection as before, and you get two real numbers instead of one. You group these into some complex number. Alpha is equals Q plus IP, and this is the alpha, the argument of that function. Okay, so these are well-known techniques, not entering too much into the details. So what are somehow the drawbacks of these techniques? So for homodyne tomography, there's the fact that actually the state reconstruction method has to make assumptions on the measured state, and theoretically you would need infinitely many measurement settings, one for each choice of angle, to actually retrieve all information about the state. So in practice, you would choose a finite set of angles, but then that would induce some errors in the reconstruction. So heterodyne tomography doesn't have this problem. It only uses single measurement setting. It also has interesting symmetrization properties that I'll mention afterwards. But both of these methods, they make an assumption of bounded support on the measured state. This means that if you recall this vision where we have that black box, we need to assume that this state coming out of the box has a bounded support over the fog basis. Another super common assumption is the IID assumption, meaning that when we query the black box, we always see the same state. Maybe it's not the state we asked for, but we always see the same state. The state coming out of that black box are independently and identically distributed, so IID. And also it's not scaling well with the size of the system we're trying to measure. So this I'll mention a bit at the end of the talk. For now, we're going to restrict to single mode case. So what we've been doing is trying to address these different drawbacks to obtain some sort of reliable method for performing the same task, essentially. So we do it with heterodyne detection because it has this advantage of providing a single measurement setting. And we obtain a method that provides analytical confidence intervals that removes both the assumptions of bounded energy and IID. And also as an application, we're considering the multi-mode case where we are able to efficiently verify the output states of a boson sampling interferometer, for example, using this single mode protocol as a subroutine. So what I mean by analytical confidence intervals is the following. So again, we have that black box that outputs some quantum state rho. The verifier has to perform a single mode heterodyne detection. Many times it builds statistics with the samples, computes some estimates, given some target operator A with bounded support. And then we have this theorem that says, depending on the number of samples scaling with epsilon and delta, we know that the estimate computed by the verifier is close to the expectation value of this operator for the true state that the prover sent, with some high probability, right? And so interesting applications of these, well, if for the bounded support operator, you take this operator, then the trace of A rho directly gives you any element of the density matrix of the state you're characterizing. So you can really perform full density matrix reconstruction with this method. If now the operator is kind of a pure target state with bounded support over the fog basis, then this expression reduces to the fidelity between your target state and the tested state. And also here, we're not losing too much by assuming that the kind of target state is bounded support, because we can always, for any target state, we can always choose a bounded support state that approximated to arbitrary precision. Okay. So how it works, so I already said that the fidelity equals this trace, and we introduce estimates. So these are kind of just mathematical bounded functions such that the following equality holds approximately. So I'm not giving the full detailed statements in the talk, but you can go and see the paper. And so one reviewer pointed out, the TQC reviewer pointed out that you can see this part of our result as a generalization of the optical equivalence theorem for antinormal ordering. So if you're a physicist, maybe this will speak to you a bit. And then because of this inequality, so with the usual standard Hovding bound, we know that with the samples, we can estimate this expected value just by computing the sample mean. And then this sample mean is itself our estimate of a trace of a row. Okay, so this is all nice, but this Hovding bound, it only works if the samples are IID. Okay, so for removing this assumption, we're using a definity reduction cryptographic technique that let us remove this assumption. So briefly, the way it works, so this is kind of the full-fledged version of the protocol. The verifier asks the prover to supply him with many copies of some target state. Actually, the prover sends some state, so rho n plus m, meaning that that's a state which is over n plus n subsystems, but it may not be IID, it may be entangled between all the subsystems, say. And then the verifier will choose n of these subsystems at random. We'll measure them with heterodyne detection. And with the samples obtained, we'll perform some post-processing included in the definity reduction, which essentially will let him decide whether the remaining state is close to the target state or not. So this is essentially using a definity reduction for infinite dimensional systems. And an interesting application of that is that we're able to promote this kind of fidelity estimation for a single mode state to verification of multi-mode output states. So again, here, this black box here is the prover. Here is what he should do in the ideal setting. So this setup is the setup of boson sampling. If you don't know what this is, just this U here is an interferometer. You supply single photon states, say n, in this interferometer together with vacuum states. And so Aronson and Arkhipov famously demonstrated that if you measure the state that you get at the end of this row, now multi-mode row, with a single photon threshold detection for the appropriate range of parameters n and m, then you're obtaining samples from a probability distribution which is hard to sample classically, unless the polynomial hierarchy collapses, and even hard to sample approximately, meaning that if you were able to sample from another probability distribution which has some constant total variation distance with this ideal probability distribution classically, then this would have like terrible consequence under some reasonable conjecture about permanence of matrices. So not entering too much in the detail here, but the thing is, with our protocol, we are able to verify this multi-mode output state. So the way it works is the following. First, the verifier is going to measure all of the subsystems with single mode heterodyne detection, and it will obtain some vectors of samples, just here, the alphas. Then the verifier will perform a kind of reversing the quantum operation, but on the classical data. So this is using the symmetrization properties of heterodyne detection that I was mentioning before. And so the idea is that this allows the verifier to reduce the task of verifying this complex, very entangled state to the task of verifying the simple product, tensor product of pure input states. And now this can be done just with the previous protocol, the previous single mode fidelity estimation protocol. So with the corresponding samples obtained after applying this operation, we just apply the single mode fidelity estimation protocol. And we verify that here we are indeed having a good fidelity with a single photon Fock state, and here with a vacuum state. And from these bounds on the fidelity, we're able to retrieve a bound on the total variation distance with the ideal probability distribution. So I'm skipping a lot of details because, of course, when we want to remove on top of that the ID assumption, we need the definity reduction that I was mentioning before. But I urge you to see the actual paper for the details. And with that, this wraps up my talk. So thank you for your attention.
Okay, thank you very much for an interesting presentation. So please, any questions? I don't see any questions that far, but I hope they will get some.
Sorry?
See, I can't see any questions, but I hope we will get the questions. Okay, so there is one question.
Yep.
So, so the question is first, how have you removed the assumption of bounded energy as well as exponential scaling with respect to the number of modes?
So, so for the first part of the question, there are two ways of doing this. So in the first paper, we actually, here I talked about estimating the expectation value with an operator with bounded support over the fog basis. So this is a simple way of removing this assumption. Maybe I can just show the formula to be clear. Here in the trace of A rho, it has the same effect if rho is of bounded support or A is of bounded support, if you write this in the fog basis. So you might as well make the assumption on the target operator, but there's another way of doing it without making this assumption, which it essentially is just performing some energy test with the same sample that you get from the detection of rho to ensure that with high probability, the state indeed lies in some lower dimensional subspace. So this is, for example, part of the definity reduction, also to remove the IID assumption. And then, so for the second part of the question, the idea is that, so the previous protocol, the single mode protocol, gives you a protocol for performing fidelity estimation efficiently for a single mode state, right? Now, if you want to go multi-mode, the crucial point is that why isn't that, I mean, if it was a fully general state, of course, there would be no way of evading exponential. So the idea is that we use some sort of rigidity of pure product states. So once you've inverted this quantum U here in classical post-processing using the symmetry property of heterodyne detection, if you wish, you're back to just verifying this product state. But this is still a multi-mode state, and in principle, it's hard. But what you can show is that if you have some multi-mode states such that each of the single subsystems are close to some pure single subsystem, then the multi-mode state is close to the tensor product of the pure states. It really works because this thing is a tensor product of pure states, essentially.
Okay, thank you. So I have two more questions.
Yep.
So the first one is as follows. According to no-cloning theorem, we cannot copy the quantum states. Then how we are sure about that we are getting the same state from the white box?
We're not. So if we make the IID assumption, we are. But then maybe I can just show this slide. So essentially, so we're definitely not. Either you do the assumption, you make this assumption of IID behavior. You assume that it's always the same state coming out of black box. And this is what is currently done in physical experiment. In general, you do this assumption because it feels super reasonable because you just press the button and the same thing comes out each time. That there's no adversary behind the experiment trying to trick you. But for cryptography applications, you of course you cannot pretend that this is true anymore. And so this is one way of evading that problem. You don't make any assumption of that sort, and you perform a reduction. And the idea is that so you use, simply put, you use a definity theorem that says that if your state has some symmetry, so for example, permutation invariance, then if you discard a small fraction of its subsystems, the remaining state is quite close to a mixture of IID states. Okay, so this is what is true essentially in the, or almost IID state, if you wish. This is what is true in the DV setting, and in the continuous variable setting, you need to add some kind of energy test to make sure to bound the dimension of your Hilbert space. On top of that, this is essentially what this figure tells you. So you discard a small part, a small fraction of the subsystem, you perform an energy test on another fraction of the subsystems, and with the rest, you compute the estimate that lets you know that the remaining states are indeed close to the one you asked for. Yeah.
Okay, thank you. So the last question for now, and the remaining questions will be on Slack. So the last question is, does the verification of boson sampling assume the noise to be IID?
No, it doesn't. No, it doesn't. So we actually, in this recent paper, we derived various protocols. So one with IID assumption, which of course is much more efficient because there's definitely a reduction in induce an overhead, which is polynomial, but still. And we also derived the version without IID assumption. So essentially the assumption for that protocol as presented here is IID, but if you add the definitive reduction, which we did in that paper, then on the prover, you're making no assumption whatsoever. The only assumption that you make is that the verifier has access to single mode heterodyne detection and the validity of quantum mechanics.
Okay, thank you very much for your interesting presentation again. And so we're moving to the next talk. Okay, and the next talk will be given by Jonah Helsen, and it will be about spectral quantum tomography. So when you are ready, please share your screen and start talking.
All right, does this work? Yes, I am visible and you can see my slides, right?
Yes, everything works, yes.
Okay, perfect. All right, hello everyone. Thanks for coming, I guess. I'm going to talk to you today in sort of the second half of the tomography session. I'm going to talk to you about a new tomography protocol that we called spectral quantum tomography. And it's the tagline is, it's a simple spam robust process tomography method. And just as a housekeeping thing, they are working on my building today. So if you hear any banging in the background, just ignore it. I'll try to do it too. It's kind of unfortunate, but here we are. So this is, oops. This is joint work I did back when I was still in Delft. So I'm currently a postdoc at the University of Amsterdam, but last year I was at the University of Delft in the Netherlands, and there together with Francesco and Barbara Terhal, we sort of came up with this nice little protocol for estimating things in quantum processes. And there's a paper here, and we're sort of sponsored by all of these nice people. Okay, so what is all of this about? The goal of tomography and of process tomography in sort of the grand abstract sense is to characterize noisy quantum circuits. So, for at least a large subset of us, our goal is to build quantum computers. And sort of at a bird's eye view, you can think of a quantum computation as being composed of roughly three things. First of all, you prepare some initial state that maybe the L0 state, and then you apply a bunch of gates, like 1 and 2 qubit gates, and then you do some measurement in the end. And this is sort of your core loop. And then, maybe there's some classical pre and post processing, but a lot of all of the things that can go wrong are sort of here. And, in practice, in the real world, things do go wrong. Things can go wrong in your state preparation. Things can go wrong in your measurement, and things can go wrong while you're doing operations. And this is sort of, I think, the most important part. And it's also the part that we're going to focus on today. We're going to focus on something like sort of a broad field of things that I like to call process characterization. And this is really the study of what goes wrong. I'm going to put on a pointer here. What goes wrong in a quantum circuit when you try to run it on an actual quantum computer. And this is a very important thing, and correspondingly there's a lot of characterization procedures sort of invented already. People have been doing this for decades, and you might ask yourself, okay, what is really the need for having like just another variation of extracting information from quantum circuits. So I'm going to start with sort of a quick overview of what the process characterization toolbox looks right now. So there is, this is non-exhaustive. I'm going to pick out a few examples that I think are sort of common, but by all means, if I forgot your favorite protocol, it's probably going to be in there. So I think there are sort of four like sort of popular things going on in experimental world right now, which are randomized benchmarking, process tomography, direct fidelity estimation, and gate set tomography. And all of these have sort of different pros and cons. And you can, I think it's sort of nice to go over them. So I've sort of organized the pros and the cons of these four sort of main, I guess, classes of protocols, because all of these have a dozen different variations. And you can sort of characterize them by asking yourself, how scalable are they in the computer science sense? Like how many samples, how does the number of samples that I need to take sort of scale with the number of qubits in the device? How interpretable is the output? This is sort of a physical statement, like the number that comes out, how much work do I need to do to understand what is going on? Is it sort of easy to understand, or do I need to make a lot of assumptions on the underlying device? How detailed is it? Are we just making statements about sort of very average quantities, maybe averaged over gates even? There's quite a lot of difference between these protocols in terms of how much data they actually output. And there's sort of trade-offs between all of these things. And then there is a really nice one, which is the one that we're going to score well on, so I like to include it, and it's speed. And I mean speed here, in opposition to scalability, I mean speed in the sort of absolute sense. Like if you give this protocol to an experimentalist, how much time does it actually take to run on a practical computer? And there are things that are, you know, in theory scalable, but are in practice actually quite hard to do, and also the other way around. And then the last thing that I sort of want to include, because it sort of separates a few things from a few other things, and you know we're also going to score well on it, is spam robustness. And SPAM is sort of a technical acronym that stands for state preparation and measurement. And this is basically a dividing line between in process tomography procedures or process characterization procedures that allows you to, like, where the question is basically, can you lost my train of thought there. Can you extract information independent of knowing something about how well you can prepare states and how well you can prepare measurements? And this isn't entirely trivial. And for some of these protocols, you really need to make strong assumptions about your state preparation and your measurement in order to learn something about your actual processes. And you know, you can sort of score all of these things in terms of how well they do on these things. So for instance, randomized benchmarking is an extremely scalable procedure, but it's not very detailed. It outputs a single average fidelity, and this average fidelity is not even an average fidelity of a single process, it's an average fidelity averaged over a whole bunch of different gates. And sort of process tomography is kind of the other way around. It takes a single gate and you learn basically the entire matrix representation of it. But you know, this is very much not scalable, and it's also not spam robust because you sort of need to well characterize your state preparation and measurement. And you know, there are other things like gate set tomography that are actually spam robust and that are detailed, and you know, they're also not scalable because tomography inherently isn't really scalable. But this thing is, you know, in practice, it's extremely sort of complicated and difficult to do. It's a really cool protocol, but it's sort of hard to actually run, and it takes a lot of time. So we were thinking, can we find something like gate set tomography, but it's sort of simpler, it's easy to run, and it shares the spam robustness, but in practice, it's very fast. And you know, we thought about this and we came up with this really neat protocol that we call spectral tomography or spectral quantum tomography. And you know, it scores reasonably well on all of these boxes. It's also not scalable, but it is spam robust, as we're going to see. It's fast, which is really nice. we're actually going to implement it, and you're going to, if a theorist can do something on a quantum computer, that means it sort of works because we don't have a lot of patience. And it's also relatively easy to interpret, which is also quite nice. So this is sort of where this thing fits into the broader narrative, and what you should think about, what sort of the motivation for this is. All right, so what is spectral quantum tomography? What are we actually trying to measure? So in a sort of, so the thing we're trying to measure is what we call the spectral footprint. And that doesn't tell you anything because I haven't explained what a spectral footprint is. So imagine you have some unitary and you're going to implement it on a quantum computer. So this unitary is itself, it's distributed over a bunch of qubits, it's composed of a bunch of gates, sort of relatively abstract object. And if you're going to run it on an actual quantum computer, it's not going to be implemented as a unitary. It's going to be represented by some quantum channel, so a CPTP map. We're going to assume that everything is trace preserving, but in principle, everything works if it isn't, with like slight adaptations. And you can take this quantum channel and you can say, oh, this is a linear operator. I can pick a basis, and in particular, I can pick a basis for this quantum channel that is just the Pauli operators. And then you get sort of a resulting matrix, and this matrix is called the Pauli transfer matrix. And we're going to, in this Pauli transfer matrix, we're going to sort of take out the relevant part, because in if you have a trace preserving channel, sort of the bit that is associated to the identity operator isn't super relevant. I mean, it sort of is, but it's not going to be for our case. So we're just going to think about the part of the Pauli transfer matrix associated to the traceless Pauli operators. So from now on, whenever I say Pauli operator, I mean every Pauli operator that is not the identity. And the goal of spectral tomography, what we call the spectral footprint, is going to be precisely the eigenvalues of this operator. And this means that we're sort of making our first implicit assumption here, namely that this thing is diagonalizable, but that's sort of generic. But keep in mind that this is a thing that we're actually sort of assuming. So we're going to estimate the eigenvalues associated to this traceless subspace. Now, why would we care about these eigenvalues? Now, there's a few, we went and thought about this, and there's a few things that we can say about them. One is that they're sort of inherently spam robust information. If you take the process matrix, sort of the eigenvectors, you can't really learn without knowing something about your state preparation and your measurement, but the eigenvalues are sort of an inherently dynamical thing. So you should be able to extract these even if you don't control your state preparation and measurement very well. They have a nice operational interpretation, which I'm going to show you in a bit. And you can also relate them to a whole bunch of standard measures that experimentalists like and know, which is always a plus. So you can make estimates of the average fidelity, you can make estimates of the unitarity. And if you have a single qubit, and we go into quite a lot of detail about this in the paper, if you have a single qubit, you can actually also calculate T1 and T2 times. In the single qubit case, our protocol can be thought of as a generalization of sort of Rabi and Ramsey processes, which experimentalists have been doing for dozens of years. So we can't really claim a lot of credit for that, but we sort of generalize that in an abstract framework. So the operational interpretation is that you can think of these eigenvalues, they're complex numbers in general, and you can think of them as modeling how much your block sphere shrinks, which is the real part, and how much your block sphere rotates too little or too much relative to the actual eigenvalues of the operation you're trying to, the original unitary you're trying to do. And if you have access to all of these eigenvalues, of which there are quite a lot, so this is sort of the underlying dimension of the Hilbert space. If you have access to all of them, you can compute this sort of number that is a nice upper bound on the average fidelity between the unitary that you wanted to implement and the actual process you implemented. Now, you can't quite get anything more than that because average fidelity is inherently a somewhat, sort of depends on more than just the eigenvalues. It also depends on how the gates are properly, they have to, like, this doesn't really measure whether or not you're rotating along the correct axis, just how much you are rotating along an axis. The same for the unitarity, but sort of the other way around. You can measure how much your operation is sort of shrinking the generalized log sphere, and this relates to this nice measure that we know which is called a unitarity. So that's sort of what we're trying to measure. We're trying to measure these eigenvalues, and there's roughly d squared minus 1 of them. And now we're going to see how we're going to do that. And the actual process of this is quite simple. But first we have to make an assumption, because we're theorists, we're allowed to make assumptions. And we're going to make one very sort of basic, simple assumption, namely that if we take a gate and we apply it k times, we do our unitary k times in sequence, that the resultant superoperator related to that is actually just the original superoperator k times. And once you've done that, you can sort of do the following estimation procedure, which you can think of as doing process tomography on the diagonal of the process matrix for different values of k. So you apply this gate k times. So you prepare some Pauli eigenstate, which you do noisily. That's what this nprep is for. You apply your unitary circuit noisily k times, and then you measure in some Pauli eigenbases. And sort of do this for all the Paulis. And then you have to play some tricks to get rid of the identity. You have to subtract some probabilities from each other, but this is all possible. And you do this for different k's, and this gives you g of k, which is just a series of numbers. And since this is a trace and these are all matrices, you can write this really as a linear combination of the eigenvalues to the power k, where n is sort of the total number of eigenvalues, and some number ai, which is sort of encodes how well you did at state preparation and how well your eigenvectors align. You don't really care about these AIs. So you get some sort of generic time series g of k, which is a linear combination of exponentials. And now you can say, okay, cool, we have this linear combination of exponentials. Can we now estimate these lambda i's? And it turns out, you know, people know how to do this. In fact, people have known how to do this for almost 200 years. Actually, it's sort of an interesting story. Barbara actually sort of invented her own version of this for a different project, and then we wanted to use it here. And then we found out that there was a guy called Baron de Broglie who invented a similar algorithm, I think 225 years ago. So, you know, it's been a while. But this algorithm that I'm going to talk about has been reinvented at least 7 times. So it's sort of an interesting piece of mathematics that keeps popping up. And we're going to use a particular instantiation of it called the matrix pencil algorithm. So what you do is you take your data and you sort of chop it in half. This L, you can think of it as roughly like your total data stream chopped in 2, but you can sort of slightly vary it. So we're leaving it as an open parameter. And you make this big Hankel matrix. And then you chop this matrix further into 2 matrices. And then it turns out, and then you can sort of take these 2 matrices, turn them into a linear system, which is called a matrix pencil. And it turns out that the sort of the generalized eigenvalues associated to this system are precisely the exponentials in the linear combination. So they're the eigenvalues they're the spectral footprint of our original superoperator. So you solve this, you can just solve this. In practice, we do some in our experiments, we do some pre and post processing to make this more noise resistant. But I'm going to very quickly sort of tell you why this works, why you should, you know, expect this to work. So imagine this a signal that is composed of a single complex exponential. You can write down these 2 matrices. Now they just look, you know, it's a function of some prefactor and this exponential. And now it's quite easy to see that G1 is just G0 times lambda. So the only solution to this difference is precisely lambda equal to the lambda in G. And you can generalize this if you have a linear combination and you take your time series to be long enough, then any element of the sort of generalized spectrum of this matrix pencil is going to be an element, a complex element in this linear combination, and therefore an eigenvalue of this thing. So this is sort of how it works in general. And there's really nice performance guarantees for these algorithms. It works reasonably well in practice, as long as your eigenvalues are sort of well separated in the complex plane, which they tend to be as long as your dimension is not too high. So we've actually, you know, we put our money where our mouth was, and we implemented this on this sort of simple procedure on various experimental systems that we could get our hands on. So we implemented a pi over 4 rotation on the IBM Q. And this is really what I like to call the spectral footprint. So this is the complex plane, but sort of turned inside out. So the further you are away from one, the smaller the eigenvalue is. So it's sort of the other way around, and the rotation is still the correct way around. We found that this is a really nice way to represent sort of the differences between these things. So we implemented this gate for in an IBM device, and then we also implemented it in a device that we had locally at QTech, and you see that sort of our experimentalists were quite proud of that. You see that the number for the QTech device is just slightly higher, so we won a little bit. And then what we also did is to show that we could do this for 2-qubit gates. We also went ahead and implemented the same algorithm for a CNOT gate. And a CNOT gate basically only has 2 eigenvalues because it squares to 1. So it has a 1 eigenvalue ideally and a -1 eigenvalue. And the actual thing that we ended up finding had 4 eigenvalues that were sort of complex. And this is interesting, and you should count dimensions in your head. And I'm going to get back to this in a bit. But it's sort of interesting that there's 4 and not, 2 or 3. Yeah, so this is the last thing I want to talk about. And it's sort of all about what happens if we drop the one big assumption we made. So a lot of our goals was to make as little assumptions as possible and still have a viable, experimental procedure. And one of the assumptions that we had to make was this Markovianity assumption, namely that the power can be pulled out of the super operator, basically. But in practice, this is often not true. But it turns out that this data processing method, this sort of make a time series and then decompose it as a linear combination of complex exponentials, it doesn't actually care about this Markovianity assumption. It just spits out something. And it turns out that this makes spectral quantum tomography into a really reliable probe of non-Markovian effects. And we sort of investigate this in quite a lot of detail numerically in the paper, but I'm going to show you a few examples. So one of the things that we did was we said, like, oh, let's imagine a qubit that is coherently coupled to an external field. This is sort of a classic model of non-Markovian dynamics, and we're going to try and do the same sort of pi over 4 gate. And you see that instead of 3 eigenvalues, we get 7. And some of them are even larger than 1. And this is because at some point our signal sort of starts going up. So you get an extremely clear signal that something non-Markovian is going on. Because if you have a single qubit and you have know that your process matrix has dimension 3 and it's a real matrix, so it should have 3 eigenvalues, one of which is real. So if you see something like this, you know that something non-Markovian is going on. And now that I've told you that, you should think back and think about this 2-qubit CNOT gate that I showed you before, which was this IBM device. And you see, hey, there is 4 sort of eigenvalues that we detect, and none of them are real, which can't be because under the Markovianity assumption, the traceless subspace of the process matrix of a superoperator has dimension 15, so it must have at least 1 real eigenvalue because it's a real matrix. And this is clearly not going on, not here. So there must be something non-Markovian going on. So we put on our experimental hats and we went to talk to some experimentalists that we know. And we sort of tried to find the simplest possible model that could reproduce this. And the thing we came up with, this was sort of more for fun. The thing we came up with was a non-Markovian effect where instead of, you can think of your CNOT gate as sort of rotating 180 degrees across a fixed axis in 16-dimensional space. We proposed this little model we call frame accumulation, where every time you do the rotation, the axis just shifts a little, and this shift keeps building up. And it turns out that this, if you do it across any axis that is not the one that you were originally rotating on, you get something that looks basically exactly like the like the data that we also observed. And this is very robust. So it's sort of a nice thing that we can, propose simple explanations for these things that we observe, and we get to pretend to be experimentalists, which I really enjoyed. Yeah,
So
this is my last
time. Yes.
Yeah. So this was spectral quantum tomography. It's a quick, easy diagnostic tool. It's spam robust, and it's a pretty good detector of non-Markovianity. There's also lots of things that don't quite work yet. So it's not scalable, which is kind of annoying. And I'm thinking of like using sort of compressed sensing or shadow tomography techniques to make this scalable, or like scalably estimate an interesting subset of the eigenvalues. We also need to make these sort of linear spacings in the time series, which is kind of annoying. We would really like it to be a logarithmic sweep, because then we can get much more precise estimation of these exponentials. So I'm thinking about doing sort of more fancy signal processing using like sparse Hankel matrix reconstruction algorithms. And then there's also some fun things that are actually in the paper about what happens if your super operator is not diagonalizable and you have non-exponential decays. And this is, theoretically interesting, but also physically relevant, because if you have a critically driven system, this is something that actually happens. All right, with that, I'm going to end my talk. You can find all of our code and all of our data here, and you can find our paper here. And thank you for listening.
Okay, thank you for your presentation. And so we are running out of time, but we can have maybe one short question. Okay, it seems there are no questions, so let's thank Jonas again for a very interesting talk, and then we reconcile in half an hour with the next session. Thank you. Okay, we are starting in 2 minutes.
Can you hear me?
Yes.
Okay, great.
Okay. Hello, everyone. So let's start with the second section of this afternoon, Hamiltonian complexity. Okay, and before we move with the talks, maybe a slight thing. If you want to ask a question, so you can use both the tool question and answer tool or the Slack tool, and please start typing questions before the talk ends, because thus we will lose very few little time, and we are really short in time, and so it would be great if you could do that. And so going back to the talks, so the first talk of this session will be given by Anurag Anshu, and so its title is Improved Local Spectral Gap Thresholds for Lattices of Finite Dimension. So whenever you're ready, please, Anurag, share your screen.
Hey, all right.
Yes, looks good, yes.
Looks good, great. Okay, so I'm gonna start the talk now?
Yes.
All right, thanks. Okay, thanks, Alex. Thanks to the organizers for putting together a very, very nice program. And thanks for everyone for joining. As Alex said, I'll talk about the improved local spectral gap threshold for lattices of finite dimension. An object that looks like this is a favorite of many people, I'm sure in the audience as well. These are the system of interacting spins. But if you haven't seen it before, let me introduce a few slides to tell you about it. Here is an example of a one-dimensional system, which is a collection of some constant dimensional blue spins or particles. And these spins interact locally. And the interaction is defined by this term I plus 1, for instance, which for convenience is assumed to be a positive semi-definite matrix, and it is assumed to have a bounded energy, a constant norm. When you add together all these interactions, what you get is the Hamiltonian associated to these particles or spins. This Hamiltonian is a matrix, it's a positive semi-definite matrix, so it has a lowest energy eigenspace, which I'm going to denote by G. The space orthogonal to G is denoted by G perp. That's all the high energy states added together. And the difference between the lowest energy and the next smallest energy is called the spectral gap, which I'm going to denote by gamma. The same kind of formalism extends to higher dimensions. For example, here is a two-dimensional system of spins that are interacting. And in this case, you see this grid of blue spins. And for convenience, one would label them with these integers. Now, we can again assume that the spins are interacting in a local manner. So for instance, here we have spins interacting through a placket kind of interaction, which is this red square denoted here. As before, these interactions are bounded between 0 and identity. Once you add together all these interactions, you get the Hamiltonian of this particular system. Once again, the G is the lowest energy eigenspace, and G perpendicular is the everything orthogonal to it. Gamma is the spectral gap of the Hamiltonian. Now, for many researchers, a very important goal is to find ways to approximate the spectral gap of the Hamiltonian. This turns out to be a pretty important quantity in many contexts. For example, it can tell you about the phase in which the matter is. It can tell you about correlation and so on. Unfortunately, it turns out, thanks to a series of very nice results, that this problem is undecidable in the thermodynamic limit, which means that as the system size grows, it's hard. You cannot decide whether the system of interactions is going to be gapped or not. So one has to settle with a more realistic goal, which is to hope to find ways to approximate the spectral gap. This tends to be a pretty challenging problem. Now, in a special class of systems, which are known as the frustration-free systems, there has been a lot of progress in this direction. So let me spend a slide introducing you to these kind of systems. A Hamiltonian H is said to be frustration-free if the ground space is a zero energy eigenspace for every local interaction, which means that none of these local interactions are frustrated. Well, I mean, of course, if a Hamiltonian does not satisfy this property, then it is called frustrated. Now, when the Hamiltonian is frustration free, then you can assume that each of these local interactions are a projector. Because what you can do is that you can scale the eigenvalues of this local term to 1 without changing the ground space, because the null space doesn't change in that process. And with that, you get a Hamiltonian, which is a sum of projectors. Now, frustration-free systems are really well studied in physics and also quantum complexity. So for instance, we have the famous AKLT model, which probably introduced this class of systems, I believe, in more formal setting. This notion was generalized to parent Hamiltonians of tensor networks. There's a well-known Heisenberg ferromagnet. There's a toric code, and for computer scientists, most of the quantum satisfiability problems come under this class. Before moving ahead, I'll need the notion of local spectral gap, which I'm going to more formally define as I go along, but here is a rough idea. So fix a collection of spins on the lattice, for example, the one on this rectangle, the dark blue rectangle, and look at the Hamiltonian when you restrict these interactions to be contained within this region S, and let that Hamiltonian be H of S. Then I'll denote by gamma of S the spectral gap of the Hamiltonian associated with these particles. And note that, as before, I will the spectral gap is the difference between two distinct smallest and second smallest eigenvalues. All right. So the first result, which is relevant for this talk, is that of Knabe, which applies to transition invariant systems on a ring. Now, you might be a bit confused by the figure that's here, but the limits of my artistic ability are not the limits of your imagination. So just think of these spins to interacting together. So you think of this whole chain as actually a ring. Unfortunately, I couldn't draw it that well. So it's a transition invariant interaction where all the spins interact with the same local term. And Knabe denotes by gamma of t the local gap over all the continuous segments S of length t, where continuous means that you take neighboring spins up to length t. Knabe shows that the global spectral gap can be lower bounded in terms of the local gap as follows, where you lose a factor of -1/t. So larger the t gets, better you get to the estimate of the gap. And even if you can lower bound the gamma t for a modest size of t by, let's say, exact diagonalization, let's say you take t equal to 10 and you see that the gap gamma t is at least 1/9. Then you have established that the overall gap should be at least a good, not too large, but good constant. So that's a way to lower bound the gap. Also, one more interesting property of this statement is that if the system is known to be gapless as the size increases, then what it means is that the gap has to decay. For the frustration-free system, the gap has to decay to achieve that, achieve this gapless limit. So gap has to decay as 1/t, according to Knabe's result. Starting from in recent years, there has been a series of progress in this direction. So starting from the work of Gosset and Mozganov in 2016, who improved the result of Knabe to a quadratically better statement, which goes in the form given here. And it turns out that this statement is near optimal because the family of Hamiltonians known as the Heisenberg ferromagnet. These are gapless, and their local gap scales as constant over t square. Please don't quote me on these constant. I just rounded them off to the nearest integer in the right direction. So 5 is actually something else. It's a irrational number, and 2 is also an irrational number. But I just put 5 and 2 for convenience. They also proved a statement in higher dimensions. For example, in 2 dimensions, they showed that if gamma of t is the spectral gap over squares of width t and t cross t squares, then a similar statement holds that the global gap can be lower bounded by the local gap gamma t minus 6/t square. Just like Knabe, their result was for translational invariant systems. Soon afterwards, actually 2 years later, Lem and Mozganov, they showed that something similar, an improvement can also be seen for 2D lattice with open boundary condition. Knabe and Gosset Mozganov were considering closed boundary conditions, and they showed a statement of this kind. Castoriano and Lucia, they showed that when gamma goes to 0, gamma t scales as 1/t to a log factor, and looking at their work, one can convince oneself that it could be improved to 1/t square using some improved version of detectivity lemma, but I won't go into those details. Later, Lem showed that, so just to point out that these constants may depend on the dimension of the lattice over here, but Lem showed that this relation holds for any finite dimensional lattice. That means the gamma is at least gamma t minus 3/t. This line of work has been very successful because Lem, Sandvik, and Wang, they used these techniques along with some DMRG type kind of calculation to prove that the AKLT model on an hexagonal lattice is gapped, which was an open problem for a very long time. All right, so I'll jump into the results of this talk. It applies to any dimensional lattice, which may be periodic or non-periodic. It doesn't really matter. Translation invariance is not needed, but let me point out that in the previous works as well, translation invariance was not necessary, as far as I can see. So what we can show is that the gap is at least some constant, but that depends on the dimension, times the local gap gamma t minus 1/t square, where again, what is gamma t? It's the gap of t cross t cross t type hypercube. But we also have statements for more biased hypercuboids, and we can show that gamma is at least the gap of these hyperrectangles of certain dimension minus some constant divided by the smallest length of these rectangles, this family of rectangles. It turns out that this min over dependence on the smallest length cannot be improved, and it is witnessed by the Heisenberg ferromagnet, just like in the work of Gosset and Mozganov. These scalings may not be tight, that the dependence on dimension could be definitely improved. All right, so I'm going to describe all the tools that we use and then conclude. Let me quickly mention what happens in the previous works. They are based on this identity, which is a very neat way to capture the gap. What you do is that you square the Hamiltonian and then you try to lower bound it by a constant times the original Hamiltonian. So whatever value you can put here, you get a lower bound on the gap. This holds for frustration-free systems because the ground energy is 0. Now let's expand H as a linear combination of these terms. If you square it, you get this quadratic kind of expression. You can collect all these i's which are same as I prime. Sorry, there should be I. And you can sum over other terms like this. And it turns out that because I've assumed that the H is a projector, each local term is a projector, then I can write this expression as H plus this product of non-similar terms. Now, if it was the commuting case, then this term would be positive, this summation over I not equal to I prime. And you'd get that the gap is at least 1, which is true for the commuting case. But in the non-commuting case, these terms can be a problem, and one has to put a lot of effort to deal with them. And that's what is achieved in these works. Our approach will be different, and the first tool that we are going to use is the detectability lemma operator, which was introduced in this work a while back. And it's an operator that is defined using the local Hamiltonians, H, I, and I plus 1, for example. So for this, define the projector onto the null space of each of these local projector and take a product in a certain manner. For example, in this case, in the 1D case, I have these red and green projectors. There's a question. Maybe I'll take it towards the end. All right. So what you do is that you look at the orthogonal. Let me just take the question. Spectral gap of the Hamiltonian is the difference between the smallest and second smallest eigenvalues. Okay, so you take the product of these projectors, and that defines the DL operator, detectability lemma operator. You can define this also in 2 dimensions by taking the product of the red and the green and the blue and so on, these projectors. And the reason why this operator is very useful is because it is a proxy for the Hamiltonian. I mean, it kind of reflects the energy spectrum of the Hamiltonian to some limit. So for this operator, DL operator, the ground space is the highest energy space. And the eigenvalue, the largest eigenvalue is 1, and the second largest eigenvalue is 1 minus the gap, just like the Hamiltonian. So it kind of reflects this gap property. And it has a series of very nice properties. Using this operator, one can define what is known as the coarse-grained Hamiltonian. And this was introduced in a prior work in 2016. And it's a Hamiltonian made out of, it's very similar to DL operator, detectability lemma operator, but it's made out of these bigger operators, bigger projectors. So for example, if HI is the, GI is the projector onto the collection of spins, on the ground space of collection of spins, then HI, the coarse-grained projector H, would be summation over these orthogonal to these Gs, where each G acts on T spins. What we show as a first result is that the gap of these HT scales as T square gamma over 1 plus T square, which means that as you increase the coarse graining parameter T, the gap increases. So that's the coarse grain projector, and this factor comes out of Chebyshev, the properties of Chebyshev polynomials. All right. The next tool we use is a chain rule for spectral gap. I mean, that's how I see it. Feel free to think of it in a different manner. It is an observation due to David, and it relates the gaps of a collection of Hamiltonians that we have seen so far. So first Hamiltonian is the original one, H. It has spectral gap gamma. Hamiltonian, if you fix your region of interest to some size T, then there's a Hamiltonian on the segment of length T, and that's gamma T. We talked about gamma and gamma T. And also there is this coarse-grained Hamiltonian, whose spectral gap is gamma of HT. This coarse-grained Hamiltonian as shown here. The chain rule says that the gap of the original Hamiltonian is at least the gap of the coarse-grained Hamiltonian times the gap of the local region. It's like a chain rule. If you take a log, then it looks like the general for conditional entropy sort of. All right. So now the task is very easy. I'm going to use the chain rule, and I'm going to use the lower bound on gamma of ht, which I showed you earlier, t square gamma by 1 plus t square. I put them together, gammas cancel, and one can easily check that gamma t is at most this gamma plus 1 over t square, which was a promise statement. This was all for one dimension. Argument easily generalizes to higher dimensions. Doesn't matter what is the periodicity of the lattice. It applies for open and closed boundary conditions. So what you do is that you collect these interactions in these columns and view the whole thing as a one-dimensional system. You cannot do this in the previous technique of squaring the Hamiltonian because these columns are not projectors anymore. But in the current way of proving it, you can do it. All right, and then you relate the gap of the whole lattice to the gap of this red region. Apologies for this sound from the email. I should have turned this off. And then you relate that to the green region. So by this recursive analysis, you can prove the result. All right. So I'm at the last slide. A series of questions that would be nice to answer. It would be nice to figure out how does the gap scale as the length t. That means the dependence of 1 over t square. The factor there is important for practical applications. So could I prove nice bounds on this parameter 1 over t square? I mean, could the constants be improved than what we have so far? That would be very helpful in many settings. Also, under one very interesting problem is under what conditions does the converse hold for this result? It's not clear. The problem is undecidable in general, but can something be said for the frustration-free systems? And finally, if your Hamiltonian is translation invariant, could you improve this result in some ways? All right, thanks for your attention. That's the end of my talk.
Okay, thank you very much for interesting and well-timed talk. And so it's time for questions.
I hope I answered one of the questions that was in the Q&A.
Yeah, I think you answered
right.
that one, yeah. And yet I can't say anything else.
Does the reduction apply to? Yes, it applies to all dimensions. You can reduce for any dimension d. You can reduce it to. I mean, you can view it as a 1D system, and you can get the gap from bigger to smaller. All right. Henry asks, could you explain what is the? Oh, all right, sounds good. I'll go back to the slides. Oops, I just shared the screen. Oops. So the coarse-grained Hamiltonian is defined in the following manner. You look at the ground space projector on T spins. I'm doing it in one dimension. You can do also in higher dimensions. So you look at T spins together and let G with the relevant subscript be the projector onto the T spins, the ground space of T spins. When you define the Hamiltonian h of t as the sum over the orthogonal to these terms. So what happens is that as t increases, this Hamiltonian ht becomes more resistant to excitations because it's very hard to excite all these t terms. So you expect its gap to be better. But it turns out somehow, due to Chebyshev polynomial, due to the magic of Chebyshev polynomial, that the gap scales as t squared times the gamma, which is somewhat mysterious. But you'd expect t times gamma, but actually there's a bit of random walk kind of behavior. So the gap scales as t squared gamma. So this Hamiltonian has a better gap. Right. So one question by Anirban is, could you say a little more about what do you mean by practical ways of bounding the spectral gap? Well, so these techniques of using Kanabe kind of argument are very useful. For instance, these results and some optimization was used by these authors to prove that a KLT model on hexagonal lattice is gapped, which was an open problem for a very long time. So while the statement that we have is optimal for all dimension, the issue is that these factors that I wrote as poly of D have very large prefactor in the front. And it would be great to give nice bounds on these parameters. Let's say if this was 1 or 2, then you could imagine that you could take a decent sized lattice and you would be able to bound the gap. So by practical means, I really mean to improve these parameters, or in fact, also in the previous works, could you improve the techniques to apply it to more and more larger class of Hamiltonians in more relevant, more practical settings. I hope that answers the question.
Okay, it seems there are no more questions.
All right.
Okay, so thank you, Anurag, again for your very nice talk and nice answers to the questions. So let's move to the next talk. Okay, and the next talk is by Karen Moritz, and its title is Right Way Beyond Project State Approximations for Quantum Analog of Max Cut. So whenever you're ready, please share your screen.
Yep, I'm working on it. And can you hear me?
Yes, we can hear you. Nice. We can see you as well. Okay.
There we go. Okay, hi everyone. Thanks for the intro. So this is joint work with Anurag Anshu, who you just heard talk, and also David Gossett, who's a professor at Waterloo, and I'm actually a PhD student in chemistry at Toronto. And so the general problem we'll be focusing on today is the two local Hamiltonian problem, where we have a Hamiltonian, which is the sum of terms Hij, where each term Hij acts non-trivially only on qubits I and j. So we'll want to find the maximum eigenvalue of this Hamiltonian. Now, there's a couple of reasons you might be interested in this problem, one being that it's relevant to solving in problems in your real life, such as XKCD's rendition of going to the movies, but it's also relevant to some physics problems. The difficulty is that it's actually QMA complete, and in fact, it's been known for a little while now that it's even QMA complete to approximate the maximum eigenvalue to within a small error. So the two local Hamiltonian problem is a particular type of constraint satisfaction problem. And in the world of classical computation, constraint satisfaction problems are pretty well understood. So first of all, we know that they're NP complete. And moreover, we have the PCP theorem, which was a major result at the end of the last century, telling us that in fact, it's even NP hard to achieve an approximation for some constant approximation ratio less than 1, where the approximation ratio is defined as the value you've achieved over the actual optimal. But nevertheless, there's these well-studied approximation algorithms to deal with this. And we'll talk a little bit about that in a minute. Now, on the quantum side, there's still lots of room for discovery. So we know that these constraint satisfaction problems are QMA complete, but we don't know if the quantum analog of the PCP theorem holds. And we're still coming up with approximation algorithms. So in some sense, we're in the Wild West era here. So to give you an idea of some of the work going on in this area, I've included some highlights. So first of all, Garibian and Kempe have shown that for any two local Hamiltonian, there always exists a product state, as in a state which can be written as the tensor product of single qubit states, which achieves at least half of the optimal value. However, the best known efficient algorithm to calculate a product state only gives us an approximation ratio of 0.328, which was discovered by Hallgren, Lee, and Perec and announced at QIP this year. And so in order to try to do better than this, one common strategy is to consider a special family of graphs. And in fact, it's been shown that we can get approximation ratios arbitrarily close to 1 for these three families of graphs. So grids, planar graphs, and dense graphs. And then in a slightly different problem, Bravi, Gossett, Koenig, and Temme showed that for traceless Hamiltonians, there's an efficient algorithm to get an approximation ratio which scales as the inverse of the log of the system size. Now, I want to take a brief detour to go over the famous example of max cut and the approximation algorithm proposed by Gomans and Williamson. So max cut is the problem of trying to assign a 2 coloring to the vertices of a graph to maximize the number of edges with differently labeled vertices. So if you write that as a Hamiltonian, it can be written like this, where Wij is the weight of an edge, or the coupling constant, if you like. And then this Zi is the Pauli Z operator acting on qubit I. And so then we can define the cut value as the energy achieved by a computational basis state Z. And so the max cut is just the maximum over all of these states of the cut function. Now, it's well known that max cut is NP hard, so what can we do? Well, what Gomans and Williamson did is they considered an SDP relaxation, where this matrix M now, instead of being binary, is made up of real numbers and has these other constraints. And so this actually defines an SDP problem. So we know that we can efficiently calculate a matrix M which achieves this maximum value here. And then the problem is that's a real valued matrix. And so how do we turn that back into a valid input for the max cut problem? And Gomans and Williamson showed a randomized procedure to do this and proved that it achieves a 0.878 approximation of the true max cut. So in our paper, we consider the quantum analog of this problem. So given a graph G, we construct a Hamiltonian where for each edge, we apply this I minus XX minus YY minus ZZ operator. And the weight is weighted by the weight of the edge given. And so again, this is the Pauli X, Pauli Y, Pauli Z. And we're trying to find the maximum eigenvalue, which we'll call the opt for optimum. But now there's a slight hiccup, which is that even this restricted problem of the two local Hamiltonian problem is still QMA complete. But as it stands, it's a big open question whether it's QMA hard to approximate the maximum eigenvalue for some constant approximation ratio. So we'll be looking for some approximation algorithms for this problem. Now you might be wondering why that problem, and there's a couple of reasons, but perhaps the easiest one to explain is that it's kind of the quantum version of max cut. So what do I mean by that? Well, you'll remember that max cut has a Hamiltonian in this form. And so the maximum energy for a given edge is when the qubits at either end have a different value. So the state 0, 1, for example. But this Hamiltonian is classical in the sense that these terms are all diagonal and each term commutes with all the other terms. On the other hand, we have this Hamiltonian, which is sometimes called the Heisenberg model. And it's non-classical in the sense that these terms don't commute with each other anymore. But you can actually rewrite this as identity minus swap. And so you can see that a single edge has the maximum energy when the qubits at either end are anti-symmetric under swap. And so that would be the singlet state like this. And so it's kind of the quantum analog of the notion of difference across the two vertices. So given that, you might have the intuition that maybe we should try to approximate it this using the same strategy that Gomans and Williamson did. So let's see how that goes. First of all, note that you can write an n-qubit product state like this, where we're taking the tensor product over all of the qubits, and then these vectors are three-dimensional vectors, three-dimensional unit vectors, which are defining the x, y, and z components of the state of each qubit. And so then the energy of a state like that can be written like this, where for our Hamiltonian, you wind up just taking the dot product of the qubits defining the vector, or the vector defining the qubits at either end. And so then we're going to write the maximum product state, so the best product state, as the maximum overall states, which are tensor products of single qubit states of the energy. And so we're going to try to approximate this value. So let's define this function alpha, where this k is just used to define the dimensionality of the vector. And so then you can convince yourself that if the vectors are one-dimensional, this is exactly the same problem as max cut. And like we just said, if we keep to 3 dimensions, that will define a qubit product state. So again, you can see the sense in which our problem is the quantum analog of the max cut. And then you'll recall from before that the semi-definite programming relaxation occurred when we let the vectors be n-dimensional, and we wrote this instead as an n by n real valued matrix. And now remember, the key step before was how to turn that semi-definite programming solution back into a solution for our specific problem. So one way to do this was shown by Briette, De Oliveira, Filo, and Valentin, where they showed a randomized procedure to get an estimate that is within 0.956 of the best product state. And sort of a key point that we'll keep coming up against is that so far we don't know how to round an SDP solution to something which is not a product state. So their SDP rounding solution is to a product state. And you'll recall that Garibian and Kempe showed that the best product state is only half of the optimal in the worst case scenario. And so overall, this algorithm is only guaranteeing us 0.478 of the optimal value. So another strategy was shown by Garibian and Perec, and they achieved 0.498 relative to the optimal value. And they did that again by considering an SDP relaxation of the optimal value over all states, and then again rounding this solution to a product state. So they also noted that this is almost optimal in the sense that, for example, for our Heisenberg model on just 2 qubits connected by a single edge, the actual optimal state is the singlet state, but the best product state is the max cut state, which only gives us half of the optimal. And so Garibian and Perec's 0.498 is very close to as good as it can get in general for product states. So a natural question then is, can we do better with entangled states? And the challenge here is that most n-qubit states don't have a concise classical description. And worse than that, they can't even be prepared efficiently on a quantum computer. So obviously we're going to focus on states that we can find efficiently. Now, before I continue, I want to give a quick overview of our key results. So first of all, although Garibian and Kempe are correct that in the worst case scenario, the best product state is only half of the optimal, we can show that this is not tight for larger graphs. And in fact, we get a significantly better approximation ratio for large graphs. Next, for weighted graphs, we show that if we loosen our notion of product states a little bit to include products of 1 and 2 qubit states, then there's always a state that gets at least 0.55. And on top of that, we demonstrate an efficient algorithm to calculate a state that gives at least 0.53, which is the best known algorithm to date. Finally, we show a short depth quantum circuit which computes a state that outperforms every product state, but only for this restricted family of graphs. Okay, so let's start with that first result. So remember, Garibian and Perec had this almost optimal approximation algorithm in the sense that the best product state on the worst graph only gets a half. And our theorem shows that this is not tight for large graphs. And so if we use that algorithm that I showed you from Briette, De La Verafillo, and Valentin, we can get an approximation that is closer to 0.546 for large graphs. So before we prove this, you might be wondering how we can prove an approximation ratio when we don't even know what the right answer is. And what happens is this. So first, we'll find some way to upper bound the maximum eigenvalue of our Hamiltonian. And it might not be a good upper bound, but we can usually find some upper bound, such as assuming that we satisfy every single edge perfectly. And then we find an algorithm which outputs some state psi, and we don't necessarily know the energy of that state either, but we can lower bound its energy by its average value, because clearly the maximum eigenvalue can't be less than its average value. And so by taking the ratio of the lower bound and the upper bound, we get an approximation guarantee for the actual energy. So in our case, we're going to decompose the graph into stars and use that to get an upper bound on the maximum eigenvalue. And then we'll decompose the Hamiltonian into the X, Y, and Z components, which will allow us to get a state which achieves a lower bound. Okay, so what's up with these stars? The idea is simply that every graph is just a bunch of overlapping stars. So like there's a star, here's a star, there's another star. And you can see that you can take apart the entire graph into these stars. So we'll rewrite our Hamiltonian as the sum of the Hamiltonians describing each stars. And then since we double count every edge, we get this extra factor of a half. But then using that, we can use the triangle inequality to get this upper bound for the optimal value. Now, in order to use that, we wind up needing this lemma, which bounds the energy of the star by the sum of the weights of all of the edges plus the maximum weight of any edge in the star. So I won't go into the details of this, but basically we use this Lieb and Mattis result about spin eigenvectors on bipartite graphs. And then it turns out that this gives us a restricted problem related to the Laplacian of the graph, and we're able to use this result from Maris to get the equation in the lemma. So for now, let's just take this for granted and plug it in. And since we have an unweighted graph, this equation just becomes the degree of the central vertex plus 1. And so then when we plug this into our upper bound for the optimal value and sum over all the vertices, we wind up with an upper bound, which is the number of edges plus half the number of vertices. Now, we need a state with a lower bound, so we're going to decompose the Hamiltonian into the x, y, and z components. So each of these guys is just the sum of the x components, sum of the y components, and the sum of the z components. Okay, and so since all of those things are just exactly the same thing, but in a rotated basis, they all have the same maximum eigenvalue. So this lambda max is the maximum eigenvalue of one of these guys. And so using that gives us a different upper bound for the optimal value, which is assuming that we satisfy all three of them perfectly. And then we can also see that there's a product state which, there's a computational basis state which achieves this guy, which is the computational basis state solving one of these. And so the maximum product state has to be at least that, since that is a product state. So then we can rearrange these two equations to solve for this lambda max and plug in our upper bound for the optimal value from before, and we get this equation. So that actually takes us through the meat of the theorem, and we wind up needing to just consider the max cut state on spanning trees for sparse graphs. And then there's a little bit of simple algebra to get us to the statement of the theorem. So that gives us the theorem for the lower bound with product states. And when we combine it with this other algorithm, it gives us a way to calculate an approximation that's at least 0.546 times the optimal minus an error that diminishes with increasing number of edges. So now if we extend our notion of product state a little bit, our second result was that for weighted graphs, there always exists a state which is a product of 1 and 2 qubit entangled states, which gives an approximation of at least 0.55. And using that, we can efficiently calculate a state that gives an approximation ratio of at least 0.53, which is the best known efficient algorithm right now. So what's the idea behind this? Well, the problem with weighted graphs is kind of what you're seeing in this picture. So in the sort of generic case with randomly weighted edges, things are more or less okay, but you can imagine a case where many of the edges have very, very low weights, and then a few of the edges have very, very high weights. And so the energy overall is dominated by the contribution of these heavy edges. And we know that product states do very bad on single edges, and this is kind of like a collection of a bunch of single edges. But you recall that we also know the correct answer for a single edge, which is this singlet state. So you can kind of see where this is going. So what we do is for any edge, which is the maximum weight edge incident on the qubits at both ends, we'll put the singlet state for that. And then on everything else, we're just going to put a uniformly random bit string. And then we're going to compare the energy of the state we get from that to the energy of the single qubit product state approximations from the other algorithms that we saw. And so that doesn't get us quite to the right answer, and I don't really have time to go into the specifics, but you can see how that strategy would give us just enough of a push to get around the worst case scenario for product states and do just a little bit better. But up till now, we've barely gone beyond product states, and our intuition about this quantum Hamiltonian tells us that it's likely that the optimal state is actually a state with some entanglement. So what can we do about that? We took a first step in this direction by showing that we can use a constant depth quantum circuit to get a state which outperforms every product state, but only on this specific family of 3 and 4 regular graphs. So how does it work? First of all, we're going to start by calculating a state that achieves a good approximation of the max state using the max cut state, sorry, using the Gomans and Williamson algorithm. So that's this ZGW. And then we're going to apply this funny gate set to it. So for every edge in the graph, we're going to apply this 2-qubit Pauli gate, where if the qubit started in the state 0, then we'll apply X, and if it started in the state 1, we'll apply Y. And so we're going to do this 2-qubit thing for every edge in the graph. And why are we doing that? Well, sort of the intuition is that it creates the singlet state on the single edge graph, so maybe it will do something good in general. Plus, all of these gates commute, which makes it a little bit easier to analyze. So we can't actually just put the singlet state on every edge because we bump into monogamy of entanglement. So we're going to variationally optimize the circuit over a single parameter theta, which sort of defines how much we apply this entangling circuit. And you can actually just write down the average energy of this state 5 theta, which gives you this equation. And then when you plug in degree 3 and degree 4 and take the maximum over all theta, you get these values. And so that's how we outperform every product state on this restricted class. So overall, what we've shown is that we can do better than product states for this specific case of the 2 local Hamiltonian problem. And in particular, we showed that 1 and 2 qubit states can beat the product state lower bound over all graphs. And we've shown that using a short depth quantum circuit, we can prepare a state which outperforms every product state, but only for this specific family of graphs. And this is also all just for this specific Heisenberg model. And it would be much more interesting if we could say something about the 2 local Hamiltonians in general. So there are still lots of open questions here. And obviously the major one is the quantum version of the PCP theorem, which is it in fact QMA hard to get a constant approximation ratio to the maximum eigenvalue of a 2 local Hamiltonian in general? Maybe a bit easier, are there similar efficient algorithms which beat all product states in the general case? And as an idea, is there a way to round an SDP solution to an entangled state rather than to a product state like the algorithms that we've seen so far? So with that, I'd like to thank you for your attention and remind you of the relevance of this problem to your everyday lives, and I'll be happy to take some questions. Do we have questions?
Okay, thank you very much. Okay, we do have one question. I think it's approximate ratio of what?
I'm not sure what this is referring to.
Yes, it was early on the talk.
Yeah, I don't really. So in general, we're trying to approximate the optimal value, so the maximum eigenvalue. So probably that's what I was talking about at the time. I'm not sure if this person could.
Yes, our next question. So from Henry Yuan. So great talk. For the quantum circuit solution, can you explain what the input state is again? You mentioned it was the output of the GB algorithm.
Yeah, exactly. So our whole Hamiltonian is defined by a graph. So the problem is we're given a graph and we construct this Hamiltonian and we're trying to find the maximum eigenvalue. But we can also take that graph and look at what the max cut state on that graph is. And obviously we can't generally efficiently solve that, but we can use the Gomans and Williamson algorithm to get an approximation to the max cut state for that graph. And so that is the state that we start out from for our quantum algorithm. And then we apply this funny gate set to it to sort of push us a little bit farther into the entangled states.
Okay, any more questions? So another question from Konstantinos. Any thoughts on states prepared by deep circuits?
Well, we did a little bit try to look at sort of deeper circuits than this. So this is a constant depth circuit for 3 and 4 regular graphs. And we did try and do things like sort of applying this gate set twice with like 2 parameters or something like that. And honestly, it just turns into a nightmare to analyze. So I think there's probably something there, but I so far have not had any genius ideas on it.
Okay, so thank you. Another question from Phil Watson. Yeah, very interesting talk. It seems to me that the perfect answer to a max-cut problem is a computational basis states where all the vertices are 0 or 1. For approximate answers, entanglement seems to help a lot, as you say. Can you say more about what the role of entanglement is in improving the result?
Yeah, so for the max cut state, you don't gain. So for classical max cut, you don't gain anything with entanglement. It's a classical problem, and you're exactly right that the correct answer is a computational basis state. So everything is just zeros and ones, and that's fine. But for the quantum analog of max cut, so our Hamiltonian is actually I minus swap on all of the vertices. And so it's got the lowest energy when your qubits are anti-symmetric under swap. And so there has to be some kind of correlation between those qubits. And so we need that entanglement in order to get this sort of 0, 1, minus 1, 0 thing going on, so that when you switch the value, when you switch those two qubits, you get a minus sign on your full wave function, if that makes sense. So the role of entanglement here is trying to achieve that anti-symmetric condition.
Okay, so this will be the last question. So from David Master. So presumably the 5/7 is not tight. Is there any known upper bound?
I don't believe there's a known upper bound for how well product states can do. Yeah, so that 4/7 is specifically for the product states, and yeah, I think so. As you go to, so if you take the limit of a star, as a star gets to higher and higher degree, the product states get arbitrarily close to perfect because of the monogamy of entanglement issue, which you can basically think of as you can only solve a single edge perfectly. And this is kind of in that lemma that I didn't really go into. But you can only solve a single edge perfectly because of the monogamy of entanglement when you have a star graph. And so kind of you're only getting half on all of the others, even with the actual best state. And so the product state gets closer and closer to perfect in that case. But on the category of all graphs, I don't think, yeah, I hope that answers your question. I don't think there's a upper bound in general.
Okay, thank you, Karen, very much for your interesting talk and thoughtful answers. So let's move to the next talk. And so the next talk, sorry, is by Anirban Chandhari. And its title is Computing Partition Functions in the One Queen Qubit Model. So, yeah, so the floor is yours.
Is everything okay? Can you hear me?
Yes, we can hear you. We can see your presentation.
All right. Can you see it? Okay. Should I start?
Yes, you should start. Everything is fine, yes.
All right, thank you. So thank you everyone for coming to my talk, and I thank the organizers for putting together a great schedule and giving me the opportunity to speak at this conference. So today I'll be telling you about some work we put out on the archive a few months back, and this is about computing quantum partition functions in this so-called one clean qubit model. So this is joint work in collaboration with Rolando Somma and Yi Tsubashi from Los Alamos National Laboratory. So this work, in some sense, ties together some old and new ideas in quantum computing. The one clean qubit model dates back to the days when people use NMR quantum computing. And we use, in this one clean qubit model, some more recent ideas that have found use in quantum computing in the last few years. So partition functions are quite useful in physics in general. For a Hamiltonian H, a partition function at a particular temperature is defined as this trace of an exponential minus beta over h, where beta is the so-called inverse temperature related to the actual temperature T via this relation. So this partition function is sort of like a master key to computing, well, all of physics. Once you can compute the partition function, you can compute a bunch of other quantities in thermal equilibrium, such as free energy, entropy, by doing simple operations on the partition function itself, like taking log, computing derivatives, etc. And computing the partition function in the thermodynamic limit can tell you about phase transitions and critical points too. Outside of physics, the partition function also relates to various counting problems in computer science, such as finding perfect matchings of graphs or computing permanence. So it's a really useful quantity that tells us a lot of things. Now, as you'd expect, there is no free lunch. So computing this partition function turns out to be an extremely hard problem. Exactly computing partition functions is known to be sharp P complete. So that's numbers among some of the hardest computational problems we know of. Then you can ask, well, what about approximating them then? Well, it turns out that even for classical systems, such as classical Ising model, this turns out to be NP hard when you're asking for a multiplicative or a relative approximation to the partition function. Now, in many cases, you can get efficient classical approximation algorithms, but they work for certain restricted regimes, such as like high temperature partition functions or other restricted cases. In general, there are no efficient algorithms, or indeed algorithms that converge, or we know upper bounds on their running time, etc. In some cases, the estimation within an additive error, which is a slightly easier requirement, that can be done on quantum computers. So the bottom line is this is a very hard problem. And if you want to learn more about this, you can look at some of these references. Nevertheless, we're going to try to do it in something that is even more restricted than quantum computing. And this is this one clean qubit model introduced first by Knill and Laflamme back in 1998. So here, as the name suggests, there is only one clean or pure qubit. And there are a bunch of other qubits, n of them here, and they are in the maximally mixed state. So these are noisy qubits. So this is an idealization of what goes on in an NMR, or nuclear magnetic resonance-based quantum information processing device. On this one pure qubit, we apply a Hadamard gate, and then we do a control unitary, with the control being on the clean qubit and the unitary acting on the noisy qubits. After doing this, we measure this one clean qubit in either the Pauli X or Pauli Y basis. So that's all we're allowed to do. So one might think, well, what can we do in this model? But it turns out there are certain interesting things we can compute. One is computing the trace of this unitary. And we can do this by just looking at the probabilities of getting plus minus 1 outcomes of these various measurements. And that will tell us the real and imaginary parts of this trace. Now, we can only efficiently estimate the trace up to a normalization 2 raised to n. But nevertheless, this turns out to define what is called a TQC1 complete problem. So the TQC1 complexity class is a computational complexity class that captures what you can do in polynomial time in this model. Okay, and it turns out there is no efficient classical algorithm that can estimate this normalized trace in polynomial time. So this is something that seems to do more than what we can do efficiently on a classical computer. So our goal will be to map the partition function problem into evaluating traces of unitaries. And for that, we need to know, well, what is the complexity of getting this estimate? So the precision to what you get this estimate essentially depends on short noise, because we are trying to infer the quantity from measurement outcomes. So basically, if we want an epsilon additive error in our estimate, we need a number of measurements that scale as 1 over epsilon squared. So now we'll talk about more formally about the partition function problem. So we consider a Hamiltonian that acts on m qubits, and this is given as a sum of L terms, alpha L times HL, where each HL, if you looked at the last couple of talks, you can think of them being like local terms. So a projector acting on a few number of qubits at one time. And we can also relax this to being a unitary, which you can efficiently implement using like a constant sized quantum circuit. And we'll also assume that these alpha Ls are positive. And our goal is to estimate this quantity, trace of exponential minus beta h. For technical reasons, we'll assume that the norm of h is less than equals 1. But this is without loss of generality, since we can basically subsume this into this inverse temperature beta. So our goal is to estimate this quantity, and we'll consider 2 different error metrics. One is an additive approximation. That is, we want to return an estimate hat of z hat, such that the difference of that and the true value of the partition function is less than epsilon, where epsilon is some small quantity greater than 0. And we're going to do this probabilistically with some high probability. So again, this delta is a small number, small positive number, greater than 0. So this is an additive error requirement. The second we'll consider is a relative error approximation, or a multiplicative approximation, as it is known. So here we'll demand that the difference between these 2 quantities is less than a fraction of the true quantity itself. So this is a more stringent requirement. And the way to see this is, suppose your partition function itself is very small, something like 10 raised to minus 5. Then you're asking for an estimate of this partition function within a fraction of 10 raised to minus 5. Whereas here, if you say this z is 10 raised to minus 5 and your error target is 10 raised to minus 2, you might as well return 0 and you're fine. In this case, you won't be. Your estimate has to be as small as the partition function itself, as accurate as the partition function itself. So this is a harder requirement. And we'll find that both of these are in some ways related. So our goal will be to map this into evaluating this trace of this operator into evaluating traces of unitaries. And just to give you a brief overview of the results, the first result is regarding this estimation within additive error. So this turns out to have complexity that goes as this. So it's 2 raised to m over epsilon square, m being number of qubits, epsilon is the error, and delta is the failure probability, and beta is the inverse temperature. So because of this 2 raised to m factor over here, this is generally not efficient. But it turns out to have an interesting complexity theoretic consequence. So there's some previous work by Fernando Brandão that showed that estimating this normalized partition function z over, sorry, this should be 2 raised to m here, not 2 raised to 2m. This is DQC1 hard for certain log m local Hamiltonians. Log m local meaning that each term in the Hamiltonian acts on log m number of qubits at one time. So this within certain 1 over poly m additive error, this is DQC1 hard. Now, our algorithm, this result implies that this problem is in fact TQC1 complete. Because of this normalization over here, this thing kind of goes away and everything else turns out to be polynomial time. So this is the first result for additive error. Then we extend this to get an algorithm to estimate the partition function within relative error. And the result turns out to be similar to what we saw before. Here, the only difference is that we have this 1 over z in the denominator over here. So it's 2 raised to m epsilon r times z, whole thing squared. And I'll tell you how this comes about later. So again, this is not efficient in general, but we can hope that in some cases, it can give you a speed up where this z scales have some small exponential in m. So this is an algorithm that works in very general scenarios. We don't need, say, a high temperature regime. We can put an upper bound on how it performs for a wide variety of cases. Now, the only other algorithms that work on the broad regimes is basically classical diagonalization methods like Lanczos or exact diagonalizations. And those without scaling that go as 2 raised to m or worse. So you don't get this 1 over z in the denominator. And we hope that you can get some speed up from this. Now, to get this relative error result, we had to come up with a new classical algorithm that effectively iterates multiple rounds of getting additive estimates to return a relative error estimate. So that was a new thing we had to come up with. So now I'll go to the main tools here. So again, we have this 1 clean qubit model where we can estimate traces of unitaries, and we want to estimate the trace of this operator over here. So what we do is we convert this into an approximation with a linear combination of unitaries. We go through this integral transformation, which is effectively a Fourier series, and we can truncate and discretize this efficiently to get something like this. So these are unitaries now. These are evolutions with some Hamiltonian, and there are some coefficients here. These coefficients are Gaussian, so the net result is that these decay very quite fast, and this approximation turns out to be very efficient. So this is this is a result from one of our previous papers on preparing thermal states on quantum computers, and we use this. Now the next step is quite simple. We put a trace here, and voila, we have traces of unitaries, which is what we have here. Now we'll appeal to some known algorithms for simulating this real-time evolution. So there's I here, so it's a real-time evolution with this square root of h. Now the square root of h is a little worrying because how do you take square roots of Hamiltonians in general? Now there are techniques due to Boishu and Soma that allow us to construct an effective square root of h. I won't talk about that, but you can look at this paper or ask me later if you have questions about this. So this maps this partition function into a linear combination of traces of different unitaries that can be generated via time evolutions. And this is one way to do this. There's also an alternate way to get this mapped to a trace of unitaries, and that goes through this so-called Chebyshev approximation. So it turns out we can also write down this exponential minus beta h in this form, where these tk of h are operators that are basically Chebyshev polynomials in the Hamiltonian, and these ik of betas are Bessel functions. So we can again truncate this to get an approximation with just these few terms. And the cool thing about these operators, which consist of Chebyshev polynomials of the Hamiltonian, is that there are a wealth of quantum algorithm techniques to generate them. One popular thing being this cubitization method introduced by Lo and Chuang, which is an improvement upon some results by Childs from further back. So again, the main point is we can estimate this partition function as a linear combination of traces of different unitaries. So these things are unitaries, except they're not quite traces of unitaries. What the quantum algorithms do is they implement a larger unitary that implements these time evolutions or these Chebyshev things in a particular subspace. So what we need to do is effectively take a trace over a subsystem. Now, thankfully, there's a result by Shore and Jordan that lets us take even these subsystem traces without paying much overhead in the one clean qubit model. So that puts together all the pieces of the puzzle. We have the trace of this approximated by trace of sum of traces of unitaries. And this naturally leads to algorithms for estimating the partition function within an additive error. So doing all of this gives us this algorithm estimate add with some things, epsilon and delta, which are things we can control. This returns an estimate z hat, which is within some desired additive error, epsilon over here, with some high probability for m-qubit Hamiltonians. So I told you two approximation techniques, and they end up giving slightly different complexities. Here you will see it's 2 over epsilon squared, whereas here we have this exponential beta factor over here. And now this is a consequence of the fact that in this case, we are assuming this Hamiltonian to be positive semi-definite. So, and here this Hamiltonian can be negative. So the maximum partition function can differ. So this maximum value partition function here is 2 raised to m times exponential beta. Here it's just 2 raised to m. So there are some slight differences, but overall they have some similar structure. So this is the results for estimating with an additive error. Now we're going to take a further step and ask, okay, can we use these results now to get something that is a multiplicative approximation or a relative error approximation? So we want to get an estimate z hat, which satisfies this quantity. So the error in the estimate scales is some small fraction of the true partition function itself. And why we want this is because if you want to compute physical quantities, such as, for instance, the free energy here, that involves taking the log of the partition function. And if you want to, demand that we want an estimate of this within some additive error, this will correspond to a relative error in this partition function itself. So that's why relative error approximations are quite necessary in many cases. So one naive approach would be to just say, okay, let's get a lower bound on what is the smallest possible value of this partition function z. So let's put a lower bound on it, and let's call it z min. Then we set our additive error goal in the previous algorithms that I talked about to epsilon r times z min, and just use the previous algorithms as they were. So this would give us an estimate that satisfies this condition, because we have just replaced the z by z min, and that's the smallest possible value it can take. Now, the downside of this is that this would have scaling that goes something like this. And this is pretty bad, because our knowledge of the lower bound could be quite bad compared to the true value of the partition function itself. So what we would really like is for this z to show up here, not z min. And the question was, can we do this? And we thought of a procedure that goes as this. Okay. So again, we have this algorithm, this additive error estimation algorithm, estimate add epsilon delta, which returns an estimate of this form. And these epsilon and deltas are things we can change. This epsilon just depends on how many measurements we do in our one clean qubit model. So our rough idea is something like this. We start with some initial epsilon, which is quite big. Then we effectively zoom in. We keep doing estimations, then compare the estimate we get with the additive error goal we have set at that step. And now the idea is that once this additive error gets quite small compared to this estimate, then we can say, okay, we have converged, we have got relative error. We have got relative error that is roughly of epsilon r times z. So this z hat, which is the estimate returned by this thing, that serves as a proxy for the true partition function. So this is the idea. Keep reducing the additive error, keep doing additive error estimations, and compare your estimate and your error. And proving that this works is a bit of a work. Okay, the overall algorithm ends up looking something like this. We set our initial additive error to be this, which is the epsilon r is the relative error we want at the end of it, and z max is an upper bound on the partition function. So it's the maximum possible value of the partition function itself. Then we have a counter, and we just keep iterating additive error estimation with successively decreasing error goals, and also by reducing this probability of failure at each step too. And we have this condition that says we keep doing this unless this epsilon becomes small compared to this quantity over here. So the estimate you get multiplied by epsilon r over 2. And once this becomes smaller, we stop and output z hat. You can show that this will actually give you an estimate that satisfies your relative error condition. But the problem is that this thing ends up having no guarantee of terminating, because this estimate it gives you a estimate within epsilon only with some probability, which is 1 minus delta. So you can get supremely unlucky, and all your estimates in this iterative process can end up being outside this range, and then this method does not terminate effectively. And you can have other similar edge cases which can lead to problems. But what you can show is that if we run multiple rounds of this overall algorithm and consider the average number of iterations we do, we can show that it terminates after these many iterations, log 2 z max over z iterations. And from this, we can put a bound on the expected complexity of this process, again, just computing the average complexity of this entire thing. And this goes as something like this. This is where you get this 1 over z squared thing. You have 1 over epsilon r squared, 1 over delta r. And you gain a polylog z max over z factor here from summing over. And these dot dot dots indicate other prefactors that we had in our additive error estimation algorithm. So putting all this together, our overall algorithms end up having complexity that goes as this. The main thing to focus on again is this part, that it goes as 2 raised to m over epsilon r z squared. And again, we can hope that when this z scales somewhat with some small exponential in m, this can give you a speed up over exact diagonalization. In terms of future work, it would be nice to have a better comparison as to how this scales with complexities of classical algorithms, because here we have this 2 raised to m over z dependence, and we don't know this z. So it's hard to get a real idea of how this algorithm will perform in practice. So for instance, can we prove some kind of lower bound on z to get a better idea of the scaling? And the other thing would be to directly evaluate expectation values of correlation, sidestep the problem of evaluating partition functions altogether, because it's a hard problem, and just look at quantities that you actually measure in physical experiments. So this brings me to the summary, and in the interest of time, I'll just thank my collaborators and thank you.
Okay, thank you very much. And we actually have quite a bunch of questions by now. So, so the first one is from Sharia Kathar. And so what is the physical significance of partition function?
What is the physical significance of the partition function? Okay. So I'm not sure how best to answer this. It basically gives you an idea of how many microstates there are in a particular energy level in the way we have formulated it. So I guess that's the best we can do. That's the best I can do at this point. Okay. Yeah. Not sure how best to answer
so
that.
The next question. Yeah, so the next question, can you please explain why the norm of the Hamiltonian can be less than 1? Shouldn't the Hamiltonian be a unitary?
The Hamiltonian need not be a unitary. So let me go back a few slides. Let's see. So what we are doing is we are saying we can suppose this h has some normalization that is greater than 1. Because we're computing this trace of exponential minus beta h, we can just take that norm and put it into beta. So we'll have a renormalized beta. So in the complexities, wherever you have a dependence on beta, you can imagine that there's a dependence on the corresponding norm of the Hamiltonian as well. So we do not need this condition, but this is mainly for ease of analysis. We are effectively manipulating this expression over here, taking the norm and putting it into beta, and renormalizing the temperature.
Okay, thank you. So the next question is from Nagateya, and it's rise to results 2. Get this right. And so, is this independent of the multiplicative failure rate?
Sorry, can you repeat that?
Is this independent of the multiplicative failure rate?
I'm not sure I quite follow the question.
Multiplicative failure rate. So is this independent of it?
Can I just look at it? I'm not sure what I understand. I understand what is meant by multiplicative failure rate. So sorry about that. Maybe we can discuss this offline.
Okay, so the next one is why the additive error can be ignored when we use the time evolution approximation and Chebyshev approximation?
We are not ignoring the additive error in that case. So there is some additive error in the when we are approximating this. So there is some additive error here as well. Okay, but this has a logarithmic dependence on the additive error. So we can essentially suppress this from the final result. So the dominant scaling is 1 over epsilon, and there'll be some logarithmic scaling in 1 over epsilon too, if that was the question.
Okay, thanks. Okay, so the next question is from Sevak Garibian, and so great talk, thanks. So the question, slide 14.
Okay.
So on slide 14. So does the algorithm for conversion to relative error work as black box for more general additive to relative conversions, or are you using specific properties of the partition function here?
Sorry, can you repeat? Okay, sorry, I see the question. Okay. So, okay, this is a good question. So, no, this is a very general algorithm that will work for, I think, most additive error estimation problems. So this is something I should emphasize. So anything where you're trying to estimate a positive quantity within some additive error, you can put it to this box here. What's going to change is this complexity. Here, this epsilon r square, z square, and this dependence comes from the form of the dependence in our additive error estimation algorithm. So if this has a different form, if that had, say, a cube, it would be a cube here. If that had a polynomial in 1 over delta r, this would be a worse polynomial in 1 over delta r. So there'll be changes like this. But this general protocol, I think, will work for a wide range of problems. And anything that has an additive estimation algorithm which goes as 1 over epsilon square log 1 over delta, anything you do by looking at measurement statistics or just sampling, that you can fit into this and get a relative error estimation.
Okay, so the two last questions from the penultimate one is from Changpeng Shao. So what is M?
So M is the small m is the number of qubits, So 2 raised to m is the Hilbert space dimension.
Okay, and so the last one is again from Sevak. And any hope for doing better with more general algorithms beyond DQC1?
Yes, so you can use like a quantum, like BQ, like not BQP, but circuit model quantum computation. And there, what you would get is you will get rid of this 2. You will have some other dependence. I think you'll have 2 in this. You'll have like a linear dependence on this quantity, if I'm not mistaken. But I'll have to look into that more carefully. So you can improve some of these scalings, but it will be, I guess, an overall polynomial improvement in this. That's the best you can do in the general case.
Okay, thank you very much for your talk and for your answers to the questions. So let's move to the last talk of this session, and it will be going to be by Lucas Brady. And the title is Optimal Protocols in Quantum Annealing and QAOA Problems. Okay, so.
Can you see my screen?
I can see your screen. Yeah, I can see your screen. We can see you. We can hear you. Everything is fine. Please go on.
Thank you. Just 1 minute. Okay, so I'm going to be talking about several different types of analog quantum algorithms, how they compare to each other, how we can look for what is optimal among these. And this is joint work with some of my colleagues at the Joint Center for Quantum Information and Computer Science in Maryland. So to get into this, the first algorithm that I want to mention is quantum adiabatic optimization. Here, we start in some Hamiltonian B hat This is usually a simple Hamiltonian. Transverse field is very typical. That's what I'll be using for the numerics later on. And we know what the ground state of that Hamiltonian is. We're starting in that at time t equals 0. And slowly, we're going to evolve our system into the Hamiltonian C hat. This is some complicated Hamiltonian where we want to know what its ground state is. Typically in these kinds of problems, C hat will be a diagonal Hamiltonian where we're just looking for the bit string that minimizes the cost function along the diagonal. And the adiabatic theorem says that if you start in the ground state of this Hamiltonian, evolve slowly enough, you'll wind up in the ground state of this Hamiltonian at the end. And so you'll wind up in the ground state of C hat, which is what you want, where slowly enough is based off of things like the minimum spectral gap over the course of the evolution, some matrix norms, things like that. A slight generalization of this is quantum annealing. This is what if you want to go faster than adiabatically? What if you have a lot of noise? Quantum annealing is kind of just the catch-all for a more generalized form of adiabatic. And the analytics here are harder. They do exist. It's a very rich field, but there are issues here. And I do want to mention that this is what the D-Wave computer uses. I will not be talking about D-Wave at all. Quantum annealing is more general than D-Wave. There are other devices that can do this as well. And we can generalize even past quantum annealing to just this more generalized Hamiltonian here, where instead of a linear ramp or linear annealing schedule, we just have some arbitrary annealing schedule that I'll parameterize by this U. And what we're going to ask is, for a given time tau, a given amount of time that you have to run your algorithm, what is the optimal U of t that you want to do? There are numerous ways of looking at this problem, both to optimize U and other things here. Shortcuts to idiopaticity. What I'm going to be talking about largely is variational optimization. Quantum speed limits can help here. You can also analytically optimize this in some cases, for instance, with the analog version of Grover search. That requires an optimized annealing schedule to work effectively. And talking about variational approaches, QAOA, quantum approximate optimization, is one of the most commonly talked about near-term algorithms. And it's exactly this form. We have the exact same Hamiltonians B and C, but instead of doing a linear ramp, we're going to do a bang-bang structure, where we have B applied for some fixed amount of time gamma, then C applied for a fixed amount of time beta, or actually the reverse of that. We start in C, then B, then C, then B again. And these gammas and betas, the goal of the algorithm is to find the gammas and betas such that at the end, your energy is minimized, the energy with respect to the C hat. And the way we do this is the quantum computer can prepare the state with gammas and betas, measure what that energy is. We send that to a classical computer that then varies the gammas and betas based off of gradient descent or other optimization algorithms, sends it back to the quantum computer, and just this back and forth hybrid approach in order to optimize this as much as possible. So QAOA, typically what we do is fix the number of bangs that we have, the number of layers, which is given by P, and just have those bangs be as large as they want to be. We don't usually consider time constraints here. But for this talk, to put it on equal footing with quantum annealing and quantum adiabatic, we are going to fix the time. And maybe we're going to fix the time to be smaller than what that number of layers generally wants. We're not necessarily going to be able to get as good as if we gave them as much time as they wanted. But this will be a slightly different time-constrained variant of QAOA. I've talked about 3 different algorithms here. Quantum annealing and adiabatic might be considered the same algorithm, but what's optimal? What do we want to do? If you give me a fixed amount of time, what is the annealing schedule? What is that function u of t that I want to do? And at the moment, I'm going to ignore how difficult it is to find that u of t and just focus on what are some of the general properties of that u of t. Can we say anything about it? Do anything there? And in terms of best, I'm going to be talking about what gives us the lowest energy at the end. You could think of other metrics for best, but this is what we'll be considering. And some things have already been said here. So specifically, QAOA and quantum adiabatic are connected in some way. Namely, if you take quantum adiabatic with these smooth ramps up and down, you can trotterize it. You can break it into time slices as you're going. And those time slices should be small time slices such that at the beginning, you have a lot of your driver Hamiltonian, and at the end, you have a lot of your problem Hamiltonian. And this is actually how QAOA was originally proposed. Just what if we did this trotterization but didn't require the small time slices and did just a few bangs? Can we get anything good? And as you go to an infinite amount of time and an infinite number of bangs, QAOA should be quantum universal because it can approximate adiabatic. And adiabatic is universal, assuming that you have general enough Hamiltonians. In practice, it doesn't actually do that. QAOA with a fixed number of layers, giving it as much time as it wants, doesn't actually do a trotterization. The step sizes are not small. Another thing that's been looked at is in a lot of classical problems, the bang-bang form that you get in QAOA is time optimal and provably time optimal. And some initial results had proposed that that was the case for these kind of algorithms as well. So you should be looking for something that has the form of QAOA. There were some caveats with that though, and some things called singularities that are essentially exceptions to the results that were presented before that they kind of brushed under the rug. And our results are essentially those singularities, those caveats are actually extremely common and might be the problem in general, not the exception, at least for these quantum problems. So to get into this, let's look at optimal control theory. This is what proves that bang-bang classically is optimal in those settings. And for those of you who aren't familiar with optimal control theory, this is just the calculus of variations again. If you're familiar with Lagrangian mechanics, the derivation of that, this is the exact same mechanics, the exact same mathematics. So we're going to start with a cost function that we want to minimize. In this case, it's just the expectation value of our energy. And we want our state, this x here, to follow the Schrodinger equation. And to impose the Schrodinger equation in this case, we're going to use a Lagrange multiplier. So just this k here will be the Lagrange multiplier to impose that the Schrodinger equation has to be followed. And we'll just add that on at the end. And then we'll do a calculus of variations approach, looking for the x, the k, and the u that give us the optimum of j, that give us a critical point of j. And if you go through the machinery, you find some necessary conditions for an optimal. One of them is that you have to follow the Schrodinger equation. Our Lagrange multiplier was put in place to do that, so that's good. Another one is that your Lagrange multiplier follows the Schrodinger equation. And that they're connected, that the Lagrange multiplier, this costate k, has a boundary condition at the end, that it's related to your final state and the energy operator that you're looking for at the end. And I want to specify this Lagrange multiplier, it's kind of fictitious. It's just there to make sure that the mathematical machinery works and that you're staying in an allowed state. If you really don't like it, you can move it away for some time-ordered correlate or time-ordered commutators and things like that. But for our purposes, this is good enough. And there's one other necessary condition that comes out, namely the necessary condition of if you change u of t by a small amount. So if you look at the change in your cost function due to a small change in u of t, you end up getting this function phi coming out. And ordinarily, we would satisfy this with phi equals 0. But we have a slight problem. Our u of t, it's between 0 and 1. By that, I mean your experimental system can only go between B and C. You can't have negative C, for instance. You can't have 2C. This is just based off of how strong your magnets are or something like that. So we have to constrain U to be in some range that our experiments work in. And that means that the critical point you're looking for might not be in that range. It might be outside that range. And so to modify this, optimal control theory changes things up. So now, instead of an equality here, we have a greater than or equal to. That would be a less than or equal to if we were looking for a maximum. This is just saying for any allowed perturbation that we have, it has to increase the energy from where we want to be. And this gives us a little bit more freedom, because now if u of t is between 0 and 1, then yes, phi of t has to be 0. If u of t equals 0, then delta u can only be positive. And so phi could be positive and satisfy this. If u of t equals 1, delta u can only be negative. So phi of t could be negative and satisfy this. And so that's where it's coming in. And the big question is, can phi of t be 0 for a finite length of time? If phi of t cannot be 0 for a finite length of time, then we must be in one of the bang regions. U must be 0 or it must be 1. And what I've shown here in this plot is phi of t in the blue for a QAOA procedure in red. And this is normal QAOA, not time constrained, nothing like that. I specified that this had to be bang bang. And you can see that phi is positive when we're in a u equals 0 bang, negative when we're in a u equals 1 bang, and has to pass through 0 when you do a switch. And it turns out that for some classical systems, provably phi of t cannot be 0 for a finite length of time unless you have weird singularities in your matrices. It turns out that these singularities mean that you might not even be able to fully control your system, that you might not be able to do with it what you want to do. And those classical systems where this occurs most often is when your equations of motion are linear in x, your state, and u, which were actually not linear. The Schrödinger equation that we're looking at has our ket times our control variable. And so we're actually bilinear in this case. And so the things from classical control theory don't necessarily apply anymore. Can we say anything? We can actually. Specifically, at the beginning and end, we actually know what phi is. At the beginning, it's equal to this quantity lambda. At the end, it's equal to negative lambda. And lambda is a positive quantity. It has some physical interpretation as essentially how constrained you are, how much you're squeezing your system down into the amount of time. It will go to 0 for an infinite amount of time. And we have some inklings of how it does that. That's an appendix in the paper if you're interested. That's a little bit longer than I want to go into at the moment. Furthermore, phi is continuous. It can't do a discontinuous jump. We can put bounds on how big its derivatives are, all of that. And so at the beginning, these boundary conditions mean that we have to have a u equals 0 bang, and at the end, we have to have a u equals 1 bang. If you want to think about this heuristically, at the beginning, we are assuming that we're in an eigenstate of B. B is usually just a transverse field, and the ground state that we're starting in is just the uniform superposition of all bit strings in the Z basis, if we're looking at qubits or something like that. And so applying B to its own eigenstate isn't going to do anything. And so you want to apply C there. At the end, we are close to an eigenstate of C. We're actually not exactly in an eigenstate of C. That's our goal, to be in the ground state. But heuristically, to improve this state more, we would want to only apply B. That's not exactly what's going on. The mathematical machinery holds, but this is kind of the heuristic of what's going on here. And what about in the middle? So we have a bang at the beginning, a bang at the end. In the middle, well, we can actually have a lot of different things. We could have bang-bang regions. We can go through and prove that some singularities are possible. Phi can be 0 for a finite length of time, and there are multiple different ways for that to happen. I probably don't have enough time to go into what all of those ways are, but there are multiple different ways of allowing it. And if you go past that to asking what happens in the middle, that's a problem-specific thing. And so beyond that, we have to look at numerics. And what I'm showing here is numerics for a max cut problem or an Ising model. If you're more physicsy, they're the same model, just computer science to physics. And it turns out that most max cut and Ising problems have control parameters that are optimal that look like this. And you see that the green curve here is the optimal protocol that we found through a numerical gradient descent. And at the beginning, that green curve has a bang. At the end, it has a bang. And in the middle, it has some smooth annealing and maybe another bang. And this is a very general way that these look. And so in general, we're seeing for these Ising numerics that you get a bang anneal bang structure, kind of. And the portion in the middle there, that annealing region, that actually follows the singularity type, one of the singularity types that we found. That matches up with the analytics that we looked into. Furthermore, if you look at this, the red curve here is, well, the blue curve is phi for that green curve. So you can see phi is non-zero here in this bang. It's 0 during the annealing region and non-zero again for the bangs. And the red here is a time-constrained QAOA procedure for this. I've given it much less time than it wanted for this number of bangs. I constrained it to be the same amount of time as this procedure. And you can see it matches up very well with the bangs. But in the middle, it seems to be closer to 1 when the annealing region is closer to 1, closer to 0 when the annealing region is closer to 0. It's trotterizing it. It's breaking it up into time slices. And so this begs the question, is this actually doing a trotterization? If we increased the number of layers in QAOA, would we just get a trotterized version of this curve? The answer is yes. If you're doing a time-constrained QAOA, it does trotterize that annealing path there. And I want to remind you that unconstrained QAOA, where you let the bangs be as large as they want, doesn't do this, at least not in a simple way. There might be another way that it's doing it, but not a simple way. And if you look at the approximation ratio, meaning the energy as it's approaching the constrained QAOA energy as it's approaching the energy that we found through gradient descent for the optimal procedure, it is approaching that energy asymptotically. And it's approaching it as a power of like p, the number of layers, to negative 2.2, which is roughly in line with what we would expect from a trotterization error. So, just to conclude, what we're seeing here in practice is not a bang-bang as was expected, but some form of bang anneal bang as you're going through. And again, we've looked at numerics for Ising models, max cut mostly, but we expect this kind of behavior potentially from other models. We've started looking into those as well. And we can prove the actual shape of these here, given enough information about the problem. Actually finding these curves isn't that simple. you would need to do the gradient descent procedure we are doing. We have to do this numerically. On classical computers, we can go up to maybe 10 qubits to find these. If you wanted to do this experimentally, find these curves, that would require a large number of measurements of your system, more than what you would have to do for a normal QAOA procedure. And what we're finding is the normal QAOA procedure, where you're not doing a time constraint, actually has a very similar energy to this. And in fact, the energy scaling of that normal QAOA procedure seems to at least be polynomially related to this, at least in the numerics we're looking at right now. We're going into this a little bit deeper to see how that scaling actually relates between one and the other. But from what we've seen so far, it seems to be very similar. And another thing, the gradient descent procedure that we're doing to find these optimal curves is remarkably robust. I can give it pretty much any initial conditions for U of t, and it will find what we want it to. So there's more work to be done here. For now, this is the end of my talk, so I'm happy to take questions.
Thank you very much for an interesting talk. So there are two questions so far. So the first one, when we use it QAOA to approximate the adiabatic process, shall we consider the energy gap? And is the total evolution time of QAOA the same as adiabatic process?
So QAOA, as far as we know, doesn't care about the energy gap. Quantum adiabatic cares about the energy gap for its runtime. QAOA doesn't seem to do that. And there are provably cases where QAOA can run independently of a small gap and run in constant time. That's some work by one of my colleagues, Aniruddha Bapit and Stephen Jordan, where they showed that, as well as a few other papers. So QAOA potentially can go faster than adiabatically and might be able to, or can go faster than adiabatically. In practice, it's not doing anything adiabatic as far as we can tell, and might be similar to some of these sped up annealing procedures more.
Okay, thank you. So the next question from Karen Lawrence. Why is that if we are nearly in an eigenstate of C, applying B should help to get closer to an eigenstate of C?
Say that again? I think I dropped out.
Why is it that, why is it that if we are nearly in an eigenstate of C, applying B should help to get closer to an eigenstate of C?
So it's not necessarily that B is even the best thing to get closer to an eigenstate of C. It's just, if we're close to an eigenstate of C, applying C won't really do much to the system because it's not going to change the eigenstates. And so the only other ingredient we have in this setting is B. Provably, if you go through and add in a third Hamiltonian, maybe you want to apply that. Pretty much all that this is saying, if you have a third Hamiltonian, is you don't want to apply C. Maybe you want to apply B, maybe you want to apply your new D. That's going to be dependent on your problem. But here we're really restricted in what we're allowing ourselves to use.
Okay, thank you. So there was two questions. So the first one, okay, thanks for the great talk. Two dumb questions. First, if we take noise or other practical factors into consideration, what kinds of U, T over tau are preferred? And second, from the same person, shall we design different U, T over tau for different problems, or one function could fit a lot of problems?
So I'm going to answer the second one first. We want a different U of T for every problem instance even. In practice, we're seeing that they're very similar qualitatively, but they are different for every problem. In fact, they're different for every amount of time, as I'm showing right here. And the first question about what happens if you have noise, an open system, something like that, we haven't looked into that for the optimal procedures. For adiabatic and a little bit for QAOA, I think it's been looked into for QAOA. There has been some look at noise and how that affects this. In general, it becomes much richer. You have to be more careful, but you can do roughly the same things. At least in practice, QAOA you get close to what you would in the optimal unitary no noise case. And we haven't looked into it for these optimal procedures, but I would assume that it follows roughly the same pattern, especially because we're seeing that these have similar scaling to QAOA.
Okay, thank you. And the last question, so from Phil Watchow, very interesting talk. Is it understood why QAOA gives characterized adiabatic evolution in your case with fixed tau, but not in general?
That is something that I am continuing to look into for not fixed tau. I would be happy to talk about that offline, but that's something that I've been thinking about for 2 years and is a non-trivial problem. So.
Okay, thank you. Thank you very much for your talk again and for your answers to the questions. So this will end this session, and the next session is at 6:30 Latvian time, so it's in 25 minutes.
Good evening, good morning, good afternoon, everybody. I hope everybody can hear and see me, and they had stimulating discussions at the coffee break. Welcome to this two-talk session on error correction. The first speaker is Chris Pattison, and he'll be talking about a well-known problem with designing scalable decoders for multi-qubit codes. So I'm looking forward to that. And so take it away, Chris. Thanks.
Great. So this was work done at Microsoft with my co-authors, Palomi Das and Mohan Qureshi at Georgia Tech, and Srilatha Mane, Douglas Carmine, and Krista Svoor, and Nicola Delfos at Microsoft. So perhaps another title that's more applicable is sufficiently fast decoding for fault-tolerant quantum computers, because that's mainly what I'm going to talk about today. So if one considers sort of the state of error rates on quantum computers, so Google Sycamore is about 10 to the minus 2 errors per qubit per cycle. And in order to get to the regime of useful quantum computing applications, the ones where we might change the world, we really need to be at 10 to the minus 10 to 10 to the minus 15 per qubit per cycle. And so this really means that we need error correction. But there's some problems with this. Whenever we run error correction, we need to decode the syndromes, the result of the measurements. And whenever we run these applications, we want a logical cycle time that's going to be on the order of microseconds. Any slower, and it's going to take years perhaps to run our application. And so far, current software decoders seem to be too slow. There's very few decoders that have a runtime below milliseconds. And this is quite problematic, of course. So today I'll give some setup. I'll talk about sort of our concrete sort of instantiation that we're envisioning. I'll talk about the union find decoder. I'll motivate some computer architecture, and then I'll talk about our particular implementation. And then I'll numerically estimate the constants for our implementation. So first, our setup, we're going to consider sort of patches of surface code, each encoding a single logical qubit connected to some control hardware, and then some syndrome decoder on top. And so our control hardware is going to repeatedly measure the stabilizer generators of our code, and then send this syndrome data to the decoder. We're going to run the decoder, and then we're going to send the result back and apply the correction. So this is our setup. What can go wrong? We may not be able to measure the syndromes fast enough, or the stabilizer generators. So we can't get the syndrome fast enough. We may not be able to move the data to our decoder fast enough and back down. And finally, our decoder just may not be fast enough. And this last point is what I'll talk about. So what do we require from a real decoder that we expect to decode on our fault-tolerant quantum computer? Well, it needs to be accurate, because if we just randomly apply corrections, this isn't going to correct anything. And it needs to scale. So if we require a 55 kilowatt supercomputer cabinet, like the Summit supercomputer I've shown here, then we're not going to be able to run the decoder for thousands or tens of thousands of logical qubits. This isn't going to work. And then finally, it needs to be fast. It needs to be able to compute the correction corresponding to a syndrome roughly on the timescale of our logical cycle time. If it's too slow, then our syndrome data just accumulates. And concretely, let's consider some actual concrete system with a physical error rate of 10 to the minus 3 with measurement errors. And we need a logical error rate of about 10 to the minus 10. So this is distance 11 surface codes. And let's consider some large number of logical qubits. So let's say 1,000. And we want a logical cycle time on the order of microseconds. And to correct or to decode we're going to consider the union find decoder, which is just a map from classical syndrome bits to classical correction bits. It tells us which operator to apply to correct. And our result with this setup is that we have a decoder with a fast enough worst case runtime in order to correct, which that is, it runs no slower than on the scale of microseconds. So what is the decoder doing? Well, whenever we decode, we consider these errors are sort of strings of operators on our lattice. And whenever we measure, we're detecting the open endpoints of the strings. And so what we want to do is we want to match these endpoints up in such a way that we create a trivial logical operator, the identity, with some high probability. So here I've shown a potential correction, but unfortunately this correction leads to a logical fault. So really what we should have done is we should have closed the loop the other way, and this gives us the identity. So the union find decoder, it's an approximate decoding algorithm that has a proof of optimality in the lower regime. And asymptotically, it scales like the number of qubits times the inverse Ackermann function of the number of qubits due to its usage of the disjoint set data structure. So this gives us very fast set unions and set membership testing. And we use this to build clusters if anyone's implemented a cluster algorithm. We can fuse clusters in almost constant time. And most importantly, it's very easy to implement. Really, it's only sort of pointer lookups. If we were to implement this in software, there's not even integer addition. So the union find decoder has three main steps. First is this cluster growth step. We're going to consider, we're going to start with a cluster surrounding all non-trivial syndrome bits. And we're going to grow half edges from each cluster that contains an odd number of syndrome bits. And we're just going to repeat this process of growing half edges until two clusters meet, and then we're going to fuse them. And again, we can do this quickly because the disjoint set data structure. And then we're just going to repeat this until all the clusters have an even number of non-trivial syndrome bits. Then we're going to construct a spanning tree for each connected component, each cluster. And the spanning tree has this nice property that each vertex is visited exactly once. And then we're going to reverse the arrows on the spanning tree, and then we're going to deconstruct it in the reverse order. And as we deconstruct, we're going to look if we're pointed away from a non-trivial syndrome bit, and then we're going to mark the edges of correction and then update the syndrome. And so if we repeat this, we're going to end up with our correction operation. So let me move on to some computer architecture now. So what is computer architecture first off? Well, it's the pattern of transistors that I send to a foundry. So here I have the headquarters of TSMC, and a few months later, they'll send me back a computer chip. In this case, it's a microprocessor, but it could be some chip that's extraordinarily specialized to a particular task. So there's very strong evidence that general purpose hardware is not fast enough, and it certainly isn't power efficient enough to run the decoding problem for a large number of qubits. And so far, it seems that hardware specialization is necessary in order to run fast enough and to scale. And so the question we might ask is, what is the minimum amount of classical resources we need to decode a syndrome? How many joules does it take? How many microseconds does it take? And furthermore, really what we're doing is we're just estimating constants on what is the best possible or what is a extraordinarily efficient implementation of this decoder. In terms of our tools for computer architecture, there's going to be four main tools that I'll talk about today. Sort of memories, how we can specialize the logic, what that gives us, and then pipelines, and then this additional form of parallelism, sort of the sort you might find in like a multi-core setup. So in terms of our memories, we sort of have two flavors of memories. One is sort of a stack or a queue. we can push and pop on elements to the ends, and this is in constant time. This is extraordinarily fast, and latency is the name of the game for reasons I'll get into later. The other choice of memories is these random access memories, which we can read and write to arbitrary addresses in our memory, but we pay a price for this. There's about a logarithmic latency because we need extra circuitry to do the addressing for us. And so here I've shown some example memory sizes and the corresponding latency we get for that. So the SRAM, this 100 kilobyte SRAM, this is something you might see in the cache memories in your microprocessor. And this has a latency of roughly on the order of a nanosecond. And the other extreme is sort of DRAM. These are the big chips. If you're ever building a computer, you plug into your motherboard, and they're typically the size of tens of gigabytes, and they take about 100 nanoseconds latency. So there's a factor of 100 latency to go between these two. And then next, what does logic specialization bias? So I have sort of two cases where you can find online where somebody has built an ASIC for a particular task. So first, this is the Anton supercomputer, and here we show sort of a power savings of about 2 orders of magnitude. And power savings is twofold. One is a lesser power bill at the end of the month. The other one is that you can actually build more hardware now because you can get the power to your hardware, you can cool it, and you're not going to run out of money paying the power bill. And then the other case is Bitcoin. So people have built ASICs for Bitcoin mining, and you get about 4 orders of magnitude better efficiency, probably more by now. And in the Bitcoin case, this better efficiency means you're making money because electricity is the cost of mining Bitcoin. So next, let's talk a little bit about pipelining. So let's suppose that we have a factory for making French fries. We might need somebody to peel the potatoes, to boil them, to roll them out, and then to put them in the oven. So we could hire a specialist chef and give them a fully stocked high-end kitchen to make these French fries. But the problem is that they need to peel the potatoes, then they need to turn around and boil them, roll them out, and then put them in the oven. And they can only really do one step of this at a time. So instead, what we can do is we can hire 4 unskilled laborers and train them how to do one thing. We can specialize them, and maybe these laborers are even really good at boiling water or peeling potatoes, and even better than our chef. And what we can do is first we can give them the equipment for only that one task that they have to do, and they can be trained to do only that one task that they have to do. So far we haven't really saved any resources yet, but now we have speed. We can, much like an assembly line, the first person might peel a potato, hand it off to the second person who starts boiling it, and then they might start peeling another potato. So maybe it takes 4 steps in order to get the first batch of French fries done. But after that, each step, you get a new batch of French fries. So the throughput is increased. And then once we have one optimized assembly line of French fries, well, let's make 4 more. So now we have extremely high throughput. In terms of the individual amount of hardware that we need, it's much more efficient, and idle hardware is expensive. So the Union Find decoder has 4 main steps, or 3 main steps, and so let's build three specialized hardware units to do this. We have one hardware unit to grow the clusters. So it has this specialized memory, and some other registers, some various memories, stacks, this sort of thing, and then some control logic, which happens to be very simple. And then we can take these built clusters and we can pass them off to this second thing, which is going to just do a DFS exploration of all the clusters, and then pass the edges on to the next unit. And this next unit is going to reverse the edges and correct. So far so good. We have some very simple logic, and mainly so far the memory is the issue. So there's a few observations here. Modern CMOS logic is very, very fast. If I have a classical circuit to say add two numbers, two 32-bit numbers, this can be done in a few hundred picoseconds. So really, the logic is actually not the bottleneck, or not the thing we need to be thinking about whenever we estimate the constants. Really what's going on is our device reads a particular address in memory, turns around, and then based on that read, once it gets it back, it needs to generate another read. So the characteristic timescale is how long it takes for the memory to get us our data back. We're bottlenecked by read latency. And then additionally, once we've sort of optimized the individual, or once we've determined the constants for the individual components, can we do better? And the answer is yes. One might naively say, well, okay, let me, for each logical qubit, I have an X and Z syndrome to process. Let me put one decoding unit for each syndrome. Well, in fact, I can actually do better than that. Some hardware units are faster than others. And then furthermore, because of the pipelining, it may be no slower to process two syndromes instead of one. So let me just resize the width of the pipeline and actually input multiple syndromes to my same pipeline. And so this avoids the idle hardware because, so the reason why idle hardware is expensive is because there's still a clock signal, there's still transistor switching. Not as many, but it's still quite significant. And really, we want to maximize the parallelism because hardware is inherently parallel, and we want to get the most out of a given amount of space and power, a given amount of circuits even. So great. So let's actually estimate what this is. So we derive the number of reads from sort of the cluster size, the cluster shape that's generated in the cluster growth step. And we can estimate easily sort of how the DFS, or how many reads the DFS will use, how many reads the correction engine will use whenever we peel the spanning trees. And so really what we want to know is how long does a read take? Well, for a distance 11 surface code, we require on the order of about 10 kilobytes, actually a little bit less, but let's take 10. And on a modern processor, there's cache memories that are on the order of about 100 kilobytes with a nanosecond latency. This is actually a far larger memory than what we need, but it will give us the correct order of magnitude. In order to find the real number, you have to sign an NDA with your foundry like TSMC, and then you can't talk about it in a public conference. So we simulate this. So we sample the syndromes on our 3D lattice, and then we have an event simulator that we look at how long it takes for each hardware element to do its task and how it interacts with the other syndromes that we're currently processing, and then we compute timing histograms with importance sampling. So here's the data. And so this is the time to decode 4 syndromes for these 2 qubits, these 2 logical qubits. And you'll notice that the majority of the time is less than about a little bit over 300 nanoseconds. And I'll get to this shaded area in a second. So there's an observation we can make for here. So certain combinations of syndromes are exceedingly rare. And the unifying decoder depends on its runtime is extremely variable with the syndrome. So what we can say, in fact, is that it's very unlikely to get multiple syndromes that are very expensive to correct. So unlikely, in fact, that it's actually below the logical failure rate of the system. So what we can do is we can say that actually we don't need to correct. We can just time out, say that this is an error, and not continue the computation, and this won't increase the failure rate, the overall failure rate of the system. So we're allowed to fail with some probability. As long as it's small, it's not going to increase the failure rate of the system. And here we have a 325 nanosecond runtime. So great, it's fast. So here I've considered sort of phenomenological noise on surface codes. You can just as well decode, say, circuit noise, something like this. And then our design actually generalizes to the weighted union find with some overhead. You need some additional logic, slightly larger memories, but we don't expect it to change the constants too much. And we also neglect sort of the measurement latency and the data transfer latency, right? So how long does it take to do state prep and actually measure those operators? How long does it take to get the data to our device? We don't consider this. This is a problem for the quantum hardware engineers at Google, IBM, etc. And then we don't actually have any power estimates for this, but a fully embedded CPU, which has a lot more transistors, consumes about a watt. And it actually has a superset of the resources that we require. So we can tentatively bound this at a watt. And so we can scale up. If we want 1,000 qubits, we have an upper bound at a kilowatt. And this is a lot of power, but it's not megawatts like the full Summit supercomputer is. So in summary, what do we require out of this? We require that our decoder be accurate. We require that it scale. And we require that it actually has a worst case runtime shorter than our logical cycle time. And we've considered this. So we have a microsecond logical cycle time, and we have a fast enough decoder for running this. So we check all the boxes. And so with that, decoding for fault-tolerant quantum computers is possible. Thank you.
Thanks, Chris, for a good talk, and thanks for staying on time. I sort of answered my last question in the slide because I was curious about that last sentence in your abstract about providing numerical evidence that your optimized microarchitecture can be executed fast enough to correct errors. Now, I remember a talk by Austin Fowler a while back, who was saying this could be a bottleneck. So in what, I guess, in what sense do you improve over the potential bottleneck issue?
Right. So so previously, what people were considering is sort of min-weight perfect matching, perhaps run by software or some highly parallel implementation with some ASICs. And really, the problem there is that you have a very large overhead, and it's unlikely that you can do it fast enough based on what people have tried. And so we go from sort of milliseconds to decode a single syndrome to microseconds to decode a syndrome because our decoder has improved the algorithm itself. And then also we've sort of specialized our hardware for doing exactly that. And in this case, we can process the syndromes much faster, about 3 orders of magnitude, if you consider against the current software implementations. So
Gotcha.
it seems to no longer be a bottleneck, or
thanks.
So we need to think in this direction.
As a follow-up on that, an anonymous attendee says, thank you for an interesting talk. And the question is union find the fastest algorithm in your setup?
Well, of course, there's the constants, but so far it would seem to be the fastest that we can think about for decoding, say, service codes. There's, of course, min-weight perfect matching, but at the very least, union find is simpler. So it's unlikely that you're going to be able to execute it faster. Min-weight perfect matching, that is.
Okay, we still have a few 3 minutes for questions, so I'll just sit here in awkward silence for a little bit. I'm contemplating this question by somebody that was answered, that was asked. I'm not quite sure what they mean here. I'll just say it because I don't see any other questions. Is there so this relates to your assembly line analogy. Is there some way to peel the next potatoes before the previous ones are out of the oven?
Oh yes. So if we have an assembly line, that's exactly what we're doing. And this is important because this allows multiple hardware units to be operating at once instead of just waiting around idle, because idle hardware uses power.
Good, okay. David Mestel, sorry for butchering your name, asks, how do the costs for the 3 stages compare?
So the graph generator is about double the cost of the other stages. It takes about twice the number of reads per for a given size cluster to build it. So it's twice the cost.
Mm-hmm. Okay. Well, yeah, thanks for a good talk. You got lots of questions. That's good. I think we should start setting up for the next speaker. So Chris, you want to unshare, and the next speaker is Neil de Boudreau. He's going to tackle another problem well known in the community for doing gates. So forget decoding, error correction. Let's do gates that are fault tolerant. And there's this family of easy gates and a family of hard gates, and you want to do the least amount of hard gates as possible. And so he's going to talk about fast and effective techniques for T-count reduction via spider nest identities. Hi, Neil, you can take it away from here.
All right, thanks. Thanks for tuning in, and thanks for the opportunity to speak. Okay, so after that excellent introduction, I'll just add that this is joint work with Xiaoning Bian, working at Dalhousie University, and Quanlong Wang from Oxford University. I'm from Oxford myself, and this was funded in part with a gift from Tencent. Okay, so we're working in the setting of scalable quantum computations and algorithms on large error-corrected quantum memories. And in this setting, of course, we've got some simple operations which are harder to do than others in a fault-tolerant way. T-gates, frequently for error-correcting codes, not all the error-correcting codes, but for many of the ones that we think, surface codes in particular, I guess is what I'm talking about. These are more difficult to perform than other operations. And this motivates the problem of reducing the T-count, the number of T-gates, of a unitary expressed as a composition of Clifford gates and T-gates. Okay, so.
Hi, Neil, sorry, want to interrupt you. You have a build order window that I think is from the Mac version of PowerPoint open.
Yes,
I think if you quit
okay, sorry,
if you quit,
this is not quite what I hoped was being shared.
I think you just have to close the window. If you see it, it's a small little window in the bottom right. It says build order at the top. And you have 3 things in a transform circuit, accumulate, Pauli, and group.
Yes.
You see that window?
No, I don't.
Oh, I see.
Okay. I'm going to attempt to reshare. I apologize for this. I'm sorry, I'm having some technical difficulties. Okay, so you do not see, okay. Let me just attempt to share my entire desktop. Hope that I do not have anything embarrassing there. Do you see it in a presentation mode now?
Yeah, we're all good now. Thanks.
Okay, good. Yes, so the leading techniques for doing this. One is a collection of techniques by collections of collaborations, which I will describe here as phase gate fusion. So for example, these are rotations of merging of rotation operations after some circuit transformations. There's work by Alex Kissinger and John van de Wetering using the ZX calculus, where they transform the circuit into what I would describe as a more general tensor network, and then describe how phases can be teleported from one node to another. And Pauli rotation compression, this is not how they describe it, Zhang and Chen. And then separately, there's work with by Luke Heffron and Earl Campbell involving phase polynomials and Lempel factoring. Now, previously I thought of I thought of these as significantly different techniques. Actually, I would say that the second is a refinement of the first, regardless of the chronological order here. So this phase gate fusion typically involves transforming circuits to remove obstacles. So for example, to commute Hadamard gates and controlled NOT gates out of the way of unitaries, which would otherwise be able to multiply together to, say, 2 T gates, multiplying together to form an S gate, which is a Clifford gate, and therefore does not contribute to the T count. And that's what accumulating these Pauli phases are. In the case of Zhang and Chen's work, these are Pauli exponentials, which sort of leads into the approach which is taken by Heffron and Campbell. They transform circuits to obtain a hardcore subcircuit consisting only of C0 and T gates. So again, we have this idea of transforming the circuit to get some things out of the way. In this case, there's a significant transformation where we gadgetize the H gates. I will describe this because this plays a role in our work. They then analyze the subcircuit of the hardcore subcircuit in terms of multi-qubit phase polynomials, which I'll touch on. And then they apply complex identities rather than just multiplying pairs of them. They try to consider aggregates of them and find ways of simplifying them. So a very coarse-grained view of how people have approached this problem in the past. Our approach is sort of elaborating further on the work by Heffron and Campbell. And it was informed by the ZX calculus. Now here, the ZX calculus, I won't be using in depth. It will, in effect, be a way in which I represent the operations that are performed. They will always represent just unitary operators, sometimes multi-qubit unitary operators, and I'll try to make it clear how things are being represented. So, but also, what do I mean by parity phase operations? I just mean a unitary operation of this form, something which is an exponential of a tensor product of Z operators, giving rise to some relative phase on standard basis states, depending on their parity, whether or not their Hamming weight is odd or even. And this is the way that, this is the way that we'll be denoting them in this talk, and that we denote them in our paper, and also that you'll find in Kissinger and Van de Wetering's work. They've also been talked about by others. So for example, this collaboration from Cambridge Quantum Computing denotes them this way, in which case they can talk about exponentials of other Pauli operators. And it's not just ZX obsessed people who are interested in this. Of course, Litinsky talks about similar things, including the possibility to generalize to other operators. He would call this, I suppose, a Pauli exponential with an angle of theta over 2. So these ideas, the ability to talk about these, are certainly not exclusive to the ZX calculus. It just happened to point us in this specific direction. Okay, so there are operations which arise naturally, among other things, from the ZX calculus, and which we represent by phase gadgets. These are just these graph-like gadgets representing these operations as illustrated on the right. We transform circuits, as Heffron and Campbell do, to obtain a hardcore subcircuit, which we call a homogeneous subcircuit, consisting only of parity phase operations with angle pi over 4 or minus pi over 4, an odd multiple of pi over 4 generally, which are the ones that contribute each one of them a T count of 1. And then if you have several of these operations, they have a higher T count together. We attempt to reduce that homogeneous circuit by applying identities of these parity phase operations. And this is basically the idea of our talk, is phase gadget elimination tactics. The fact that it's the question of how you try to do this by applying these identities. So, we first, as many others do some circuit transformations. So this is a necessary step to describe how we get to the point that we want to get to. We take this circuit of Clifford plus T gates. Actually, we consider a very specific gate set consisting of the basic Clifford gates, X operators, Z operators, Hadamards, S, controlled NOT, controlled Z. We also allow controlled Z and T gates in our gate set. And then we isolate the T part, as it were. So the stages, we first turn the controlled NOTs and Toffleys into various controlled Z gates. There are more general, more sophisticated ways to do this than what I'm going to present here, or that we have in our paper. But basically, the more sophisticated a way you do this, the more power you can get out of any analysis. We then attempt to cancel and commute Hadamard gates out from the circuit interior, so using various Clifford commutation techniques. The reason why we do this, we try to do this while remaining within this gate set. easily analyzed gates. And the reason why we do this is because any gates that we cannot somehow expel from the midst of the center of the circuit, we're going to replace with a measurement-based controlled quantum computing-like gadget. Again, like Hafron and Campbell do. And a controlled Z gate, we just replace with a phase gadget decomposition of that gate. So when we're doing this decomposition, we also allow ourselves qubit preparations and measurements. And we allow these to be operated, we generalize from unitary circuits of the usual sort to circuits that allow parity phase operations, which can act on many qubits, not just pairs or threes of qubits. We then commute all of the Clifford gates out to leave us with this homogeneous subcircuit, and then we fuse phase gadgets that act on a common support together. This is again like the phase fusion that I described before, and actually this gives you some reduction in the T count, similar to what you have for those others, that first collection of works that I described, that all give similar results to one another. This is just the pre-processing stage, and then I'll describe the workhorse of the T-gate reduction later. So just to talk a little bit in detail about some of these steps, the expelling of H-gates. We're just pushing out these H-gates by commutations, basically using what techniques you can find to do so. We've got a specific technique, of course, although precisely that technique is not the most important thing of our work. Doing this perfectly might itself be a difficult optimization problem. I don't know whether or not achieving the exact optimum of reducing the number of H-gates in the middle of your circuit can be done efficiently, or if it's an NP-hard problem. We just content ourselves with doing the best that we can. To eliminate the H-gates, we apply this straightforward measurement-based gadget. Again, like Hafron and Campbell do. And the controlled Z gates, we replace with this, which is just expressed in terms of parity phase gadgets, the standard way in which you would represent controlled Z gates using 7 T gates and with controlled knots. In this case, all of the controlled knots commuted out of the circuit entirely. Clever decompositions are possible. If you were doing production work, you would want to use those clever techniques. In this case, we limited ourselves to something simpler, essentially due to the size of the team working on this. For the representation of T-gates, okay, so a single T-gate, as I mentioned, corresponds to a single parity phase gadget. If you commute controlled knots past it, you can just represent it as a different parity phase gadget and commuting X gates. So if you have an X gate that you want to commute past a parity phase gadget that has one leg or perhaps more legs, then all this does is it affects the sign. This is something that you would see if you just reasoned about this as an exponential of a Pauli operator as well. Nothing mysterious meant to be happening here. And this X gate that I'm talking about, it might arise from a measurement-based gadget, in which case it might be controlled on a measurement result. In which case it would be nice to factor away the measurement dependency of the angle away from the T count. We do this just by decomposing this into, again, basically the same phase gadget we had before, and a phase gadget with a higher, in a lower level of the Clifford hierarchy, a higher fraction of pi. And if that's controlled by a measurement result, then we don't have to worry about that in terms of the T count. We can just do that as a classically controlled Clifford later. For commuting controlled knot gates past these parity phase gadgets, if you've got a parity phase gadget acting in common with a control on a controlled knot, then this leaves the gadget unaffected. You can just slide them past one another, they commute. If the target acts on one of the feet of the parity phase gadget, then you add another foot where you had the control. Yeah, again, this is something that you could see fairly straightforwardly in the algebra if you wanted to think of this as just a Pauli exponential. So when we do this pre-processing stage, we start with some arbitrary circuit and we end up with a circuit with this structure. We've got n qubits, which are the original inputs to the circuit. We've got some auxiliary qubits, which we require for these measurement-based gadgets for performing Hadamard transformations. So we do end up adding a number of qubits to the procedure. This is one of the trade-offs involved in doing this. We have some Clifford gates that we perform, and then we do the hard core of the circuit, hard in terms of having a non-trivial T cost. And then we perform a bunch of rounds of measurements and classically controlled diagonal Clifford gates. And these don't contribute to the T count either. So it's this central blue box that we're focusing on. So far, the only things that we're doing here that are different from Hayfron and Campbell is that we're doing some additional circuit pre-processing that they don't explicitly consider, and that we've chosen a particular representation for the part that contributes the T count for the homogeneous circuit of pi over 4 parity phase operations. Okay, so then now on to the main body of the work, which is simplifying that sub-circuit. So this is the goal that all of these works have in common, of reducing the T count. Well, in the case of Hayfron and Campbell in our work, we've got this circuit only of these phase gadgets, only of these Pauli exponentials, and we want to produce an equivalent one with fewer phase gadgets in it. So they commute and they preserve the standard basis. It's effectively a purely classical problem that we're considering of equivalence of polynomials or equivalence of functions. It's a hard one in general, as Amy and Mosca noted. An optimal solution amounts to decoding of a Reed-Muller code on an exponential number of bits. So it's not something for which there are clear, fast solutions. The approach that was taken by Hayfron and Campbell is applying identities of symmetric 3 tensors, extending some work done by Lempel in 1975. And the approach at all, however, just amounts to some strategy of applying identities of phase gadgets. And this is what we focused on, just the fact that we're only just trying to apply identities of phase gadgets. And because it's a difficult problem, the question is what identities you try to explore that you can apply effectively. So a phase gadget identity is it's something like a hammer. It's an object in its own right. You can consider it its construction, how simple it is, how complicated it is. And then there's the question of how you might try to use it. So it's basically a way that you can try to use something that you have a grasp of in order to help to solve your problem. But it's just one tool out of many. If you want to practically simplify a circuit, you're going to have to select from a range of tools and know when you apply which tool. Not all problem is a nail that needs to be hammered. Sometimes you need a saw. Try to figure out how to use the tools that you have at hand in order to be effective at reducing your problem. So the program that we sort of pursued and that we suggest is that you have a purely mathematical, if you like, idea of exploring identities and the phase tactics, that is the phase gadget elimination tactics that arise from them. And then trying to find productive ways of deploying those tactics. So what are these phase tactics that we're talking about? So in this case, we just mean ways that you can apply identities. So we need to talk about the identities of these phase gadgets. And we talk about spider nest identities, and it'll become clear why we call them these. So here, I'm just going to describe an identity of phase gadgets. So here we've got a collection of, we're going to have a collection of phase gadgets acting on n qubits. Here I'm describing just n single qubit operators. These, depending on the value of n and what fraction of pi that turns out to be in that formula for alpha 1, these might be T gates or some power of T gates, or they might be powers of S gates. So they might have a non-trivial T count, or they might just be Clifford phases. But the identity that we're first considering is one where you've got the same angle on every single one of n qubits. And then you can on top of this, consider all pairs of qubits from the same set being subject to a phase gadget, again with the same angle as each other, this alpha 2, which is described there. And then you can consider all triples, again subject to the same phase, in this case just minus pi over 4. And then finally, a large gadget acting on all of the wires with phase of pi over 4. And the observation is that this is equivalent to the identity operator. Now, this essentially just corresponds to one particular code word of the Reed-Muller codes. So the fact that this represents the identity, it happened to be proven in our collaboration using the ZX calculus, but it's just essentially a mathematical fact that we're representing the ZX calculus. Yes, so we call this a spider nest identity because essentially it looks like one large mama spider together with a very, very large number of small baby spiders, large, of course, depending on what your value of n is, growing as order n cubed for n wires. just to give it a name. And we're not setting this out as a formal definition. This is just sort of generally the idea of the structure of this. We are also happy to consider as a spider nest identity any identity of this form, any composition of parity phase gadgets that compose to form the identity, to be equivalent to the identity, consisting of a handful of large parity phase operations and a multitude of smaller ones. Okay, so from that circuit that I displayed, depending on, and the smaller gadgets may be Clifford phases or may not be. So there's a question of which of those parity gadgets, which of those phase gadgets were actually usable for the reduction of T count. So we just attend to the fact that some of them are usable for reducing the T count and some aren't. The tactic arising from a particular spider nest identity is that for some subset of the qubits, you can consider some set of the wires in your circuit, and you count whether the number of phase gadgets involved in an identity is more than half of the, whether the number of phase gadgets involved in the circuit that act on just those wires is more than half of those that are involved in a given identity. And if so, then you can, just as a trial, compute what would happen if you just composed your circuit with the appropriate spider nest identity on those wires. The spider nest identity is the identity operator, so doing so shouldn't change the meaning of your circuit. And then you just compute the T count as a result of that. You use the substitution which gives rise to the greatest reduction out of the set of circuits, the set of spider nests that you have at hand. I'm going to quickly run through this example. This is just one example circuit. So here's the standard representation in terms of Toffleys and knots. You can decompose it. Here's the pre-processing to turn it into controlled Z gates with a non-trivial, controlled Z gates with a non-trivial T count. This happens to be how you'd represent it in terms of parity phase operations. There are 8 T gadgets there. So 8 gadgets contributing a T count. It turns out that there's a spider nest identity that looks like this, with a large spider acting on 5 wires, a large spider acting on 4 wires, and the accompanying baby spiders. You fuse those together, those baby spiders together, to get a reduction in the T count for them. And by applying the corresponding spider nest identity, you get a reduction to 7, a T count of 7 in this case. Okay, so using these in practice, our approach is to consider the spider nest identities on 4 qubits and all compositions of spider nest identities that you can have on 5 qubits. So those are 63 circuits in total, 63 families of identity or circuits equivalent to the identity. We attempt to reduce the T count by applying, for each of those identities, some number of trials in sequence on random wire sets of size 4 or 5. R is some constant. In our case, it happens to be 20,000. The runtime analysis for this is order m squared time, where m is the number of gates in the circuit. We compare this with order m to the 5 for Todd. The asymptotics are sort of useful, but the proof of the pudding is in the eating in terms of the actual amount of time that is taken. So in our work, we don't account for the number of Clifford operations. We don't attempt to reduce them. This is a trade-off that you'd have to take in practice. Our runtime is actually dominated by the Clifford gate preprocessing, not by the T count reduction steps. Some improvements are possible there, perhaps. It's very unlikely that the particular strategy that I'm showing there it's likely that it can be improved upon. Again, we've chosen this just to get work done and due to the size of our team. Here's a quick glance at the results. The full table is available in the article, of course. So the things that I'd like to point out is that we don't always have the best recorded results in terms of the T count, but they are frequently the best that we could find. And they're not always the fastest results. In fact, we are sometimes substantially slower for the smaller circuits in particular. But for the larger circuits, we're faster generally. And we are frequently the fastest and also the best at the same time as being fast. So in summary, T count reduction, it's a difficult problem where you're going to have to be content with various tactics for reductions and ways in which you deploy those tactics effectively in order to get reductions of the resources that you're going to require. Isolating the part of the circuit which has a non-trivial T count, as Hefron and Campbell do, it does seem to be quite effective. There's going to be a question of trading off of, say, C0 count. But if T count is the most significant barrier to you, then it's worth considering. And simple strategies for applying phase tactics, I would say that the tactics that we're applying are fairly simple. And to apply to these particular operations, they prove to be both fast and effective in practice. And I would say that there's plenty of potential for still further improvement on that. Okay, thank you for your time.
Thank you, Neil, for a good talk. Couple minutes for questions. There was one so far, and somebody's asking you to remind us why we need to decompose a circuit into Clifford and T-gates in the first place.
Well, for a great number of error correcting codes, the easiest operations to perform are Clifford operations. So it's natural just to decompose it in that way. To decompose it, well, decompose it into the simpler operations that you can perform and to isolate the harder parts is just one reason that you can do this. For most error correcting codes, it so happens that the ones that are simplest to perform are Clifford operations. Here I'm being quite agnostic about what error correction code that you're using. There are some error correction codes for which T-gates are simple, so in which case this work would be somewhat less urgent, perhaps. But for those for which the Clifford gates are easiest to perform, it's a natural decomposition. And there's maybe a historical bias as well, that people like to distinguish the Clifford parts, which are easier, for example, to simulate from the T-count. So there are a number of reasons for doing it, but pragmatically informed by design for performing it on error-corrected memories, and particularly if you're being slightly agnostic as to which error-corrected memory you're going to use.
Right, thanks. I had a quick question. When you had that slide where you reduced 8 gadgets into 7, I noticed one of them was a very, very small baby spider. And so I'm curious whether you've looked into if it's possible to use these identities to reduce the locality of the gadgets.
That's a reasonable question. Now, something that I didn't touch on at all is the fact that you wouldn't actually realize these operations by trying to realize these gadgets directly. This is a tool to represent, to reduce the hard problem of, attack the hard problem of reducing the T-count. There's the question of, well, then how would you realize those operations? And the answer that makes the most sense to me, in many cases, would be you would simply reduce it back to controlled NOT gates and T gates. There's the question of the most effective ways of doing that, what those would be. If you're using the surface code at least, and I expect perhaps also color codes, but maybe more relevant for the surface code, you could try to more directly realize those parity phase gadgets through the splittings of memories and re-merging them. So through lattice surgery. Now, if you had long range parity phase gadgets, this would probably require a very flexible architecture. Think more photonics than, say, silicon. So yeah, that would not be something that would work for all platforms. So there's a couple of ways that you would do it, but actually, I would suggest doing it for CNOTs, doing it with CNOTs. Now, that still leaves us the problem of reducing the locality of these operations. We haven't looked into that. That's definitely a good question to look into. There's the question of what will cost more, the CNOTs or the T-gates. And that's something that's going to be relevant in any application. The more costly a CNOT is for you, the more important it will be to reduce the locality of those phase gadgets. We haven't looked into that, but it's obviously a relevant problem.
Mm-hmm. Okay, cool. I don't see any more questions, so last call for questions if anybody has them. You can always contact the speaker offline. And yeah, I guess if there's no more questions, I guess I want to declare this session and the whole day of the first day of the conference closed.
Thank you again.
Thank you, everybody. I think the local organizers will have the time of the next session up now to remind everybody when to tune in tomorrow. If not, I can check. Yeah, so tomorrow at GMT +3 time at 10 o'clock, there will be a quantum physics section. And yeah, I guess with that, thanks everybody. Have a good day or night.